The second International Quantum Communication Conclave, organized in collaboration with CDOT and TSDSI. It's our two-day event, which was inaugurated yesterday on 15th of February 2024 in the august presence of respected Dr. Neeraj Mittalji, Secretary Telecom and Chairman, Digital Communication Commission, along with Professor Ajay Kumar Soodji, Principal Scientific Advisor to Government of India, Dr. Subrata Rakshit, DG Technology Management, DRDO, and Srimati Triti Saxena ji, Senior Deputy Director General and Head Telecommunication Engineering Center. So on the second day of this conclave, we welcome all the speakers, experts, officials from the different departments, organizations, industries, startups, academic and research institutions, guests and speakers who will be joining virtually, and those who are connected online. We welcome you all in this second International Quantum Communication Conclave. And today we have sessions on quantum networks and post-quantum cryptography. Then we'll have a session on standardization efforts towards quantum technologies, later emerging trends in quantum technologies, and thereafter panel discussion on applications of quantum technologies, deployment perspective and use cases. So now we'll start with the first session, or shall I say the first session of this conclave, which is on quantum networks and post-quantum cryptography. We'll invite our speakers, but first, ladies and gentlemen, we have Professor Anupam Chattopadhyay. He is joining online from Singapore. And to tell you about Dr. Anupam Chattopadhyay ji, he's a distinguished researcher, serves as an associate professor at the School of Computer Science, Nanyang Technological University, Singapore. With a PhD from RWTH Aachen, Germany, he has an in-depth domain expertise in hardware security, AI security, edge computing, cryptography, and federated machine learning, contributing significantly to the academic landscape with over 250 published papers. So we have with us Dr. Anupam Chattopadhyay ji. Welcome you, sir, in this session.
Okay. Thank you for the welcome message, and thank the organizers for inviting me to speak to this very exciting development in International Quantum Communication Conclave. Unfortunately, I couldn't be present in person, but I would be very much eager to look forward in future editions of this conclave or trying to meet in person with all the audiences there whenever the opportunity arises. So today I will talk about quantum safe digital world using PQC. We have a small slots. I will try to cover the key takeaways and information in the following few slides. The first thing that I'm sure most of you are very much aware of, that there is a growing threat of quantum computers to break public key cryptography. So this is one estimation that was released in 2019, which shows that the current public key crypto systems, which are at the very heart of all the security protocols that we are using in the digital world, could be broken within few hours if we have in our access a large enough quantum computer. And this is an estimate which is continuously being refined over the last few years, and we have been working on also on this topic, which is otherwise known as quantum cryptanalysis, that these numbers are coming down, and at the same time the capacity of the quantum computers are growing. So some people, the argument can be that if the quantum computers are not there yet, why do I have to worry? But there is a very clever deploy that is already happening, which is called Harvest Now Decrypt Letter, which basically tells that there are some data which are having a long shelf life and being encrypted with the current crypto systems. So if you are taking data in the banking, insurance, or life sciences sector, they are supposed to be preserved for more than 20, 30 years. And this is mandated by the different government agencies around the world. So if I need to keep a data for 30 years and I'm encrypting it with the RSA or ECC, then it's very likely before that time we will have a quantum computer to break into RSA and ECC. So And it has been reported also that there are cyber criminals or malicious actors who are storing such data set right now so that this can be decrypted later. Besides, we also know that in the past history of information technology, the migration from one crypto system to another crypto system takes tremendous effort. And here we are talking about the migration of a protocol which is at the backbone of every digital industry, which means that we have to move fast and we have to move with caution. So this is something that is already happening. There are multiple countries that have released their standards. They have started adopting the defense in form of post-quantum cryptography. The standardization bodies across different industry verticals are coming together. Major industrial players are launching their PQC-enabled services or products or doing testing. The examples like France has tested in 2022 already post-quantum secure encryption for diplomatic messages. So now for some people, this is actually moving hand in hand with the other possible defense to quantum computing based attack, and that we call as the QKD. To give a better picture of the entire thing, we try to segregate this domain into these three clusters. One is quantum computer, those itself, like D-Wave or IonQ, Honeywell, PsiQuantum, they are developing the quantum computers. And then we have a technology called quantum key distribution developed by ID Quantic, Spectral, Cryptalabs, which are trying to address the threat from quantum computer by spreading the key across a specific dedicated network of quantum key distribution. But however, there is another possibility also of defending against a quantum computing based attack. And there are companies, including some spin-off that we are also trying to work on in Singapore called PQ Station, which is offering specific solutions with algorithms that are resistant to quantum computing based attack. Now, how do I know when to take up QKD or when to take up PQC? So these are the two different alternatives for defending against attacks. And this could be summarized in some comparisons, like what I tried to put here, that in case of QKD, we will definitely need a new infrastructure with optical fiber, photon generator receptor. And PQC is working on the standard telecom infrastructure that we have now. There is a limit to the currently available QKD solutions over the range that the key exchange can be done, whereas PQC does not offer such limit. QKD can only achieve the security objective of confidentiality between a sender and a receiver. It can exchange the keys. Whereas in PQC, one can do all the traditional security objectives like confidentiality, integrity, authenticity, non-repudiations, and so on. There has been a dearth of standardization in QKD, although it's coming up now, and very recently they have announced the QKD standards, whereas PQC standardization moved much bold and faster. There are organizations like BSI in Germany, they have released a PQC standard long ago, and NIST also released the standard last year with some more specifications being developed by NIST. So direct applications of QKD, yes, it can work on quantum random number generation, sensing, key distribution, whereas all the digital data in rest and transit we see now, they can be handled with PQC. So essentially PQC offers everything that the current public key crypto systems do offer. So realizing this contrast, actually the QKD companies like ID Quantic, they offer the quantum key distribution as an additional layer on top of existing asymmetric cryptography, which itself is vulnerable. So they basically move by adding post-quantum crypto together with QKD. So in essence, there can be a simple and direct transition to PQC without having to worry about infrastructural updates or having to worry about the distance limitations. But there are also very niche and specific application domains. If there is a private network within an enterprise or a network within a specific physical perimeter, then people may also opt for setting up QKD for that purpose, or maybe ground to satellite communication to have with the QKD. So they do offer some complementarity, but in order to move moved with the migration first, PQC seems to be the safer option to adopt. And this is also corresponded and corroborated by a very recent position paper that is released by multiple governments in European Union who clearly claim that QKD is not yet mature enough for mass adoption. So now coming to the big question of the PQC migration, there are already some white papers released on how the migration would happen. Basically, it all started from 1994 when it was shown that quantum computers can break security. In 2017, NIST initialized the standardization process. It announced the first standards in 2022 and 2023. This is corresponding also at the same time with White House released a very specific memo on adoption of PQC definitely by a certain time period. So what we see is the post-quantum era is actually beginning in late 2030s, and there will be a Y2Q or years to quantum moment. This moment when we will clearly see that the quantum computers are breaking RSA and ECC. So we started our research in 2017 and we are now preparing for the long PQC migration. So in our research, we mostly were focusing on the side channel analysis and fault injection analysis. So if you think of the traditional crypto system, where there is an encryption and a decryption with an Eve trying to either modify or listen to the messages, this is not any more complete scenario. We definitely have to look into all possible side channels that are visible or modifiable by Eve. So this is the realistic model of a physical world where cryptanalysis goes hand in hand with the platform-specific details. So this is the setup that we have, one of the state-of-the-art setups with the many custom-designed boards for performing side channel attacks and fault injection attacks on varieties of FPGA boards and microprocessors that we can conduct here. So our lab is also helping with the evaluation of latest gadgets and devices on their side channel vulnerability. So based on this setup, we were able to make a huge impact on the post-quantum crypto standardization, in particular lattice-based cryptography. So there are a couple of surveys that we did on the optimization and implementation with side channel attack robustness for lattice-based cryptography. There are multiple physical attacks that we did, which led to, in some cases, a modification of the algorithm itself, including hardware trojans and backdoors, which are very stealthy and very difficult to detect. There are corresponding works that we did in order to defend against these attacks, which are countermeasures. Often countermeasures are bulky and can slow the system down, so we provide some optimizations. So these are purely IP level studies. But beyond this efficient software and hardware implementation of PQC, we also moved on towards the efficient solution integration, like integration together with a security protocol, like the TLS protocol, or integration together with an application, such as a browsing application where the PQC can be embedded. So one such application that we also looked into is a secure boot flow. In a typical processor, secure boot is one of the first and most important defense mechanisms. So currently the secure boot that is embedded in most of the commercial processors, they go through the phases like zero stage, first stage, bootloaders, initialization of kernels, and beginning with the user space applications. So we actually verified the kernel in the first stage and zero stage bootloader using post-quantum digital signature and benchmarked whether it is slowing down or it's improving on this. So you can find more details on the research papers that we published on this topic. So what we bring to the table is an academic research in collaboration with the IACR, SCM, IEEE, with 50 plus research articles in PQC, 100 plus research articles in general domain of cybersecurity. We were deeply involved in the standardization process by participating in NIST standardization forum and identifying loopholes and weaknesses in different algorithms. So we do have very efficient implementation both in software and hardware for different platforms like ARM, GPU, FPGA, and ASIC-based technologies for key exchange and digital signatures. We created a secure protocol test bed which, for example, could be catered to the automotive sector for post-quantum cryptography. We do have prototypes of devices that are very useful for custom side channel attack and fault injection attack testing. This is used in our security evaluations. So to summarize in a very short span, what I could cover is that PQC definitely ensures and brings us a quantum safe digital world. This is standardized through NIST. We did and we are still doing a very detailed evaluation of their implementation and side channel analysis. It is important to realize that there is already a threat looming large for harvest now, decrypt later, and we should start the process of post-quantum crypto migration, which requires elaborate planning across all different technologies, industry verticals, and application scenarios. So this also has to be considered with synergies with traditional security protocols and how this can move ahead with quantum key distribution. Like one of the challenges in QKD is that one needs to classically authenticate the sender and repeater nodes between a photon generator and receptor. This classical authentication can only be achieved if we have a post-quantum crypto there. So with this, I would like to conclude my talk. I can be reached at any time with my email ID, and I will be very happy to set up individual discussions, be it on a research collaboration or be it on a technology commercialization for post-quantum cryptography. Thank you very much. If I have some time, I can also handle questions.
Thank you so much, Dr. Anupam Chattopadhyay ji. Thank you for joining in from Singapore. And now, ladies and gentlemen, may I invite our other speakers on today's. Dr. Natarajan Venkatachalam ji, I request you to please join us on the dais. HOD Quantum Security Group, SETS Chennai. Next, we have Colonel Sai Shankar ji, Vishish Seva Medal Indian Army. Dr. Ramchandra Rao Yella ji, School of Physics, University of Hyderabad. Dr. Rajkumar Kittimuthu, Ergoni National Laboratory, USA. And we also have with us Shri Srinivas Hegde ji, CTO of Secure Machines Private Limited. Ladies and gentlemen, can we welcome our speakers on the dais, please? Thank you. And I'll now request Dr. Natarajan Venkatachalam ji, but before inviting him, let me share a few things about you, sir, please. Dr. Natarajan Venkatachalam, currently scientist at SETS Chennai, has worked in the cybersecurity area for nearly 14 years. His research on secure quantum communications and experimental quantum key distribution systems is focused on the fundamental and applied quantum cryptography. So I'll request Dr. Natarajan Venkatachalam ji, please.
Good morning all. Thanks for the opportunity. So in this talk I am going to focus majority on the quantum networks. So at the high level how the quantum networks is being looking for. So it is more of a computer scientist view how the entire quantum network looks and what are the challenges when we try to realize in the field the quantum networks and what are the opportunities. So if you look at the quantum network is similar, the classical network, we try to exchange the quantum information through one device to another device through a dedicated channel. Right? So if we take a analog, classical analog, when the computer network been introduced, it is basically connecting two classical computers and through a network, say, transferring data. So that's where the computer networks been started. But there at the time the computer was well established, 19th century. So there is no problem where one can transfer through a different protocols. That's where TCP/IP was created. But in quantum network the scenario is different. If you see the computing and communication is little well ahead, and then now the boxes are ready, the network is already been progressed. So, but the quantum computer is not arrived. Right? So the challenge here is where you no need a computer, still use a two device and you can exchange the information. And the protocols itself is different, and there are different mechanisms one can realize in different categories of protocols. So in that case, how are we going to handle when we take it as an interoperable system, or when you combine with the multiple protocols together and different technologies? So in this talk, I'm going to abstract the quantum layer, which is a hardware layer. But what if the upper level? How are we going to connect these devices together and to different purpose? One is for a quantum communication, another computing. See, we cannot directly run a single quantum computer. Now already there are systems where a classical client can interact with a quantum computer to perform a task. What if I distributed quantum computing environment, if I connect quantum computers together? And now the sensor field. So sensors also cannot be attacked. So it needs to be connected to together, it's a sensor network. So in that case, how are we going to build such a network? What could be the topologies? It is more of an academic view, but it has a practical consequences. So as I said, there are features where one can exhibit its superposition and entanglement. In future, there are many more quantum mechanical properties can emerge. And it is basically a process of transmitting a qubit in form of quantum information to one device to another device. These are like some of the network architectures that been ported in some of the networks. Thank you. So the other thing is what the structure looks. So some of the papers that are realized that fundamental difference between a classical network and the quantum network is classical network, the algorithms and protocols deals the information as a logical bits, zeros and ones. But what more than that, the quantum information is no more a logical bit, it is a physical objects. It's a quantum is a physical object. There is a mechanical property associated that one can deal with when you setting up the quantum network. So there is a physical layer also plays an important role in this quantum network. And the logical, always one can connect with the different logics as well. So the key components in these networks are, because networks we all know the topologies, collection of nodes, where different nodes connected together and then forms a network. So these nodes are quantum processors basically, right? So the nodes which are connected in the quantum network are quantum processors, which can generate the quantum data, manipulate the quantum data, and measure the quantum data. That then also the connecting these nodes called edges in networks. Here they call as a channel, because the quantum channel, it could be a free space channel, or it could be a fiber optic channel, or a cavity channel, where one can connect these quantum nodes. And then various way to realize, one is the repeater, where one can boost the, since it's the long distance is a problem, where one can segment these part and partials and boost those things. And then memories, that also one of part when we store the information and retrieve. And the other things are classical in nature, but it's very important. I always say that the heart of the quantum computing as well as the communication is the optics are the heart of the system, wherein the classical processing is a brain of the quantum computers. It's true for a communication system as well, where optics plays a heart as a role, and the processing engines as a brain, which enables the entire system. So wherein the error correction and the controlling system also is very important for. So it's kind of an application where and all the quantum networks can. One, it's obvious case, if you look at the literature past 20 years, where the quantum networks only talks about QKD. When I say quantum network, it is a QKD network. But the scenario is little different. We are not only using the network to distribute the key. There are many applications. So in this slide, it talks about what are all possible applications where of the quantum networks can be used. One is the cryptographic, of course, sharing, distributing a key. So other one is the communication. As I said, the quantum computing, it's not only a DAC, it's going to be a distributed. So in that case, enable a quantum distributed computing, it requires a connection of a quantum computer network, and then quantum internet, and then sensing. So as I said, the sensor, because the sensors are now picking up, because you can perform a high precision measurement for sensing and other applications, defense applications including. So the sensor networks also it's required to connect with across the networks and the internet. So these are the some of the applications where one can bring in the quantum network. It's essential also. And also like quantum computing, the quantum communication is also not a general purpose. It is a specific purpose systems where you cannot afford for at least the current nature of this concern. Okay, so like now the parallel, if I take how the classical versus quantum. So if you look at this tag here, in the green and the red ones, so we know the well-established OSI model for a classical network. So what if in the quantum network? So we are clear about there is a hardware, dedicated hardware. It could be use any technology. It's an ion trap or what superconducting. Or you can use prepare. What type of? It is in physical layer. So what if the intermediate layer looks like? So there is not much focus on this aspect. One can realize how do we handle a different kind of a technology hardwares to bring a network enabled. So application level is going to be the same. So we are not going to touch because the applications are well established. But the intermediate layer is a question, and not much efforts been invested to how do we bring the entire quantum network is enabled. And this classification, if you say the classical network, we know the classical communication is internet. And also we have a super dense coding where it is a hybrid form of computing, where use distribute a classical 2-bit information, 1 qubit is enough. That's already is well established protocol. So what if I use it in a quantum internet? So what are the protocols that one should realize? What are the stacks one should build to make entire quantum network is enabled? So these are like type of networks. It's again is a theoretical level classification where the immediate time, the trusted repeater networks where one can enable with a repeater, and then prepare and measure networks. It's already in QKD people are using to make a prepare and network, and entanglement based distribution based networks. Already very few experiments been done. So because the QKD is a 2-party protocol, how can I make it multi-party? So because the 2-party is very difficult in a network. So how can we make it as a multi-party protocol wherein entanglement distributions can be used, and then quantum memory based near feature and the fault tolerant, and finally the quantum computing network where quantum computer can interact. So this over the period of time it is published, and the functionality wise it is more powerful when you compare from top to bottom. Okay, so now the challenges, how the quantum network challenges. So I'd like to remind yesterday's the first talk, Dr. Rakshit mentioned that there was an objection from NSA where the QKDs are not for the security. So also there was a paper subsequently published to respond their NSA's objections. So mainly their objection is the QKD systems are not practical at this point of time, and so it is not recommended for implementing for strategic agencies. But I just want to bring a highlight in the security point of the table here. Yes. So there is a comparison between the PQC and the QKD. So now the at this point current time and midterm and the long term. So when I say in research, it's now midterm is like 2 to 5 years, and the long term is 10 years the time. So according to the literature. So now one should analyze in the security in 2 different ways. One is the protocol level security, another one is the implementation level security. So the protocol level security, when I say the crypto by design. So how strong your crypto system by design? How strong your crypto system by implementation? That's the 2 ways one can look and observe the crypto systems. So by design, if you see, PQC is all again a conventional algorithm which is based on the mathematical hardness. Right? So again you build a strong mathematical cases where one can, it is a hard for a certain time, but the time the hardness can be shrinked over period of time. But the QKD convenes that protocol which is based on the quantum mechanics principle. Even if you bring up with the new devices or new such algorithm, the hardness still remains the same according to the quantum principles, right? So you cannot. So that's where people say hack-proof communication or unconditionally secure. It's the difference between the conditionally secure and unconditionally secure, where the hardness of the mathematics remains on the PQC algorithms. It's conditionally secure over the period of time. Let's say 10 years or 15 years. But the quantum QKD systems promises it's unconditionally secure. If you look at the protocol level security, all terms it looks good. Though it is a categorical measure, everything it has a proof, experimental proof. But in the PQC system, now the system itself says it's a time it may be go bad or mid time. For a good example is there was a psych algorithm, super singular isogenic key encapsulation mechanism algorithm. Within overnight it got broke. Right? So that's a good example where a PQC can be broke because of the even classical computer they have demonstrated. So implementation wise, yes, PQC is evolved over a period of time, and the cryptographers in post-quantum, they are well good in experiments and implementing things and convincing a NIST. So they are very good, reasonably doing good in this area for now on. But since the quantum QKD based implementation is not yet mature, the hardware is not yet mature, the software is not yet mature, the quantum cryptographers is like they are little lagging to convincing the standardization bodies. That's the reason now at this point of time QKD looks little bad. But over the period of time you can see the mid time it's going to increase because we are going to evolve with the new techniques to how can we build these gaps. Right? So over the long time it says QKD is a good solution. So it is an observation that one can understand the QKD provides a long-term security than the PQC. But it's going to be a hybrid solution because certain cases QKD cannot. Say for example, a QKD is a end-to-end solution where the key resists in the box. But how can I going to transfer the key to end user devices? That's a gap, right? Last mile thing. So there you can. So the hybrid is going to be an ultimate solution. But to respond the NSA objection, it's already been recorded in NSA website also. So another challenge is, say the systems are ensuring the security. So what if, how can I guarantee that formally verify whether it is performing correct or not? Either as a computing system or a communication system. How can I verify the correctness of the system? So still there are a lot more attention one can form up. But how do I validate the system, correctness of the system? Another thing is, as I said, it's a large scale implementation. It's a two-party protocol. How can I make it a multi-party? Because it's two-party, it's very difficult to convince the entire ecosystem. And integrating with the existing and classical system is another problem. And the cost-wise is another challenge. These are the major challenge one can focus. And I said the diagram represents the hardware and the equipment and put together to make a system. So the opportunity-wise, yes, I said the coexistence of classical and quantum needs to be done, and testing and analysis of validation is very, very important. And the effective systems, the software need to be matured enough to handle these kind of challenges and performance-wise as well. So with this, I thank you. Thanks for it.
Thank you, Dr. Natarajan Venkatachalamji, for speaking on quantum networks and post-quantum cryptography. And I would like to request all our speakers, because the time we have kept for every speaker is 15 minutes, so kindly adhere to that, please. Thank you. Next we have, ladies and gentlemen, Professor Colonel Sai Shankarji. Colonel Sai Shankar is presently Director of Vediti Working Group in Army Headquarters, responsible for implementation of the app Pan Army. He has developed indigenous app, Sai app, akin to WhatsApp, Telegram, etc., for the armed forces to eradicate the use of such platforms for any official communication. He has also implemented quantum secure audio-video solution and quantum secure VPN for this app. For his outstanding work for implementation of Sai app, he was awarded with Vishish Seva Medal in 2021. So now we have Professor Colonel Sai Shankar.
Jai Hind everyone. First of all, I would like to compliment to the organizer for organizing for such a wonderful talk and conclave. People and audience may be a little bit mesmerized. What are the images of Hindu gods are doing on my first slide, and when which we are going to talk on such a complex and modern complexity. I'm reading quantum science from the last 5 years, and there are a number of questions which are left unanswered. So when I'm doing the deep research, so I found that number of scientists, especially from US and Europe belt, are reading and coming to Banaras and various places, reading Sanskrit and going deep into the Vedas. So once you started, I said why they are going to Vedas, then I've started reading Vedas from the last 1.5 years. So the number of questions which we do not understand from the modern physics is being answered by the Vedas. So this is the reason that the images are there. It has nothing to do with religion. Now coming to this, the presentation I will be cover on the following subways: basics of quantum science, what are the application from the, especially from the defense perspective, and what are the recommendation as a common one which we think. Why I want to cover the basics of quantum science is that yesterday while I was having an interaction with a number of people, the students, the decision makers, and also the senior people, they are supposed to take decision, but somehow they don't understand the quantum in totality. So I thought that let's have a few slides on it, so that it clears the cloud and which will assist the decision makers because of their seniority and experience. They cannot ask a open questions. So this is the basic overview. I am not a scientist, I am not an academician, I am a pure ground soldiers who understand quantum from the bird's view. If there are some issues or something, I would be happy to take the observation offline to update myself.
For most of our history, human technology consisted of our brains, fire, and sharp sticks. While fire and sharp sticks became power plants and nuclear weapons, the biggest upgrade has happened to our brains. Since the 1960s, the power of our brain machines has kept growing exponentially, allowing computers to get smaller and more powerful at the same time. But this process is about to meet its physical limits. Computer parts are approaching the size of an atom. To understand why this is a problem, we have to clear up some basics. A transistor is just an electric switch. Electricity is electrons moving from one place to another, so a switch is a passage that can block electrons from moving in one direction. Today, a typical scale for transistors is 14 nanometers, which is about 8 times less than the HIV virus's diameter and 500 times smaller than a red blood cell's. As transistors are shrinking to the size of only a few atoms, electrons may just transfer themselves to the other side of a blocked passage via a process called quantum tunneling. In the quantum realm, physics works quite differently from the predictable ways we're used to, and traditional computers just stop making sense. We are approaching a real physical barrier for our technological progress. To solve this problem, scientists are trying to use these unusual quantum properties to their advantage by building quantum computers.
So, as you have seen just from the video, so what I'm trying to bring out, whatever the equipments or the technology which you're seeing as on date, this projector, the computer, everything, they're based on the classical physics. But whatever the upgradation, when we are trying to increase the computing power, the physics is not behaving or it is not answering the way it is supposed to behave. So that is the reason where the scientists started looking for answers and where is the quantum physics came into existence. And that is the reason from the last 30 years they are working deeply. And if after this conclave, if many of the people come with this thought process, yeah, this quantum mujhe to bilkul samajh mein, not an issue, you have a good IQ, because many people don't understand quantum. Quantum is not supposed to be understood, it has to be felt. So these are the few major reasons why the people have gone into the quantum and in everything. But the two words which are important from the quantum perspective is that exotic and counterintuitive. The moment we apply logic, the quantum will not be understood. Over the last 200 years, we have been trained like this. If 1 plus 1 is equal to 2, then only I will agree. But that is not how nature behaves. Nature is never binary. It is quantum in nature. So let us see how things are happen and why I'm focusing on this word counterintuitive. Means when we try to look for answers, logical answers, they are not answered, but they start happening on the ground. And we see why it is happening on the ground, then again that logic fails. So there are a number of terminologies that are associated with quantum, but few terminologies, especially from the difference perspective and from the other perspective, are superposition and entanglement. If we understand these two definitions properly, then we can see from the 90% of the applications are based on these two definitions only. Now, what is superposition? Superposition is nothing but ability of a system to exist in multiple states at a point of time. So let us understand with a small few example is this. Suppose I flip a coin, the output is either head or tail. But this is what a classical physics says, that I can have a state either head or tail at a point of time. Where a quantum physics states that not only will I have head and tail, but I will have a combination of head and tail at the same point of time. That is the simple way explanation of superposition. So now this is a classical example where we exemplify head and tail. This is the same answer comes from Mahabharata, where the Ras Leela, where the Krishna at the same point of time has the ability to dance with thousands of gopis at the same point of time. How can a Krishna can at the same point exist in multiple? This is the classical example of or quantum example of superposition. Now coming to the entanglement. Now entanglement is that if two object states are entangled to each other, if I change one state, immediately the other state will change. So let us try to examine again, understand with the help of example. Suppose I take two coins, I rub it out, and I place one coin here in the New Delhi and the other coin at New York or Bangalore or any place. There is no optical communication, there is no microwave, there is no satellite communication between these two coins. I flip the coin here, immediately, instantaneously, the other coin will also get flipped in New York or wherever place. This is the entanglement. And now if you want to understand with this small example is that if everybody have seen a Salman Khan movie called Hello Brother, where the two twins are there, if one twin does some action, immediately the other action is done with the other twin. This is the classical or quantum example of entanglement. Now again coming to the Mahabharata, we get an example of entanglement is that when this king is not able to see the entire war, and he asks his Vidur, please tell me what is it. So Vidur has this capability, has an entangled state, one sitting in the war scenario and one sitting in front of the king, and he is able to see it. Whatever the changes are happening in the war, and he is able to see it here. So this is again example of entanglement. And the third and last example of quantum tunneling, where we have just seen, if there is a barrier, the electron requires some amount of energy to overpower the barrier. But in quantum physics, without this energy, the electron is just moving through the barrier. So this is called quantum tunneling or quantum teleportation. This is nothing but, if in our old age, with Ramayana and other serials which you have seen, a rishi sitting in this closes aisle, and in a second he moves from Prithvi Lok to Swarglok. That is an example of quantum tunneling. So having this, these are the major applications. Just have an overview. So from the defense perspective, these are the major applications. So let us have an overview. What is quantum computer and why it is so relevant? Everybody is saying it is breaking the encryption. What has suddenly it has come into so powerful? Let us read it. So we all understand classical computers. They work in the principles of ones and zeros. So either it will be 1 or 0. As I mentioned, quantum computer work on the principle of quantum physics. So it is not only ones and zeros, but a combination of ones and zeros. That is the power of superposition. So this is nothing but just ones and zeros. So if it is, okay, the state is in multiple states, so how it is going to affect me, how it is going to help me out. So let us again try to small example. So I have a brand new Firefox cycle. So I have two friends, or you can say two thieves are there. One is a classical thief and one is a quantum thief. A classical thief has a classical computer and a quantum thief has a quantum computer. So I don't want to give my bicycle to him, so I have used a lock, and this lock has 3 combinations and each has a 0 or 1. So if you see that number of combinations that are possible are 0, 0, 0, 0, 1, 0, 0 like this. So 8 combinations are possible. So when a classical thief comes, he first applies 0, 0, 0. Lock doesn't break. Let us assume that the lock is 1, 1, 1. So at the 8th attempt, he is able to break it. Whereas the quantum computer, if it is a 3-qubit quantum computer, this all 8 states are available to him at the same point of time. So he will be able to break in 1 second or 1 go. So in this, what I'm trying to bring out, if it is a classical computer or classical thief, he took 8 attempts to break it. whereas a classical quantum computer or a quantum thief is able to break in 1 second. So today you have a 64-bit, or today you have 32-bit. So number of combination are 2 to the power of 64 combination available. But this combination are available to you at one point of a time. Suppose you have a quantum qubit with number of combination, like suppose 64 qubit quantum computer, you will have 2 to the power of 64 qubit quantum computation available at the same point of time. That is the reason why Dr. Natarajan and the previous professor also brought out where the quantum computer comes out, all our encryption will be broken in days and seconds. That is the threat. So these are some of the slides or some of the information. They say that 3000 qubits it will be able to break, is more powerful than the entire quantum computers. So what are the advantages when such a huge amount of, tremendous amount of computational power is available to you? So if such an amount of this has the various power available, but especially from the defense perspective, it is able to break every level of encryption. So it has two use case, two scenarios. I will be able to break enemy communication. I will be able to hear what are its plans, what are its strategy. And at the same point of time, if the adversary has a quantum computer, he will be able to break my communication, and he will be able to understand what are my plans. So it has both ways of implementation. Now is the threat real? So there are a number of papers which are coming with them. We can see, take it with a pinch of salt, but this is a recent publication around 6 to 7 months back, wherein a group of scientists from China claim that they are able to do cracking RSA encryption. And for all general knowledge people, the banking application we use, the HTTPS, railway reservation, everything, they uses this RSA. So, okay, now we have a good gyan of quantum computer. So, this is going to break my every level of encryption. The bank sector is at risk. The finance sector is at risk. The railways are at risk. The telecom department is at risk. So, what I should do? So, again, the answer lies from the field of quantum only. Yes, there is a threat. Then how does the protection also come from the domain called quantum cryptography? Quantum cryptography is it is a sub-subject of two branches, which is quantum key distribution and post-quantum cryptography. Let us have a quick overview. Now coming to both this post-quantum cryptography and the QKD, they are only key distribution mechanism. They are not encryption algorithm at all. And we have to see and do the implementation from that angle only. And the PQC has nothing to do with the quantum. It is based on pure classical physics and pure classical mathematics. And we use hard problems like lattice-based cryptography or multivariate-based cryptography. Now coming to the quantum key distribution, it has been covered subsequently. I don't like Alice and Bob, so I'm fond of Ram and Lakshman, and the eavesdropper is the Ravan. We have to work from this angle only. See that unless until the thought comes from the inside of the heart, you cannot implement. You will always be a follower. I say that be a student, not a follower. You read everything, apply everything, and apply your own brain. So these are again QKD protocols where it has been covered sufficiently. It is where the Ram and Lakshman want to communicate secretly, and they don't want Ravan to hear it. The secret keys between the two people are used whether generated, they are not distributed. I will use the word generated with the principle of quantum physics. And once the keys are generated, they can use any encryption algorithm, block cipher, AES or ChaCha20 to implement the encryption. Now QKD, once I get such a high rate of the keys, so one of the most protocol which is very difficult to implement or to break is one-time pad. But why we don't implement one-time pad? Because it requires there are two characteristics of one-time pad. The length of the key should be equal to the length of the message, and every key should be encrypted by a different. Every message should be encrypted by a different key. But both are scenario not feasible, so we are using one-time. So the quick comparison of QKD and PQC, I believe to that. So is the quantum threat real? Yes, the threat is real, and the immigration has started. But surprisingly, at the national level, we are not yet come up with a roadmap. Now coming to yes, we have seen quantum computer application, cryptography and sensing and metrology. We are aware that all the navigation are done in the GPS environment, and we are aware what happened in Kargil. The GPS was denied to us. It was spoofed to us. So we had a tough time. But what we can do, entire our satellites are based on GPS. So if you have a GPS navigation using the quantum physics, you will be able to use it. There is nothing but we used to, before GPS there were gyroscope and other mechanism, but they were not used because their efficiency was not there. So coming to the navigation, yes, submarine is one of the use case. What happens, the submarine for the GPS, it is most of the time it is under the sea. Ma'am, I will take 2 minutes. For the GPS lock, it comes to the surface. The moment it comes to the surface, it is prone to attacks. So if you have a navigation system without depending on GPS, the submarine can under the sea for months and months without under detection. So radar, just have a read and I will try to explain. So quantum radar work on the principle of entanglement. This is the class radar. So I eject an electromagnetic wave, the aircraft observe or deflect, I do the detection. So if it is a stealth aircraft, the detection is very, very low. But if I have a quantum entangled radar, I will take two entangled, one entangled photon I will fire towards the radar, another entangled photon I will keep myself. So if any changes happen on the aircraft or the touching, immediately the changes will happen on the ground and I will be able to detect it. So these are from the public domain, true or false, I will not debate on it. So quantum sensing, yes, where I will be able to sense throughout the walls, throughout the radars also. So if it is an attack on Taj Hotel, so if I have a quantum camera, I will have ejected entangled photons and it will have mapped the entire rooms of the Taj Hotel and I have got the picture before the energy commandos can take into action. That is the power of quantum sensing. So we have different types of antennas for different frequency range. So if you have something on Rydberg atoms, you can have one antenna for all the ranges. No, it's in a nutshell. So what are they? It can break enemy communication. We can secure our communication. We can detect stealth aircraft, navigate in a GPS and denied environment, and also this. So what is the defense contribution? The first QKD trial has been done with the help of a private company called QNU Labs in the year 2020, and immediately followed by in 2021 we have done the trial with CDOT, and this was the first QKD link at that time. As Professor Raghavan has mentioned, please don't go to the media. We are not going to the media. The first it was done way back in 2020-21, 54 kilometers between Chandimandir, that is Chandigarh and Kasauli. And now coming to the quantum secure audio video. The project was funded by NSCS. It has been implemented by a private company called SkyTel Alpha Private Limited. And for a VPN, we have something called developed by quantum secure VPN by IIT Kharagpur. In addition to this, we have a training institute called MCT MAU. We have a training lab also. This is our defense contribution or the way we are having it. So these are the first feature of the first QKD trial which was done way back in 2020. So people take that how it is you're talking about quantum computing proof. So this is a quick overview. So we have the entire computing suite consists of three vertical: key generation, key distribution, encryption. For key generation, use PRNG, key distribution, use PKI, and encryption AES. So we replace PRNG with a QRNG, PKI with a PQC, and AES with an indigenous encryption. So this is the indigenous. So what I'm trying to bring out is that even as a nation, we got liberated from the last 50 years. We have the best mathematician. Till we are using the entire crypto suite developed by NIST and everyone. We have yet to have an encryption algorithm. We produce the world best mathematician. Publications are happening day by day, but we are yet to do. Entire crypto suite of you take any organization of the India, we are using only foreign crypto suite. So this is India's first quantum secure audio video solution, like your WhatsApp party of 8 called. We are just having this. So okay, I know ma'am is there. I'm out of time. I will request the audience to just hear me from the last 30 seconds. As I mentioned that if you see the niche protocols, surprisingly, even we have the best academician, mathematician. I'm not doubting, I'm not questioning anyone. We have not a single application contribution from our submission for the PQC. Today also all the PQC we are using from outside. We recently came to know there is one submission, but and people should understand this is not an upgradation from 1G to 2G or 3G to 4G. It is in quantum physics. It is a separate science of physics. It has to be seen from that vertical. People think that it is an upgradation. No, what is it? Upgradation takes place in the existing science. It is in separate science. And the second part, in addition to the DRDO, defense should also take part, lead into the R&D, because we are the user, we understand what is our requirement. So we request the academicians also directly interact with the Army headquarters, directly understand our use cases and take it ahead. And as I mentioned, there is a threat. We should not wait for the threat. We should upgrade our consumption. And this triad is very much important. Unless and unless this triad is not, things will not move. The government, industry, and academia. The R&D institutes can keep developing the products and keep the POC, but unless and until the product does not go into the field, they don't get the feedback, that will not improve. Please give the TOTs to the companies. Let the startups take it. Let the startup take it to the industry. R&D institute cannot do L2, L3, L1, L2 support. That is the role of the startups or the group. We have the national level project, NQM is where the multiple agencies are coming under one roof. How it is going to implement that, I do not question. But if I have given the power, I will bring all the mathematicians, all the physicists, all the opticians, all the computer players at one place and make them sit and do. Individual project given to different people at different places and then combining together, I don't know. My mother says a simple thing, अगर मुझे खीर बनाना है तो शक्कर, चीनी, दूध सब कुछ यहीं ला के रखना. उधर से जाके पहले वहाँ से नहीं हो सकता. You have to, in all the ingredients should be one place. And last, we are looking from the modern perspective of the physics and everything, but I request the decision makers to look from the Vedic perspective also. I'm not saying that close your minds to the mathematics, close your minds to the physics, or the please from the Vedic, combine together. There will be some indigenization. We will do something better for the others. That is our request. And all the R&D organizations today is so like this. And last not but the least is that we have missed the semiconductor bus. What reasons we have missed, that I don't want to comment on it. But nature give a chance to every nation once in a time. Whatever the progress that have to happen in the classical physics is happen. Now it is a chance of the quantum physics. We are investing a lot of money to the IITs and the industries. I spoke to the PhD students and why you are leaving the nation. To make an IIT or PhD student, the government spend lot of money to them, and the money is by whom? That by the taxpayer, that rickshaw wala, the pantela, who is giving the money. Now these students get the money, get the PhD student, they go to outside India, they work with Hughes or any one company, and this Hughes and all these companies sell back to this product. So it is like that we are giving the money, or we are becoming an IT coolies to most of these world countries. Then the second question asked is that why you are not, sir, we want to work in the nation, but their infrastructure is not there, the environment is not there. So what I'm trying to bring out is that please don't work for yourself, please work for your generation, for grandchildren. If you want them to be in the nation, in the country, to see your age dying, you have to create the infrastructure. That's it. Then.
Just actually your talk is quite patriotic, and whatever you have said, like Vedic science, actually what is happening, the Veda has been treated as a religious text, but it is not a religious text, it is a complete science. But what happens, to understand Veda, you need to have Sikkha, Kalpa, Vedanga, Nirukta, Vyakarana, Chanda. All that same person has to read all these things. Then only he can decipher what is written in Veda.
Sir, if you allow me, we'll open the forum later. Can we just
1 minute?
Please,
1 minute.
Jay.
So I request, particularly yesterday, the science and technology and defense, we should also include Sanskrit professors who are experts in Veda to be in the quantum mission. That is my suggestion. Thank you.
Thank you. So, ladies and gentlemen, we had Professor Colonel Sai Shankarji. And thank you, Professor Colonel Sai Shankarji, for making it so easy that a layperson like me can also connect with. Thank you so much. And now, ladies and gentlemen, we have Dr. Ramachandra Rao Yalaji. He's currently working as an assistant professor in the School of Physics at the University of Hyderabad. His research interest is mainly in the area of quantum photonics and suits commercial applications in quantum technologies. We now have Dr. Ramachandra Yalaji.
Okay, good morning to everyone. Thank you, madam, for your nice introduction. And in first place, I would like to thank the organizers giving me the opportunity to speak about our work here. So today I'm going to discuss about, I'm an experimentalist, so I'm going to discuss about how to develop a fiber-based nanophotonic platforms for quantum technology. So before we are switching into the technical details, so I would like to thank, this is my group, which we have 4 PhD students, and couple of MSc students and all that. These are the funding agencies which we are getting funding to establish this lab at University of Hyderabad. Okay, so since it's a quantum, so how do we, I mean, what kind of things we are working towards is that we would like to realize a quantum internet. So for that, there are key ingredients which we are fabricating in our lab. Okay, so what are the key ingredients are that we need as an information carriers are the single photon sources. Okay, how to generate a single photon source? And if you have a single photon source, how to make them communicate between these two nodes, which are the sources of the single photon source. Okay, as this is a theoretical proposal, when you trap an atom in the cavity, in a single atom, so it would emit a single photon, then it can be communicated or it can be sent through the quantum channel, and you can connect the another trapped atom in a cavity. So these are called nodes. And if you could connect these nodes in a multiple, then you can make a quantum internet or the network. So this is the original idea. So this is the quantum node, how to make it, and how to incorporate into real existing systems is what the challenge. So what we are planning is that, which means that in order to combine with a fiber existing technology, because nowadays, I mean, from the past years back, that we are getting the internet through the fibers, right? So if you can develop a functionalized fiber, which is a quantum fibers, which is a quantum source incorporated fibers, so it would give us that we can make a quantum network, right? So our proposal is that if you have a nanophotonic based, how to make a quantum node fiber. So that for that we propose that you have a nanophotonic based quantum node, then we can easily incorporate into the existing photonic technology. So this is the original idea. So how to make that? So before that, how to realize a single photon source is which is the heart of the quantum technology. So since I work in a very basic science, so first I will start with a very basic. So if you have, I mean, there is a misconception that if you have a laser light, if you attenuate the laser light, you would get the single photon. Okay. So, but what is a real quantum? I mean, what is a real quantum or real single photon source? How to distinguish? So there is an experiment called an Hambre boundaries experiment. If you send a one photon, if you place a beam splitter, either it will be detected here or here. Both the detectors cannot be clicked simultaneously. That's a quantum nature. Okay. So if you send a laser, which is a weak coherent pulse, sometimes people say that using a single photon, then you would expect that if you measure the photon correlation, it is a flat, which means that it's a classical source. Okay. So when you have this is what is shown in statistics, but if you have a quantum source, as I said, that if you send a single photon, since it cannot be detected either, it can be detected either here or here. So if you take a coincidences, you would expect that at zero delay, you have a zero coincidences. This is how we distinguish whether your source is a quantum source or the classical source. Okay, this is the preliminary experiment. This has to be done first. Then if it is verified, then you will treat that source as a quantum source. Then you would do the quantum experiment. So then also there are a couple of points which has to be, in order to have a good single photon source, it must be on demanding, which means that if you give a one photon to the system, it should give you one photon back, so that you will get on demand single photon. And it should be high single photon count rate. You should have a high count rate so that you can use it for various purposes. And also importantly, you should have a narrow spectral line width. Okay, it's not that if you have a single photon, it should not exhibit each photon have a different wavelength. You should have a very really narrow spectral wavelength. And also the fourth point, which is quite challenging, that it should be fiber coupled, so that, as I mentioned, that all the existing fiber-based technology can be replaced with the all quantum technology-based networks. This is the idea. Okay, so how to generate a single photon, which is not that easy as what people used to think. It's a quite challenging task. It's like you need a two-level system to generate a single photon. So, for example, if you have a two-level, which is a ground state and excited state, you excite the atom, and if it relax, then it will give a photon. So, what are the existing single photon sources in this present era? Is that you have a single atom, and you have a single molecule, and you have a single color centers in nanodiamond, and you have a single semiconductor quantum dots as well. So, if you want to get a single photon from a single atom, trapping of a single atom is a quite challenging task. So, technically it requires a lot of effort. Okay, so in our lab as of now, what we are doing is that the semiconductor based quantum emitters, which are the single color centers in nanodiamonds. These are the samples. Then this is a nitrogen vacancy or the silicon vacancy in nanodiamonds. And this is the colloidal semiconductors which we are using for generating the single photons. This is we are using just for easiness actually. So, but these solid state quantum emitters have some other issues which we will discuss in future and in further. So, then as I said that in solid state quantum emitters, when you have it, you should, you should have a good efficiency. Again, as I'm saying that it's a quantum yield, it should be high. And also it should have a fast decay rate and the narrow spectral line width. And what are the state of art technologies exist to, it's not that you generate a single photon, so you should be able to detect the single photon, you should be able to manipulate efficiently the single photon, so that you will have a more application in a quantum technology, right? So you have, it's a single, an atom is there, on the emitter is there, it is emitting single photon in all the directions. But if you don't collect in a particular mode, then how would you be able to manipulate? So even particular mode, there are already existing technologies, or it's a lenses you can use it, and also you can use a cavities and also metal nanowires and the photonic crystal cavity, and you can use all these kind of a state-of-art platforms, nanophotonic platforms. Okay, but the key issue lies is that as we are, moving to make a quantum internet, which is based on the fiber, when you combine them with their fibers, when you're trying to couple to the fibers, what will happen is that there will be a mode mismatch. So it would not couple very efficiently to the conventional single mode fiber. So therefore it makes the system more complicated. Then what we are doing is that, can we make a very simple system which automatically couples to the existing conventional single mode fiber? So this is a system which we are working, is that simple conventional single mode fiber, you pick it up and you make thin enough that it can collect the single photons very efficiently. Okay, in this part you can functionalize, you can quantum functionalization, you can do it by depositing a single quantum emitter. Then the moment it emits the single photon, it will come to the normal single mode fiber. That single mode fiber you can connect it anywhere so that you can use it for the quantum technology. And also there is an optical nanofiber tip. This is if you place it here, the quantum emitter, this will couple to the efficiently. And the main reason why it will work is that if you see the field confinement at the surface of this fiber is that very high, which means that if you place any medium here, it would efficiently interact and it will automatically couples to the fiber. So for that, these are the technologies which we are using to make a fibers. This is the typical pictures of the fibers, how do you make fiber tips, and this is a chemical method which we use. And this is the method where we have a pulling method. So we heat the fiber, so we can see that 125 micrometer fiber will come down to half micron. So at the center you will have a very thin, then you can use it for the quantum applications. And this is the typical images which we have the fiber diameters of 500 on the order, which is good enough to collect the single photons. So these are, using that, these are the activities which we are doing. Then this is the fabrication of those tips and the fibers. And this one we are able to manipulate the single and few photons. These are the typical simulation results and the corresponding the experimental results. And the left hand side, not only the fibers, we are also working on making capillary fibers so that it can effectively interact with the single photons. So we are making a nanofiber. At the center we are making a hole so that we will be able to reach the field maximum at the center. This is how it looks like. And also this measuring the nano dimension, optical way of measuring, we found a method how to measure it. And importantly that now you would agree with me that so far in this technology, the speed is limited by the now what we have the electronics, which was made by the semiconductors, right? So if you can make the electronics with the optical way, like if you have a optical diode, or if you have a quantum optical diode, okay, so you would enhance the speed of the information much faster, because a photon is much faster than the ultimate speed you can achieve. So we are moving in that direction, that this is a proposal, and this theory was done. This is a quantum optical diode. You can see that as of now there is no experimentally realized quantum optical diode. So we are moving towards that if you can replace your all optical components, transistors and diodes with the optical, so everything you can make it optical without use of the electronics, because we are limited by currently with the electronics currently. That's a key challenge. And also we are working on this, there is something called longitudinal cavity QED, which is a very, very different from conventional cavity QED, which I'm going to discuss in the further slides. And with that funding agency support, we will be able to establish, these are our facilities at our lab we have. So these are the spectrometer where you can measure the with a very high efficiency of the 1 photon spectrum. And this is the facility where pulling facility, and we have the clean booth facility. And this is the Hamre bound setup where you can characterize whether the source is a quantum or the classical. And these are the nano positioning states and the microfluidic technology we use. And as I mentioned in the first slide itself, that you need a cavity QED for the quantum node. So sometime back it was demonstrated that if you place two optical elements, we can realize a good cavity on the fiber, which is a standing wave here. So if you place a quantum emitter, you can see that cavity is being enhanced. So recently we have started working on it, that for future applications, going the photon into the two directions are not much useful for the quantum technology. So we wanted to develop a photons which goes in a one direction. So we are stopping it the other side of the fiber. So for that, what we say, it's a one-sided cavity. So we have simulated first, then we have done the experiments. So and we found that there is a good coincidence between the simulation and the experiment. And there is a key problem that which we have not discussed when we discuss a single photon source. So most of the people in the quantum technology is trying to use the existing entangled photons or weak coherent pulse. The reason is that still the developing of a single photon source itself is emerging. We don't have ideally very, very good single photon source. So for that we have spent a lot of time to develop by ourselves, by collaborating with the company in Japan, that we could state-of-art single photon emitter we could develop, which is a silicon vacancy center in nanodiamonds. This is typically how does the spectrum look like, and this is the polarization of the single photon. And the challenge lies there is that these kind of emitters are synthesized on the substrate, then you have to pick it up and bring to the make a hybrid system. So we use a atomic force microscope system to pick it up and bring to our fiber. And also that when we work at room temperature, because that will be the for application purpose. So when you are working with a dielectric structures, we are limited by the field confinement, and photon can be propagated longer, but we don't get the ultimate field confinement because various limitations. So then we started working with plasmonic nanostructures. Then plasmonic nanostructures will have other limitations. However, if you can combine both of them, we can take an advantage of a field confinement, state of all field confinement, and also we could transport the photon much efficiently. So this is the theoretical work, and it was experimentally verified, and we found that there is a good correspondence between the theory and experiment. These are the research activities which we are doing at the University of Hyderabad. Thank you very much for your attention.
Thank you, Dr. Ramchandra Rao Yelaji. And now, ladies and gentlemen, we have Professor Rajkumar Kittimuthuji. He is a computer scientist at Data Science and Learning Division at Aragon National Laboratory, a senior scientist at the Consortium for Advanced Science and Engineering at the University of Chicago, and a senior fellow at Northwestern Aragon Institute of Science and Engineering at Northwestern University. So we now welcome Professor Rajkumar Kittimuthuji.
Good morning, everyone, and thanks for the nice introduction. Thanks for the opportunity. I'm very glad to be here. Today, I'm going to share with you all about some of the activities that we are doing in the space of quantum networking at Argonne National Lab and also in the broader Chicago region. Can you have the slides? Okay, thank you. Okay, so this was about roughly 6 years ago, 2018. We started our effort in quantum networking. Things were very preliminary at that stage. When there's no quantum memory, I mean, still we don't have a good quantum memory, no quantum repeater. All the devices were in a very preliminary state, right? So we started our effort by developing a simulator called Sequence. This is an open source simulator. I encourage you all to try it out. So we have models. So we worked with physicists at Argonne, University of Chicago, and Northwestern University to develop models for various quantum devices and basically simulated them. This is a discrete event simulator. So we created those models for the hardware, and then we created protocols. So people talked about QKD quite a bit this morning. So we did simulate a QKD experiment and validated our simulator. So we had different layers. So it's pretty modular. So we have modules for entanglement management, modules for network management, resource management, and then we have developed some applications, QKD being one, and we also have quantum teleportation, and right now we are working on a distributed quantum sensing application. And then that's on the simulation part, and as things began progressing, we had, being in the Chicago land, there are two national labs, Argonne National Lab, and there is a Fermi National Accelerator Lab. There, the distance between them is roughly about 50 kilometers, right? So, and then there was a dark fiber between Argonne and Fermi. By dark fiber, what I mean by that is it was not used for any classical communication, right? So we used that dark fiber. The first experiment was, we didn't go all the way to Fermi, but somewhere in a midpoint, we basically had a loop. So had a photon, entangled photon, go to that midpoint and then come back to our lab. So so other speakers also talked about single photon, entangled photon source, and also single photon detectors. So we were using entangled photon source. This is based on a lithium niobate. And the single photon detectors are superconducting nanowire single photon detectors. So we use those detectors to basically distribute entanglement. And then after that, we got another project. I don't know if is it possible to make it like a slideshow, make it a full screen? Because some of the things are not showing up. Anyway, so we had another project called Illinois Express Quantum Network. The goal there was to basically develop a metropolitan scale quantum network. So we have several institutions in the Chicago land, Argonne National Lab, Fermi National Lab, and the starlight in there is basically an internet exchange point that was in downtown Chicago, and then Northwestern University. So the dotted fiber, the dotted line, the dotted red line shows that that fiber is being built now. The other ones are there already. So I talked about the 50-kilometer link between Argonne and Fermi Lab. And there is also 83-kilometer fiber between Argonne and downtown Chicago, and another 20-kilometer fiber between Northwestern and Starlight. So we've actually demonstrated entanglement distribution between Argonne and Fermi Lab, and then Northwestern and the Chicago downtown. We are currently working on doing some experiments between Argonne and Starlight, the 83-kilometer link. Can you move to the next slide, please? Okay, thanks. So I think Dr. Nadarajan talked about some coexistence. So coexistence is a key challenge, right? So we have a lot of fiber that's been installed, right, for classical communication for the current internet. So can we really make use of those existing fibers for quantum communication? So that's a question that we still don't have a good answer for, right? People have demonstrated some coexistence experiment by sending both classical and quantum channel on the same fiber at different wavelengths, right? I mean, so the telecom, so we have multiple bands, right? I mean, C band, O band. So can we actually send quantum on the C band and classical on the O band, or vice versa? So there's been some experiments. In all those experiments, what people do is they reduce the power of the classical signals so that it doesn't really interfere with the quantum signals. So essentially you have Raman scattering and you need to reduce that, right? But when you reduce the power of the classical signals, so we need to be cognizant of the fact that that can actually be detrimental to the classical signals, right? I mean, so what is the impact of that on the classical signals? So we are actually doing some extensive study on that. So we have a network within Argonne where we are doing some practical experiments and also simulating that, so we can actually do a large-scale study on classical quantum coexistence. But what we did in this case is between Argonne and Fermi, I mentioned about this 50-kilometer link. On that link, we were able to do both quantum signals and the clock signals on the same fiber. So the clock signals were going on the C band, and the qubits, or the entangled photons, were going on the O band. And this picture actually shows the test bed that we are building within Argonne. This is a campus scale network. So basically we have photon detectors and the entangled photon source in 5 different buildings. So this network essentially connects those 5 different buildings, creating a campus scale quantum network within Argonne. And we have connections to other institutions, as I mentioned in the previous slide. And when you have a network, you need a control plane. And I think Dr. Nadarajan already talked about the control plane. And I mean, the control plane, a lot of people are jumping on using the stack. I mean, we have the classical internet, which is good. I mean, we have a reference, but the quantum is very different, right? But people start to map the classical stack into quantum, right? I mean, we argue that may not work, right? But anyway, so you need a control plane, especially when you have more number of nodes. You need a control plane. We are also building a control plane using software-defined networking as part of another project. This QNext is one of the national quantum information science centers. So US funded 5 national centers probably roughly about 4 years ago. And QNext is a center that's situated at Argonne. Part of that, so as part of that, we are building a classical control plane. Classical control plane meaning the control plane, the control signals are going on a classical network. And there are efforts on, can we basically have the control signals go on the quantum channel as well? And that's an area of study, and people are doing work on that. So we are interested in studying the trade-off on using a classical channel to do the controls versus quantum channel to do the controls. That's going to be part of a large-scale simulation study. And this is one of the new projects. We call it InterQNet. The idea here is to connect, to create a heterogeneous quantum network, right? I mean, at Argonne, we have physicists working on different types of platforms. I think people talked about a few different platforms, ion traps, neutral atom based one, and superconducting microwave qubits. So we are working with three different physicists, one working on a superconducting qubit, another one on a neutral atom, ytterbium based atom, and another one on an erbium ion based platform. And we are planning to connect these three different platforms using a network. For that, we need, somebody mentioned transduction this morning, so we need to transduce, because the photons that these platforms will excite will be in a different wavelength. So in order for that photon to travel over the fiber, so we need to do frequency conversion. So that's something that we are working on. And the idea is, again, to use that neutral atom platform, the ytterbium atom, as a repeater. And there was a mention about the repeater. We don't have a functional repeater yet, so the quantum signals cannot be amplified using the regular classical amplifier, so you need a quantum repeater. For that, you need a quantum memory. But we're trying to build a preliminary quantum repeater using the ytterbium platform. So the idea is to create an entanglement, between the erbium ion and the superconducting microwave using ytterbium as the repeater node. So that's one of the goals for this project. Then the second goal, that we call it as interqnet achieve. So which is basically realizing a practical heterogeneous quantum network, because heterogeneity is a key thing. One of the reasons why classical internet is so successful is because of the heterogeneity. It allows you to connect heterogeneous devices, diverse devices, and you can have diverse applications on top of it, and IP is the layer that sort of glues them, right? And we don't know what that layer is for the quantum. Is it entanglement? Could be, but it's something that needs to be researched further. Okay, so the second aspect here is the scalability study, so which we are going to use the sequence simulator to do scalability study. So we'll create a heterogeneous network. We will also simulate the heterogeneous network, do some validations, make sure that the simulations are close to reality, and then we would like to do some scalable studies, because there is no scalable quantum network now, so we have to simulate. But we need to have some confidence in the simulations. Once we know the simulations are valid, we want to connect many different nodes at longer distances, many different users, connecting heterogeneous devices. So that's the second part of this project. I won't go into too much details of it, but this project has three key thrusts. One is the devices thrust. I mentioned about three different platforms. So we need work on those platforms. We need to build transducers. And error correction was also mentioned before. So we need to have error correction mechanisms. So we are planning to do entanglement distillation, create new entanglement distillation techniques, error mitigation approaches. And then I already mentioned about it, that waste thing is what? So we don't want to map the classical internet stack to the quantum network, but we rather want to learn from the classical internet what worked, right? So this hourglass-like structure where you have different heterogeneous devices at the bottom, and the narrow waist there, that provides the abstraction. That provides a common abstraction for many different applications, right? Likewise, we need to build a similar thing for that. But what are the layers? Like Dr. Natarajan said, so we don't know that, right? So that we need to do a lot of research to come up with the right stack. But that's one of the goals for our architecture thrust. And we need to develop many different protocols. So there are protocols evolving, but still there are a lot of protocols that still need to be developed. So I mentioned this already. So this is this diagram that depicting the heterogeneous quantum network, a campus scale heterogeneous quantum network. And this shows the scalable study, like I mentioned. So you have this infrastructure at the bottom level that connects a lot of different nodes. And then you have a logical plane in the middle, and then you have applications at the top. Could be many different applications. I've just mentioned a few things. So entanglement generation, which is a basic thing, and you need to do quantum teleportation and entanglement swapping. And then you can build on that distributed quantum sensing, distributed quantum computing, and all those things. These are some preliminary results. I mean, the left one shows fast, high fidelity Rabi oscillations. So this is very important for the transduction, I said, for the ytterbium atom case. And on the right, it shows the entanglement distribution on the campus scale network between two different buildings. With that, I close my talk. I'm happy to take a question or two if there is time. Thanks a lot, everyone. Appreciate it. Appreciate the opportunity.
Yeah.
Sounds good. Thank you.
Thank you, Professor Rajkumar Ketamuthuchi, for speaking on quantum network and post-quantum cryptography. And finally, ladies and gentlemen, in this session we have our speaker, Srinivas Hegdeji. Srinivas Hegdeji is an experienced professional in information security industry. He's a co-founder and chief technology officer at Secure Machines Private Limited, a startup based out of Bangalore, working primarily on data security products. Srinivas Hegdeji.
Good morning to everyone, and thanks for this invite and opportunity to talk here. First of all, I think from yesterday, a lot of speakers and experts have already shared a little bit part of what I want to explain, the post-quantum cryptography. So by the time now, I think most of us understand quantum computing and its power of computation powers, and also the cryptography parts. A few of them have touched the cryptography parts of it. So what I want to share is, and also considering the 15 minutes restriction, so what I want to do is, I want to share an experience of our implementation of PQC secure hardware in the field of network security. So it will be an overview, and I will try to make it as simple as possible. Yeah, so let's go to detail of it now. Not working. Okay, so just to set the context, where and why we come to PQC domain and who we are. So we are a startup founded in 2019. We are focused on building post-quantum crypto and in the embedded products. And we are building one of the first certified PQC device for network security, and I'll come to that, why we say one of the first certified PQC device. We have a young talented team, and we work on topics like hardware crypto acceleration and security engineering of the embedded products and post-quantum cryptography in specific, and a lot of certification. So just to two words for about the founders, me and our founder Satya. We spent almost 15 plus years in industry of security in semiconductor and security implementation of various products. So we are part of some major products like US e-passport products and German EID products. So we have spent good amount of time in exploring the whole life cycle of development of products from development to the deployment and post deployment. So these things, and we are part of certifying the product for common criteria and FIPS, which are most widely accepted certification for the security in around the world. And yeah, next slide, please. So, and we work mainly in three domains, area of work. Quantum safe cryptography, that is where we have one product called Pingala, which is a endpoint encryption device, and it has a PQC inside. And we also have quantum safe crypto cores, that is hardware IP cores which are implementing the quantum safe cryptography. So the right side what you see is the patents that we have filed in these areas and domains. Most of them have been granted and some of them in process. Second category or area of work what we do is a secure voting system. It's basically end-to-end verifiable a crypto solution which we have a patent also on for, which we call as trust vote product, and it's a different crypto concept to verify from end-to-end verifiability of any vote that has been casted and counted. So third area where we work is integrity devices, which involves secure data carrier or a full data validator. So these are all some just to set the context that we work in the area of security devices in specific. Next slide, please. So I'll spend few minutes because we understand quantum and cryptography. So we also have to understand how network layer is there and what is the security involved. Just to cover some basics, why PQC in IPsec. So what is IPsec? So network follows a OSI model, and it have 7 layers, and there is a network layer, layer 3, that's called layer 3 network layer, and there is a security protocol which is used in this layer called IPsec, which is a very crucial and critical part of any network which has VPN or security end to end. So there are also other application level layer protocols like TLS and all this thing, but they are a little more upper in the layer of the network, so it does not involve or contain all the crucial part encrypted from the source to the destination. So IPsec work on the layer 3, so that means it is more creating a secure channel at the basic level. And security context of IPsec, why it is secure? So it involves classical crypto algorithms currently as it exists now, like ECC and RSA, which are used for generating keys in both the ends. And there is a protocol called IKEA v2, which used for exchanging the keys from both parties. And they use a DH key agreement. So I just explained this because these are classically now existing mechanism whole around the world, and that is where our whole system of digital world relies on. So either ECC or RSA, and then generate a key pair using IKEA v2 protocol, and then exchange the keys, and then start the encrypted session both sides. So there is a tunnel, if you see the picture in between, so there is a tunnel created from network 1 to network 2 when there is IPsec session is created. So every data which is started from physical and data layer are immediately encrypted and passed in this tunnel. So that is where this whole protocol starts the session. So what is the threat of quantum computing? So yeah, most of us have already now understood that ECC and RSA stands vulnerable to quantum computing due to Shor's algorithm. So it is just a matter of now realizing qubits and logical bits. So that is where these things which currently existing can be broken potentially, and there is also this harvest now, or rather store now or decrypt later kind of a threat where the internet traffic can be snipped now and stored, and then once the quantum computing and breaking of this classical algorithms becomes reality, then they can just decrypt it, and the secret part of the message can be revealed. So by this we also understand there must be a recommended action for this kind of threat. So that is where the PQC comes into picture now. So the asymmetric algorithm used in IKEA v2, that is the RSA and ECC, will be replaced with quantum safe KEM. KEM is key encapsulation method, and then most organization worldwide, like NIST from USA recommends hybrid approach as of now for the cyber security area, and then later completely move to PQC. Hybrid in the sense that we use ECC, and then on top of that we still use PQC safe quantum safe algorithms, and then have both of them, and then slowly move to the PQC completely when it is evolved completely. So I think this one point, no action required for symmetric key based thing. So potentially as of now there is no threat for AES 256 keys that is considered non-vulnerable in the quantum era as of now. And this is where I think the symmetric encryption method can remain same on the both side, but the tunnel creation with the ECC and RSA must be replaced by quantum safe algorithms. Next slide please. So these are the two products which we built. It's called Pingala Kyber crystals and Pingala classic Mechales. The name Pingala comes from an Indian ancient scientist, mathematician, who derived a concept something similar to the binary methods. And also it contains the ping as a indication of the network ping. So these two algorithms are suggested basically by NIST. One is Kyber crystal is already a standardized algorithms. The draft is available public. And other one is the classic Mechales, which is fourth round selected candidate for standardization by NIST. And both of them we have tested with PQC session like IPsec or VPN creation with both the public network and also the within the network end-to-end, endpoint to endpoint tunnel creation. The speciality of this one, which is our core strength, is it uses something called certified secure element. I will come to that. What is certified secure element? And it uses a hardware crypto acceleration to generate and give a high throughput performance. So as you see, the application of this Pingala which is endpoint encryption device, can be in many areas, including IoT, smart cities, and industrial automation and enterprise security. For example, in smart cities, there are cameras which are endpoint, and then they are vulnerable to the attacks in the physical traffic that can be sniffed. So that is the part where this product can be plugged in, and then no alteration is required, and then it works as an inline encryptor. So it uses CC certified hardware platform. That's what I mentioned, and I will explain why it is crucial. Next slide, please. So this is our journey of our experience of building this. I'll quickly explain that. So OpenWRT is the Linux kernel which is used mostly in all the routers today, and we took the open source Linux kernel, and then there is also challenge of choosing appropriate platform which is suitable for doing this kind of crypto implementation. And then there is a part where we have to replace the existing IPsec protocols like ECC and RSA based thing by replacing the KEMs with PQC, that is Kyber and Mechales. We also did this implementation on both hardware and software side. So the next step is to set up use case testing using VPNs. VPN tunnel creation, so that we successfully demonstrated and set up a channel, VPN channel. And the other part, where it's an important part, is there is something called implementation security. Any cryptography have two parts. So mathematical strength of the cryptography, which is derived from a problem which cannot be solved by a classic computer or existing computation system. And there is also a part where it comes as an implementation security. So you can have a most complex mathematical problem, but when you implemented it on a software or a device, it also needs some kind of a security, which Dr. Anupam ji also mentioned, that there is a side channel attack, and if you store your keys and whatever, how strong your cryptography is, but if you get access to that key somehow using some tampering methods, then there is no use. So that is where our strength comes in. So we implemented also something called common criteria certified secure element, which manages, stores and generates keys for the PQC session. Next slide, please. I'll finish it. So certified security, hardware security is just now as I explained, it's a computational system which has undergone rigorous testing and evaluation process by adhering to some specific standards and requirements set forth by a regulatory body or an industry organization. In this case, maybe example the FIPS, common criteria, and SAG in India. So this kind of it undergoes a vigorous testing and in a third-party laboratory to test and against all the existing state-of-the-art attacks. So there are comparison. I will not go into the detail of it, but there is a comparison if you develop and implement a PQC in various platforms. What is the security level and implementation complexity of them each, and performance and cost. So we have chosen secure element because of the security, high security level. It is assured by the security assurance which is given by common criteria of FIPS or this kind of certifying bodies, and there is basically other platforms where you can get a best performance, but it may not be secure enough to have this kind of product in the field where anybody can do anything on this. So next slide, the last one, please. So from our experience of this enabling this PQC in network security and building that product, so we think there is currently existing a few points which are challenges. So there is a lack of standardization for the security goals. So any standard cryptography like RSA, ECC, which are there from the last 20 years, which have well-defined security goals and other things by the standards, and that is something now we are in the middle of era where it is just evolving. And then evaluation criteria and defining scope for the implementation security, which is what I pressed, that there is a critical part of implementation security which has to be evolved for the PQC algorithms worldwide, and that is what most of the agencies are trying to do now, like what Dr. Anupam has mentioned, and that is something we are also looking forward for this kind of standards. And one thing that is also for an Indian context, I think, where there must be a kind of a SAG framework or a similar kind of framework for PQC evaluation in India in context of security evaluation, like the hardware security and implementation security point of view. Yeah, with this, I think I would like to thank everyone. Yeah. Thank you.
Thank you, Srinivas Hegdeji. And with this, we sum up our first session. If you have any questions.
I have one question, madam. Hello. Good morning. I have a question for Dr. Ramchandra Rao. It is a very basic question, sir, since I am still struggling to grasp the ABC of quantum technology. What we have studied in the classical optical fiber communication, a wave, I think the light wave which enters the fiber, it reaches from the source to the destination by something called total internal reflection. Right. And here, in a nanofiber or quantum category OFC, you are introducing a single photon into the waveguide. Right. So what is the property or what is the phenomenon? It uses the single photon to reach from the source to destination, which may be lying maybe 50 kilometers or 100 kilometers, number one. Second question, how do we prevent that single photon, after it collides the waveguide wall, it should not tunnel out of the waveguide itself, right, by something called the tunneling effect. Right. So these are the two questions. Thank you.
Actually, the first answer is that, can you hear me? Yeah. For the first question answer is that still it follows the same total internal reflection. So that will prevent you not to lose the photon out of the waveguide. when it is coupling back to the original fiber, is that it is the tapering, the way it was done, it like efficiently you can transfer the energy from the nano fiber to the conventional single mode fiber without loss. I mean, without loss, ideally speaking, you have a probably less than 0.1% loss.
But sir, in total internal reflection utilizes the wave nature of light.
Correct.
Here, how something which is a property of the wave nature of light, and here you are using the particle nature of light, that is photon. How photon will have that privilege of total internal reflection? That is something, that privilege is available only to the wave nature of light. Here it is a photon, it is a particle.
Yes.
It cannot have that privilege to enjoy that
No.
wave nature of
No,
light.
still it is a, still it will travel in the same way of, I mean, probably you may be thinking that a localized way, actually. It's a wave packet, right? When you talk about a single photon, it's a wave
You are
packet.
introducing a single photon, that means a single dot of light is traveling, isn't it? Is it like?
Yes.
So by virtue of successive collision it is traveling, then there is definitely a non-zero probability that at some collision it tunnels out of the waveguide itself.
That's how. That's how the waveguide is designed, such a way that it won't escape from the waveguide.
No, but probability will always be there. So
That's what I'm saying. That probability is very minute. Most of the time, it lies within the waveguide. That's how it is designed.
Can we have next question, please?
Yeah, I am Arun Agrawal, the DDG in Department of Telecom. Throughout the session so far, we have discussed about quantum communication in terms of photons. But Colonel Sai mentioned about radar also, which can use quantum communication. Whether they will use the same type of radio waves even at terahertz, or whether these radars will be utilizing, or satellites will be utilizing some other frequency band for quantum communication. And secondly, it appears that this field of science and engineering is still under evolution. So when I was in college in 80s, digital communication was also evolving. It was all analog. So when do you feel it will be mainstream? It will be in next 10 years or 20 years or 5 years, when it will be mainstream? Thank you.
Sir, when it will be, I will try to answer the second question. When it will be the mainstream, that I cannot answer. That is depend on all the scientists and academicians who are sitting, sir. How they hard work and how they contribute. That we can also, yes, you bring army officers on top of it, we will definitely. So if you see most of the departments in US, all the R&Ds are headed by defense officers. So we are not intelligents, but we know how the work to get it done. That is. Yes, sir.
I mean, that's such a huge issue that we need to address, in fact.
Exactly.
How we are going to take this big task, I don't know, sir. I mean, we've been waiting over here for the past couple of months to
I totally agree with you, sir. As I mentioned, when all the elements come together under a single umbrella, then only it will happen. It cannot work in silos. Output will not come into it, especially in the quantum domain. As I mentioned, it is a separate vertical for them. Now coming to the quantum radar, it has nothing to do with quantum communication, sir. One of the quantum properties used, sir, that is quantum entanglement. So it is not that I will be straight away firing an entangled photon. It will be a combination of a microwave and entanglement photon, sir. Exact details we can discuss further. Thank you.
And I have one question from the perspective of national security. If from yesterday I have been telling that it is a totally secure communication, conditionally secure, unconditionally secure, so many number of conditions. If that means theoretically we are not able to break into a quantum key, then how lawful interception and monitoring will take place?
Sir, that is a separate question. How lawful interception? Lawful interception can always will take place, sir. There are ways and means of implementation. As Dr. Natarajan also brought out, quantum communication is a combination of quantum So there is a ways and means can be implemented.
You said about the integral photon pair generator. You have some lab, probably Argon or somewhere. So I just, mine is a very basic question. If you can explain in a language that a layperson like me can understand, that how do you create that entangled photon pair right at the first place?
Yeah, I think the other speakers talked about that. I mean, there are multiple ways to do that. It's essentially, I mean, I don't know all the details of it. I mean, it's basically physicists do it, but all I can say now is.
And anybody else in the panel can do it.
Well, yeah, I'll pass it on, but I'll just say this comment, right? I mean, so right now, you have like commercially available devices that can create entangled photons, right? So that we can, I mean, although like it's not like there's possibility to improve that, right? So it's a, I mean, the whole quantum thing is a probabilistic process, right? So there is always scope for improvement, and people are working on that. But at least the commercial devices are available, and people are also doing research on doing like creating that entangled photons in an improved way.
I was just wondering how to do it.
Okay. So,
Sir, I would like to talk to Colonel Sankar. He talked about this quantum tunneling and all that. I want to know that even we get energy from the sun using nuclear fusion reaction. Some of the subatomic particles don't have energy, classical energy to overcome the potential gradient. Through the quantum tunneling, they come and we get the nuclear fusion. That's why we get energy from the sun.
okay.
That's what I wanted to comment.
Yes.
So thank you. Thanks everybody. For now.
Just give me 1 minute time because I was the first to raise my hand. But then
No issues, sir, please.
to be brief, I will just like to thank all the panelists. Wonderful discussion today, but especially the questions from Dr. Yalla and Dr. Katie Motu. In fact, Mr. Katie Motu saved time to ask questions, but there was no questions for him. So, just what I say that if as we go to develop the optical fibers,
Correct.
as we are doing now,
Correct.
already lot of things like hollow core fiber we are doing, and multiple fibers we are all like we are doing. What you both of you perceive that what changes should be made in the optical fiber technology itself to accommodate the new quantum like traveling of photons to be precise.
Okay, thanks for nice question. That my simple answer to is that you don't have to change anything. Keep as it is whatever the fiber you have. Where you functionalize the fiber, locally you can change, and rest remains the same.
So I can.
So that I mean it forms. That is the what our approach we are following. So keep all the fibers remains the same, but at locally you quantum make it. I mean quantum functionalized, so that rest everything can be used for the existing fiber technology in every way aspect. This is what my answer is.
So maybe I can give a different answer. So there are ultra low loss fibers that people are developing, right? So if you take a normal fiber now, there is a loss per kilometer, right? So every kilometer photon travels, so you have noise in the channel, right? So there is a loss of 0.2 dB per kilometer, right? But there are fibers that can actually reduce that loss to 0.14 or 0.12, and that can make a huge difference, but probably not right now. When other devices also improve, right now, the fiber itself is not the problem. So in that
Exactly.
sense, what Ramchandra said, I agree with him. I mean, but as the end devices improve, then we will get to a point where the noise on the fiber is a problem, right? So that's one of the reasons why we are paying a lot of attention to this coexistence, right? Like, do we really, I mean, this is a big question for funding agencies, right? I mean, so do they really need to pay for new infrastructure, right? Do we really need to lay new fibers to support quantum communication? That's something that we still need to do some research to get answer. But right now, we need to do this coexistence and see, like, try to use the existing infrastructure, because it's a huge undertaking to lay new fibers and build this infrastructure. But the answer may be that we need to build the new infrastructure.
Thank
Thank you. So with this, we wrap up our first session of the day, and we would like to thank all our speakers. May I now request Shri Sudhir Kumar Raiji, DDG Northern Region, TEC, to kindly felicitate our speakers. Shri Sudhir Kumar Raiji will now present a memento as a token of thanks to our speakers. Dr. Natarajan Venkatachalamji. Now Shri Sudhir will present a memento to Colonel Sai Shankarji. May I now request Shri Sudhirji to kindly present a memento to Dr. Ramchandra Rao Yalarji. Now to Dr. Rajkumar Ketimuthuji. And of course, Srinivas Hegdeji. Thank you, Shri Sudhirji, and thanks to all our speakers. Thank you so much. So, ladies and gentlemen, as you know, we have 2 more sessions lined up, followed by a panel discussion. So, for now, it's a tea break. Please do join us for high tea and come back within 15 minutes because we have so much more to cover. Thank you for now. After the high tea in the second International Quantum Communication Conclave. So on the second day we had our first session before this tea break, and now we'll have our next session that is on standardization efforts towards quantum technologies. And first we are going to connect to Dr. Dustin Moody. He is joining from United States. And to tell you about Dr. Dustin Moody, he is a mathematician at the Computer Security Division, National Institute of Standards and Technology, that is NIST. He leads the post-quantum cryptography project at NIST, Gettysburg. His research interests include elliptic curves and their applications in cryptography. Dr. Moody received a PhD from the University of Washington. So, Dr. Dustin Moody, welcome you in this session.
Thank you very much.
Pleasure, thank you.
I appreciate the opportunity to speak. I hope you can hear me and see the slides. And I'm going to talk about the standardization that we are doing at NIST, the National Institute of Standards and Technology, here in the United States. So at NIST, we have been developing cryptographic standards for over 40 years. The very first cryptographic algorithm we standardized was the data encryption standard known as DES. Since then, cryptography has advanced a lot, and there have been a lot of breakthroughs and innovations, so we've continued to adapt and come up with new standards. Nearly all devices, all laptops, phones, routers, pretty much all use cryptography that has been standardized by NIST. The threat of post-quantum cryptography is probably well known, or the threat of quantum computers. So at NIST, we have a variety of different cryptographic algorithms that we have standardized. There's a chart here that shows a diagram of some of the different documents that we have. We have standards for public key crypto systems. We have standards for symmetric key algorithms like AES or SHA-2 and SHA-3. We have other documents that have guidance for random number generation or key management. But of course, the threat of post-quantum, or the threat of quantum, means that all of the algorithms that are currently standardized in our public key cryptography standards would be vulnerable to an attack from a large-scale quantum computer due to Shor's algorithm. This includes algorithms like the Diffie-Hellman, the elliptic curve version of the Diffie-Hellman, RSA encryption and signatures, and the elliptic curve digital signature algorithm. All of these algorithms need to be replaced. We cannot simply use larger parameters because a quantum computer that is big enough will be able to attack those very soon after as well. Now, there will also be an impact to symmetric key cryptographic algorithms like AES or SHA-2 and SHA-3. But the impact is not as dramatic, it's not as drastic. So we can protect against that by using longer keys or using longer output for our hash functions. So perhaps instead of using a key that is 128 bits for AES, we would use a key that's 192 bits or 256 bits. So that is easier to manage because we don't have to change algorithms, we just need to use a longer key. It is really the public key cryptography where the focus has been for researchers because we need to come up with new algorithms. So the name of this field, as you're probably aware, is known as post-quantum cryptography, or sometimes quantum-resistant cryptography, or quantum-safe cryptography. It's the need to find cryptographic algorithms which are secure against both quantum computers as well as against classical computers. Classical computers will still be here even after quantum computers arrive, and attacks from either one would be possible to break crypto systems. Now, just to clarify, these post-quantum cryptographic algorithms will need to be implemented in classical computers, the the same way that RSA or Diffie-Hellman are today. And that's because the majority of uses around the world, the majority of applications, will still continue to use classical computing technology. Quantum computers will be very specialized, very expensive, with special needs hardware. So we want the cryptographic algorithms to protect our data to run on classical computers. Now, I've used the word quantum and I've used the word cryptography. There's a field known as quantum cryptography, which is different than post-quantum cryptography. The focus of what NIST has been focusing on is post-quantum cryptography and not quantum cryptography, which is also known as quantum key distribution. Quantum cryptography or quantum key distribution is the notion of where you are using quantum technologies to build or enable cryptographic applications. And that is something that is different. Now, how soon should we worry? Nobody knows for certain when we will have a quantum computer that is large enough to attack public key crypto systems, but because of the harvest now decrypt later threat and the need to have standardization done well before a quantum computer is available, the United States government has been taking action to make sure that we are prepared well in advance. So on this slide, I have some pictures to show some examples of this. The White House has issued some national security memorandum. The National Security Agency has issued the Commercial National Security Algorithm Suite 2.0 that updates its cryptographic algorithms to protect against the quantum threat. The United States Congress has passed a Quantum Cybersecurity Preparedness Act, making sure that federal agencies will transition to algorithms that will protect against the quantum threat. Overall, the goal of the United States is to make sure that our agencies transition to quantum-resistant cryptography as much as possible by the year 2035. At NIST, as our role is to standardize the cryptographic algorithms, we have been preparing for this for a number of years. Back in 2016, we launched basically a large-scale international competition to find and select new algorithms for standardization. Specifically, we were looking to standardize the algorithms to replace the ones in our standards which were vulnerable, the public key crypto algorithms that have the functionalities of digital signatures, as well as public key encryption or key establishment. NIST has done this sort of thing in the past. We did this to select the algorithm AES. More recently, we had the SHA-3 competition to select a new hash function. And we have found that these competitions are very well received by the cryptographic community and have great outcomes. Our role is to manage the process in an open and a transparent way to achieve community consensus in a timely fashion. We said from the beginning there would not be a single winner, that there would be a few algorithms that would be selected because we're looking for signatures and encryption, and also because we want to have different types of crypto systems, so we don't just have one algorithm. We said that there would be a small number of algorithms that we would select for standardization. So over the past 7 or 8 years, the algorithms that were involved in this competition have been analyzed internally by us at NIST, as well as by cryptographers around the world. So we organized the evaluation process in a series of rounds. The first round consisted of 69 different algorithms that were sent in to us. We held a workshop. There was research done. Some of these algorithms were broken. And after about a year, we advanced 26 algorithms into a second round of evaluation. The second round was similar to the first round, where there was, again, more research done, more performance benchmarking, another workshop. Some of the schemes were attacked. And finally, 7 finalists and 8 alternate algorithms were advanced into the third round. The third round lasted for 2 years of very focused and intense evaluation, at the end of which we selected some algorithms for standardization. These tables here show the different types of crypto system, or the mathematical foundation upon which the candidates were selected. Many of them were based on lattices or codes, but there were other ideas considered as well. So after 3 rounds, NIST selected 4 algorithms for standardization. We selected Crystal's Kyber as a public key encryption or a key encapsulation mechanism. And for the digital signature category, we selected Crystal's Dilithium, Falcon, and Sphinx Plus. If you want more information as to why these algorithms were selected, there is a report called NIST 8413 that you can read to get more information on that process. We also still have a few algorithms that we are evaluating in a 4th round. All of these are chems that will complement our selection of Crystal's Kyber. I'll talk about them on another slide, as well as what we call the on-ramp signature process. So just to recap the 4 algorithms and provide a little bit more information about them, 3 of these algorithms are based on what are called structured lattices. This includes Crystal's Kyber, Crystal's Dilithium, and Falcon. We expect Crystal's Kyber and Crystal's Dilithium to be the main 2 algorithms that people will use for most of their applications. They both have very good all-around performance and security. We selected Falcon also as an alternative to Dilithium because it has smaller signature size and smaller public keys. However, it has a much more complicated implementation. So some applications may need that smaller bandwidth and can handle the complicated implementation, but most applications will be just fine with Dilithium, which is easier to implement. As a backup, we selected Sphinx Plus as well as a digital signature algorithm that is not based on lattices. It's very conservative with regard to its security. However, its performance is not as good as the lattice-based algorithms. It has a lot bigger keys and signatures and is slower to evaluate. Here's a timeline looking back at where we've been and where we are going in the future. I will note that in 2 months we will be holding a workshop. It will be held in person in Rockville, Maryland, April 10th to 12th, where we will talk about many of these topics that I'm talking about right now. The standardization of the algorithms, the candidates still being evaluated in the 4th round, and some digital signatures that are work for future standardization. Now, after selecting the algorithms that I mentioned before, we wrote up draft standards and we released those for public comments in August of 2023. They were available for 90 days of public comment. That comment period has ended. Right now we are reviewing the comments and we are revising the draft standards. We're making any changes that we feel are necessary in response to the comments, and we expect the first PQC standards to be published this summer in probably around June or July 2024. There are still a few algorithms, as I mentioned, in the 4th round being evaluated. 3 of these are based on codes. It is likely we will select 1 or 2 of these algorithms to standardize in addition to Crystal's Kyber for the chem category. The 4th algorithm, Psych, is based on isogenies. It has been broken, it is insecure, and should not be used. As future work, we are also looking at standardizing potentially more signature schemes. I mentioned that Sphinx Plus was a backup algorithm that was not based on lattices, but because its performance is not as good, we are hoping to find other digital signature algorithms not based on lattices, which have better performance than Sphinx Plus, that are more general purpose. So we announced a new call, and in response, we received 40 submissions that we will be evaluating in the 1st round. After a number of years, after a few rounds, we may potentially select 1 or 2 digital signatures to add to our signature portfolio. It is not expected that these will replace Dilithium or Falcon. These are intended more as backup algorithms in case there were ever to be some attack discovered on lattices. So this on-ramp, as we call it, is mostly future work for standardization of digital signatures. There are many other standards organizations and groups that are working on post-quantum cryptography. I've listed many of them here. There are other countries working on standardization. NIST is in communication with pretty much all of these, and these groups were all very much involved with our process and are using the algorithms that were evaluated in our process. So that's very good for adoption worldwide, that besides NIST standardizing these algorithms, it will also be standardized in many other bodies around the world. There's a lot of focus on the migration aspect to this, now that we know the algorithms and that the standards are almost here. NIST has what's called the National Cybersecurity of Excellence that is running a migration to PQC project to help with the transition. The project has partnered with many industry partners. On the left, that's actually only about half the industry partners that we're working with to work on tools and advice and guidance for things like discovery, tools to discover which cryptography your systems are using, as well as topics like interoperability and performance. So if you're interested in that project, I'd invite you to learn more about it and potentially join that project as well. So in conclusion, it's very nice that we are seeing some of the light at the end of the tunnel, and that the first standards for post-quantum cryptography will be available in just a few more months. There is a lot of future work that we still have going on. All cryptographic algorithms in the future will need to be post-quantum, so this isn't going away. NIST is grateful for everybody's efforts. This is a very large task that the whole world needs, and we are grateful for everyone working together. For more information, you can check out our webpage. You can also sign up for an online mailing list called the PQC Forum for announcements and discussion. And as always, you can always contact us directly at NIST. And with that, I'd like to say thank you very much for the opportunity to talk about NIST and the standardization of post-quantum algorithms.
Thank you so much, Dr. Dustin Moody, for joining in and highlighting on various aspects of standardization efforts towards quantum technologies. Thank you so much.
Yes.
And now, ladies and gentlemen, may I invite our speakers of this session, Shri R.R. Mukherjee, Advisor, Department of Telecommunications. Please, sir. Shri Vinod Kumarji, DDG Quantum Technology, Telecommunication Engineering Center. Dr. Anandita Banerjee, CDEC Pune. And we have Shri A.K. Mittalji, Advisor from TSDSI. Please, sir. And now I'll invite Shri Ritu Ranjan Mukherjee. A brief profile about sir. He is an Indian Telecommunications Service Officer of 1985 batch, having experience of more than 30 years in various capacities in Department of Telecommunications, Government of India. He has very vast experience in the area of standardization of telecom equipments and networks, including next generation networks, spectrum management and radio regulations, planning and execution of telecom ICT project, telecom and cyber security, IP56 ready logo, and telecom regulations. So now we have Shri R.R. Mukherjee. Sir, please.
So, thank you. So the topic for the next 10 minutes is WTSA 24. I don't have any presentation. I'll just introduce you to what is World Telecommunications Standardization Assembly 24. So this event is scheduled in India for the first time from 15th October 24 to 24th October 24. Before we go into what is WTSA, I would like to introduce you to an organization called ITU, International Telecommunication Union, which is a UN body which deals with the standardization activities of communication and, or to put it, ICT. Yesterday, we had a very enlightened opening session, wherein many speakers emphasized upon the importance of standardization. So ITU has 193 members, about 900 sector members, academia. So it's a fairly widespread in its reach. Many R&D organizations are there as associate member. Many standardization agencies themselves are there as sector members. And it enjoys a reputation in terms of its reach, because the governments, all governments are member states, are there as members. So it is a very vital organ for the standardization activities. It is important to know that while ITU spearheads its efforts, there are many parallel standardization bodies. Dr. Dustin's talk mentioned a few while he was telling about the efforts in the PQC. Those are IEEE, HC, 3GPP, and we in India we have TSGSI, and we have Mr. Mittal. He will elaborate on the efforts of TSGSI. Coming to ITU, so ITU has three sectors: ITU-T, that is the standardization sector; ITU-R, the radio sector; and the ITU-D, development sector. So T is standardization of equipment. R is partly standardization, partly regulation, radio regulations. Which spectrum is to be used where, so that the minimum, there is minimum interference. What should be the orbits of the satellites, what frequencies they should use, that is taken care by R sector. And D sector is promotion of ICT activities, so that all countries, based on the experiences other countries or good projects that other countries have undertaken, they can also replicate. So development, as the name indicates, they deal with development. Now coming to WTSA. Okay, before that, the whole T sector work is divided into a specialized group which are called study groups. Study group, there are around 11 study groups. Study group 2 deals with naming and numbering. Study group 3 deals with financial and tariff policies. Then study group 5 deals with EMF and circular economy. Study group 9 deals with convergence aspects, including broadcasting. Then 11 deals with the protocols and testing, certification, and finding out how, specifications related to counterfeit devices, how to handle or how to kind of catch them. Then study group 13 on the architectures, what the future networks will be there. Then there is a study group 15, pretty much optical, fiber, all related, that specifications are dealt in study group 15. Then 16 is the digital media, 17 is security, then there's a study group 20 on the IoT. So these are the study groups, and then they meet regularly. Any standardization effort, we must know, is contribution driven. If there is no contribution, there cannot be any standardization. There should be a contribution, and there should be a stakeholder participation to discuss whether it is accepted or it is accepted with modifications. So there has to be a standardization, and there has to be a consensus. Now the consensus has different meaning for different organizations. In ITU, the consensus is the near agreement by all the members, but it is not unanimity. And it depends on the topic, it depends on the context on which a particular standard is being pushed by a contributor. So the effort of all standardization bodies, including ITU, is to develop a consensus, because the consensus, reaching consensus means it is acceptable, and it will mean its implementation in various products and various networks, whatever you say. Otherwise, there may be standards, there may be recommendations, you have agreed, but when it is only on papers, it could so happen also. Now the T sector study groups meet quite often, and then if there is a dispute and if there is a duplication, then they talk to each other through what is called a license statements. So they will send a license statement and tell that what we are doing, you are doing, and then there are other methods wherein they coordinate between each other. For example, one is the joint coordination activity. So there are rules and procedures laid down, at least in ITU, because it's a government-driven kind of a body. So it is very fairly, everything is made very clear. Once in 4 years, so these all study groups, their work is kind of supervised by a body called TSAG, Telecommunication Standardization Advisory Group. So TSAG meets also, let's say, once in 5-6 months, and then they see if there is a two study groups have something which they are not able to decide, and TSAG must intervene. Now WTSA is above TSAG. World Telecommunication Standardization Assembly is, as I said, meets once in 4 years. The last meeting was in Geneva 2022, but it was supposed to happen in India at Hyderabad in 2020 because of the COVID. It got the last period got extended from 4 to 6 years because it happened in Geneva at 2022. But to again confirm to a 4-year period, they have put it in 2024. So a short 2-year cycle this time, just to again synchronize it with the 4-year cycle. India had in one of the council meetings presented a case for holding WTSA, and ITU had very kindly agreed. And this time it is in October, and the first 3 days are common with IMC. So it is going to be a big event because IMC itself has a international standing, and this one WTSA is also of importance. So I think there will be good synergies. Now, as I said, that there is a need for participation. There is a sustained campaign in ITU which is called BSD, how to bridge the standardization gap. So there are countries, there are organizations who are very active in the standardization. There are activities, there are countries which are just observers, and there are countries who contribute, but they need to improve. Another campaign this time is what ITU is telling now, that is called Network of Women. So in line with the standardization, there is a Sustainable Development Goals of UN, which the goal number 5 is gender parity. That means there should not be much gap between. So this Now campaign this time aims to target that 35% of the delegates in WTSA 24 should be women. So this is something which we all have to work. So as India, what we would do is make sure that at least and I have some experience in TEC, a standardization body of Department of Telecom, and I know that there are many exceptional lady officers who are contributing regularly to the standardization efforts. So this is one thing, Now campaign and the bridging the standardization divide. Now for that, TEC has made participation in standardization as a portal driven. So you can go to the website, there is a link, and you can choose which study group you are interested in. So you can see what are the all study group activities are governed by broad standardization area, which are called questions. So you can see, if let's say in a question 11, what is question 4? So you will know. So if you feel, so initially it looks that it is very technical. Believe me, it is not very technical. It is technical, but you can bring with a small step forward. You can go through the text. There could be some changes which you think you can make it better. You can make it more acceptable, that test. So you start with that. But these are the two main messages. WTSA itself is the administration of standards. Not much technical will only be discussed if some specification which is finally not approved but the study group may decided to escalate its approval to the WTSA. Plus, the rules and the resolutions of how to handle standardization work are discussed. I think I can talk, but I think in the interest of time, I'll end. But my main message is there should be a participation from ladies, and there should be, India should make its presence felt in the standardization this time. So this is the request, so kindly participate in large numbers. Thank you.
Thank you, Shri Rituranjan Mitterji, for elaborating technicalities in such a simple manner and also encouraging women folk. Thank you. And now, ladies and gentlemen, we have Shri Vinod Kumarji. He's an Indian Telecommunications Service Officer of 1995 batch, having an experience of more than 25 years, serving in various capacities in Government of India. He's currently leading the standardization activities on quantum technologies in Telecommunication Engineering Center.
Thank you. So, Sir has already, Mr. Sir has given some introduction about TEC, and you are all aware that TEC is the standard setting body for telecom sector in Government of India. So, normally what is the standards which are to be set for telecom sector to be used in the telecom network is done by TEC. And we are from the one vertical from quantum technology. So what are the activities happening in TEC as well as in the international level that I'm going to brief it. In quantum, we are having broadly work going on in the cryptography field, like PQC and QKD. We already had a session on PQC by NIST just before this session. So most of the brief has been given by him for the PQC part. I'm starting with the QKD one. So in QKD, mostly these are the 4 organizations which are working for the telecom standardization: ITUT, ETSI, ISO-IEC, and IEEE. ITUT brief introduction has just been given by Sir, and in ITUT, out of the 11 study groups, there are 3 study groups where the work items related to quantum technology are being handled. The study group 11 has work items in the question number 2. Study group 13 has work items in 2 questions, one is question number 6 and question number 16. And 17 has the one question which is on security. It has security for emerging technologies, question number 15. So these are the 3 study groups which are broadly handling the quantum technology related items at ITUT. Most of the items which are being handled in ITUT study groups are basically in study group 13, which is on the future networks. So we can actually divide the work being done in study group 13 in broadly 5 categories, which is QKD network, that is QKDN is quantum key distribution network, QKDN basics, enhancements, application, quality of service, and QKDN enabled future network. So these are the 5 broad categories under which the study group 13 works are going on. So to start with the basics, the large number of recommendations have been given by study group 13, which is Y series, Y3800 onwards. There are certain recommendations which have been for the QKDN networks. So 5, we can see the 5 recommendations on this page. I'm not going to read this. I mean, you can just see, and there's nothing specific. And there are some QKDN application. There are this 3808, 3809, and the supplementary 75 are the recommendations in the applications. Then again, QKDN enhancements, 3805, 3814, 3815, 3819, and the supplement 79. These are the recommendations. Then on QoS, that is the quality of service, we are having 3 recommendations: 3806, 3807 and 3811. And again 3812, 3816 and 3817, these are the total 6 recommendations on the quality of service. Then QKDN, multi-QKDN interworking, there are 3 recommendations. This is 3810, 3813 and 3818. Then we are having 3 more recommendations, that are supplementary recommendation under study group 13, that is supplement 70, supplement 74 and supplement 80. So these are all from the study group 13, the recommendations which has been issued. Then we are having some ongoing work items. There are the 7 work items listed here where still work is going on, and some more are there here, 15. So there are 14 and there's 15 work items on study group 13. Now the second most items which are there on is the study group 17, which is on security. So on security, these are the recommendations that is, they are under X series, X170 onwards are on the security part. So X710, X1712, 14, 15, and this is the one recommendation on random number generator. So there are total 5 recommendations here on quantum security. Then there are ongoing work items on security. These are 7 work items here. Under study group 11, that is protocols and signaling, there are 5 work items on which recommendation have been made, but it is yet to be published. So these are already closed. Sir is the chairman of this study group. This is closed for this 5, and 3 there are some still work is going on. So this is the total study group where QKDN work is going on in ITUT. Then we are having HC. HC has also issued large number of this recommendation. There are some 12 recommendations basically has been issued by HC, and I mean the titles are written. I'm not going to read and waste your time. Then ISO IEC basically they are working in there is JTC1 have been doing the work on the QKD quantum networks thing, but recently ISO IEC has set up one JTC and quantum technology separately, that is JTCQ, and it is going to start the work on QKD very soon. They are just issued, these 2 recommendations have been issued by ISO IEC on the security requirements part of the quantum technology. Sorry. Okay. Yes. So IEEE SA also very few work items are available right now. There's a 4 work items which I could find. Their work is going on. This is all from the international bodies. Then in TEC, TEC had issued these 2 standards, that is quantum key distribution system and quantum safe and classical cryptographic system. And the work in progress is on the quantum random number generator, which we hope to issue soon. Then the discussions we had yesterday, we are going to then work on again this modifying the first standard, that is quantum key distribution system, where the earlier standard has been issued with 2 protocols, that is DPS and COW protocol. We are going to see which other protocols which we need to add it and modify these standards. These 2 works are going to be done by TEC, and we have just recently constituted this National Working Group on Quantum Technology. In TEC, normally working groups are framed, they're constituted basically for mapping to the study groups of ITUT. So they are one-to-one, the National Working Group with the ITUT study groups. But the quantum work items being distributed across the three study groups, and so we felt that the focused approach and coordinated approach is required for having the work to be done in the quantum technology. So this work group has been constituted, and we had recently sought the nominations for this National Working Group for Quantum Technology. Maybe very soon we are going to start working with this quantum NWG. Just formation letter we are going to issue next week, hopefully. So we have already invited all the people, means the people from academia, research institute, industry, whoever is working in the quantum technology field, to join this national working group. To start with, we will be working on focused totally on the communication part, but wherever we feel there is a gap related to quantum technology, we can take up through this national working group. That's all. Thank you.
Thank you, Shri Vinod Kumarji. And now, ladies and gentlemen, our next speaker is Dr. Anandita Banerjee. Dr. Banerjee is at present working as a senior scientist, project manager at CTEC Pune. She's working on aerial quantum communication platforms, fiber QKD and QRNG, testing and benchmarking of quantum devices. She has 4 US patents awarded and 1 Indian patent awarded in quantum technology area, and has published more than 20 journal publications. She has also co-authored a book on optical quantum computation and quantum communication, published in SPIE Spotlight series. So now we have Dr. Anita Banerjee ji.
Thank you, ma'am. So first, I would like to thank the organizers for giving me this opportunity. And also, it's such an honor to share the dais with eminent people, and also to have eminent people, dignitaries, stalwarts in quantum community across the dais. So this is about National Quantum Standardization, Testing and Evaluation Center. Why do we need it? What can come out of it? And how it can be made. So these are some thoughts which I want to put across through this presentation. Next slide, please. So now let us first look at the market survey. Let us talk about products which has a higher TRL level, say QRNG and QKD. So we have quite a lot of suppliers, vendors in QRNG, a quantum random number generator, which has, and they all addressed different sources of quantum entropy. And that is the basic part which brings to you the quantum flavor. And then, of course, on top of it, there are different algorithms and implementations which they are doing, and trying to push it to the users for maybe going straight away to some applications or in their R&D labs. And another product is quantum key distribution, which is nothing but supplying symmetric random numbers for encryption. And they are coming out with different process methods, how it can be incorporated. Again, different QKD protocols, coherent one-way, or different subcategories of differential phase reference protocols. Even entanglement distribution is also some people are working on, and we heard Dr. Joy Ghosh from IIT Delhi yesterday. So this is something which is happening, and as we understand, these products are of TRL level 6 to 7, fine. And of course, there are some other products in the market, in Indian market, which are from outside India, and those products has also been tested rigorously by some academicians. Some of the Indian products has also been tested by some academicians. Fine, so this is the Indian scenario. Now let's move on to the next slide. So I was talking to an old friend, Mr. Karunakaran, and we came up with this kind of a scenario. Hypothetical situation. So we have products in Indian market, right? And let us talk about 3 CDAC centers, one in Noida, can be Delhi, Pune, and Bangalore. So I have my 3 team members who want to do quantum secure communication in these 3 centers. You can see how they are separated by even thousands of kilometers, right? And these 3 centers, we want to do a VPN talk, and it has to be a QKD based, security provided. And we can have different internet ISP providers. One of them can be Reliance, another can be Airtel, and another can be, say, BSNL. Okay, and we have enterprise routers. Okay, CDAC Delhi has an office in the 3rd floor. Okay, and there are several other offices. Then we have, for some reason, say the Bangalore CDAC Center would like to go with QNU Labs product. Delhi would like to go with C.QKD product. And in Pune, we are also working on CVQKD, so maybe we would want to have that product there, okay? Now, how is it going to work? The interoperability, how are we going to define the interfaces? How reliable will this be? How safe will this be? How will this fit into the existing ecosystem? And that what brings us to the next slide, please. The interoperability, regulations, standards, validation, certification, and that is the reason we are here today. And this panel has so nicely put up, they have covered the standardization global situation as well as the national. So now let us go to the next slide. Well, so we had first day Dr. Ekta Kapoor briefing us about the National Quantum Mission, which has 4 categories. Communication is also one of them. And we're talking about bringing products in market. We're talking about doing inter-country, please note, inter-country quantum communication, intercity quantum communication. So that is the reason I had put that first slide, okay? So there are going to be different representations of the product, okay? And as far as the logic of standardization goes, if you look at the TRL level 1, 2, and 3, the other side where I have written science, these are the customers of standardization. So science means, for example, the scientists need to come up with some measurements and some coordination, right? So they will be needing these terminologies, these definitions for a fair comparison and to bring out more innovation. So they are the customers of standardization. So I think National Quantum Mission should be addressing this part or incorporating this part as well. Then we go to TRL 4, 5, and 6. We have startups in Indian market, I think 4 to 5 of them. QNU is there, TACBIT is there, then SkyTail is there. There are other startups as well. My apologies if I'm not addressing it right now, because the importance is from TRL 4 to 5 and 6, the customers of standardization are those, particularly the system integrators or the ISP, internet service providers, because now they need to integrate those devices which the startups of new technology bring in and try to see how it will fit into these scenario. And that is what was Dr. Abhijit from IIIT Delhi talking about, and also in our previous session, that was the main concern, right? Then from TRL 6, 7, 8, and 9, the vendors are the customers of standardization, where you would want to bring in safe security, safe implementation, hardness being addressed, and that is where the concerns were rightly put up by Dr. Rakshit in the first session. Next slide, please. So this idea I have taken from the focus group of quantum technologies. I mean, I have shared the link here as well. So they kind of tell you that, particularly in quantum key distribution and quantum communication and PQC, I'm not sure if it's very much visible here, but I can share with you the slide. It talks about how these different areas, standards are worked upon in these particular areas, okay? And also, it's the same thing but represented differently, kind of giving you a feeling that how much it is needed and why it should be taken up urgently. Next slide, please. Now, so what we proposed, so I was working on this idea after I moved out of a private startup and then joined CDAC. So I figured this out in some December 2021, that why do we need a test and evaluation center? See, if you look at it, the progress levels of all the 4 verticals are different. Some are at higher TRL levels, some will come up, and we do not know. We cannot even predict precisely when this is going to happen. The requirements of all these new technology verticals is going to be different. Some might be dropped, some may change with time. Then some products can come to market even before proper testing. This should be taken very seriously because we're talking about strategic products. Interoperability of systems, that's what I brought to you in that second slide. Then rigorous testing and evaluation and how it wears out, maybe in 3 months, 6 months, 1 year, has that been analyzed, okay? Then no leading agency at present to unify the efforts for best practices for testing and evaluation of quantum products. So here I would say that things are being worked on as we speak. So we should be positive here. Then such an effort is going to help different stakeholders in a network, and it has been addressed in the yesterday's session. Then this is something very important because the testing and measurement equipments are very costly, and as you had seen, the test beds. So facilitating affordable testing and test beds for the, I would say the vendors are actually small scientists group because they are working on new technology, and they have taken up this challenge to prove something in parallel with academia, so that should be respected. And I think they should be facilitated with such a platform. Next slide, please. So now let us look at these test facilities globally. Friends, world has been working on this for last 15 years, okay? And these are some I could come out with. Of course, the quantum hacking lab is somewhere where people look into the detectors, which are the Achilles heel and also other vulnerabilities. You can find many research articles in archive there. And also, there are other groups which have now come up. I think it will be interesting to have something like this for our country as well. Next slide, please. So in 2022 August, we got a mandate from our parent ministry that we should be doing a brainstorming session and understand, that such activity, there should not be any overlap or how it has to be taken up, who is interested. And it was, attended by some 90 organizations, 90 people, many of them were representing the organizations. And we got some mandate from that particular activity, which was, there was a unanimous agreement for the need of establishing such a facility in the country at the earliest. It is the need of the hour. So whoever is being given this responsibility should act as a bridge between the SDOs and the industry. We should be starting off with communication first. Tools, technology, infrastructure should be present and be made available to industry and users. And security aspect should be critically analyzed in a holistic approach, okay? Then of course, capacity building, knowledge sharing should also be taken up by such an organization. Next slide, please. So the objective of such a center would be evolving process, benchmarking, test methodologies, security evaluation, and approach towards quantum communication and computing. Of course, it is also important. Suggesting experimentations by academicians, okay? POC testing, test beds, investigate possibilities, limitations, and uses of quantum safe methods, defining them, also hand-holding the industry and the users towards it, a national recommendations for quantum safety assessment, monitor and participate in international efforts, encourage, the purpose of standardization should be encourage innovation, promote adoption and integration of new technology, and of course, support and nurture the Indian ecosystem. Next slide, please. So this is something, I have also been doing a literature survey, and we came out with this kind of an architecture where for some things, as Dr. Natarajan was saying, his lab also does side channel analysis of post-QKD, right? So we need to work with different labs together. We need to leverage with the methods which are already there. Some methods can come up with academics, in consultation with academics who can be theoreticians, who can be experimentalists, okay? And we need to have these. So this is also addressing computing and communication, because I've written quantum devices to perform hardware, source generation, manipulation, and measurement. And then it kind of goes back to the test and evaluation center. So, if I could, this actually model needs a lot of brainstorming in itself, and maybe we can take it up sometime later. But this is an idea which I think is also what the world is looking upon. And we need to work with all the industry, users, academia, R&D, and SDOs. Next slide, please. So, our initial effort, we have done some MOUs and some R&D discussion from CDAC perspective with the SDOs and academia and industry. Okay, so this is just wanted to show that we are in sync with them and we represent their ideas and motivation as well. Next slide, please. So now, while analyzing a QKD product, okay, so this comes from my experience to have a hands-on in bringing a product up from a theoretical design to a product. So you basically have an optics layer, and that is where the quantum parts comes in, okay? In optics, you have the quantum source generation, quantum source encoding, then you have state transmission, then you have demodulation, then you have a detection, and they can be different. You have heard of Dr. Shomia yesterday, then CV and DV kind of a protocols, entanglement-based protocols. So this layer is actually what executes that kind of a protocol. Rest all, I think, which has been covered from sets, is classical post-processing. So this part is very important, okay? Because this is actually implementing the quantum part, and it has a quantum channel. The quantum is bounded by the powers of quantum Eve, okay? So it has all the powers it can do within the limits of quantum information. And, okay, so fine. Then we go to analog electronics interface. So this layer has all the electro-optical devices, analog electronics. There are a lot of them. It deals with signaling, sampling, mixing, voltage to current conversion, time to digital, okay, analog to digital. All those things are covered here, okay. So when I'm naming them, nothing is perfect, okay, and whatever is not perfect, it actually leaks information. So keep that in mind. Then we go to driver and calibration algorithms, okay. So this part is a software that deals with or conditions or deals with this lower level electrical signal which drives the electro-optical modules and the electronics. Then we have the operation cycle, which is like a state machine, kind of understanding which device will be working first, whether it is a QKD giving the source or it is giving or the service signals like calibration and synchronizing. Then we have the post-processing, which has different layers. After transmission, we have sifting, we have error correction, we have hashing, key reconciliation, all those things, which are very much classical in nature. Then we have application interface. So I'm slowly moving to the higher levels, and installation, which is a manual process and maintenance. The idea is the entire thing which I spoke about, the first part, optics, is important. Quantum attacks can be on the classical as well as on the quantum place. So basically the secure key which we generate is a function of the specifications of the optics and electronics, okay? So this is very important. Now suppose we have come out with some kind of a device. Now let us look at the second layer, the hardness against implementation imperfection. So the first says non-tested, which means that a security critical imperfection is kind of identified but not yet taken care of. Then we have something called insecure implementation. Countermeasure has not been implemented. Then a partial effective solution. That means a countermeasure which has been implemented either opens up vulnerability in some other imperfection, some other things can come up, or it has not been very carefully, holistically analyzed. Then we have a solution robust. So in solution robust, you implement a countermeasure, But then you have to also understand that with time, it can either fall back to partial effectiveness or it can move up to a complete secure solution. So these are the different levels we have to understand for each and every imperfections. And I think if you want to understand that, you should look into Professor Anirban Pathak's talk, where he explained different hacking mechanisms. And Dr. Prabha was also talking about different levels of the quantum attacker's strength, independent attack, coherent attack, so you can check that out. So we need to ask, what is the assumption we have taken for a quantum security model? What is the security model which the vendor is bringing? What is the quantum adversary model which you are trying to look at? How is the key analysis done? The key analysis is very important because QKD is not, it is probable secure, okay? If I'm saying it positively, I should say it's probable secure because it opens up information leakage by 1 to the power n. N is the number, is the length of the secret key rate. So if you have a huge secret key length, then it is kind of secure, but if it is less, then you open up, you give out information a lot. So we have something called finite key analysis. That kinds of puts an upper bound to the final secure key length. And my friends, if the shifted key length is within a particular range, then it is good. If it is more than that range, then it exceeds the bound which has been set up for by the finite key analysis. So this is something very important. Composability has to be addressed because then the random numbers which has been obtained from your QKD system should be safe enough to be used for any other cryptographic device, okay? So not all protocols have this kind of a theoretical analysis done. So we have to understand what is the protocol which has come up. Can it sustain the rate? Because here we are just saying that, go for 100, 200, 150, but does that protocol support that distance? That has to be looked at, right? Okay, next slide, please. Then we come to QRNG. Well, I was very much fascinated by quantum random numbers, but when we started working on it, it was something I felt, okay, it's just random. Nobody has defined it. We do not know how I can make sure it is quantum or it is classical, because random numbers are random, and the way to test it is based on some statistical tests, right? And that may have been carefully designed. So how to understand whether the random numbers produced by a QRNG, if it passes most of the statistical tests, say if you do one NIST 100 times, it may pass 90. Have you tried? Have you tried taking a huge data, let the machine give you some gigabits, okay? Let it generate, and then you start looking at it. You have to use some AI or other models also to analyze that. So I don't want to exceed my time. There are things I have listed here, and if anybody is interested, we can talk about it. So QRNG is not just generating some random numbers. It's a lot more analysis which goes into it. And I agree with Dr. Rakshit's statements, and this has to be taken up very seriously. We need a team of experimentalists, theoretical scientists, and state-of-art performers to look at it. Next slide, please. Okay, so how this is going to impact the national ecosystem? Of course, knowledge and training, increase the pace of quantum technology development, make in India products which you can accept, which the ecosystem can accept with confidence. Acceptance and confidence, yes, of course. Then India stock holding of quantum components. Standardization, it has been nicely addressed by the previous speakers. Skill, workforce development, and generate revenue. So this is what we are looking at. And I think that brings me to almost the end. Next slide, please. Okay, so this is one project we are working on. My gratitude to the Ministry of Information Technology for giving us, this kind of a thing, which covers the layer between the terrestrial and the satellite. And drones are important because they can maneuver, they can be reconfigured. Of course, it has to be made in a way that it can be lightweight. The power things has to be looked on. So this is something very interesting we can discuss maybe after the session. Next slide, please. And this is our team. We started with 1, then 3, then then 13, and now will grow to about, say, 17 or 18 in 3 months. These are the projects which we have started in CDAC Pune. This is the clean room, which is now ready to work. And interestingly, now we have to expand because we have so many projects working on it. And we also have access to very high compute power. That is the reason I was talking about in QRNG. We are doing some tests where we can leverage both from the scientific as well as from the compute perspectives. So yeah, I'll be interested to talk more maybe after this session. And this brings me to the last slide. Thank you, everyone, for your patience.
All right, thank you so much, ma'am, for such a detailed study and all. Now we are joined by, ladies and gentlemen, Dr. Martin Ward from United Kingdom. And to tell you about Dr. Martin Ward, he works as a senior research scientist for Toshiba Europe in their Cambridge Research Laboratory in the UK. He is chair of SEED's Industry Specification Group on QKD, which is specifying aspects of quantum key distribution, including security and interoperability. He also contributes to standardization work as a QKD expert with an ISO and ITU-T. Following a DPhil on quantum optics at Oxford University, he joined Toshiba in 2001, where he led the development of telecom wavelength single photon and entangled photon pair sources. So we welcome you, Dr. Martin Ward, in our session.
Okay, thank you very much.
Thank you.
Appreciate the invitation to speak here today. So I'm Martin Ward, the current chair of ETSI's Industry Specification Group on quantum key distribution. So we think of QKD as a security primitive to agree shared bit strings between remote parties. So it involves the transport of quantum states and the security being based on entanglement or the possibility of perfect cloning or measuring unknown quantum states. And it has the proposition of a composable security proof for QKD protocols. So we see quite a number of different aspects that are rather new for standardization and that need to be addressed. So the ISG is working in a number of areas. So firstly, security. So we need to address implementation security, evaluation activities, protocol security proofs, and authentication. But along with that, it's important to be able to characterize some of the devices that are used in QKD systems. So components and QKD modules and penetration testing. Then we have think about interoperability between systems. So in particular at the moment, the classical interfaces that are used to connect QKD systems together to form larger networks. And we also need to consider the vocabulary and improving and aligning the use of terminology across standards documents. So we can consider QKD as a sort of sustained secure key expansion technique. So we start out with a pre-shared authentication key, and QKD offers the possibility to generate keys from that, which have totally fresh entropy in each key. So the quantum safe side of QKD comes from the fact that there's no algorithmic relationship to previous keys. But of course, we still have to worry about and think about the implementation security of the protocols. So in terms of protocols themselves, we have a group specification on security proofs. So it sort of sets out the fundamental structure of QKD protocol and the way in which a security proof should be constructed. First version was published in 2010. The fundamentals remain largely unchanged, but we're working on an update to bring together the newer terminology that's being used, aligned with the protection profile, and handle developments in post-processing techniques that have happened since then. So whilst the document discusses implementation security, it's not the main subject of this deliverable, and we are working on other areas to handle that. So there are a number of different types of QKD protocols. So in terms of the way in which quantum states are distributed to deliver the QKD keys. But we can pick out from those a number of common aspects. So we have we talk about two stages, so a quantum stage and a post-processing stage. In the first stage, the quantum state preparation, transport and measurement. And then there are a number of different elements to the post-processing stage that can happen in slightly different ways in different systems, but there are some common themes there. So we then need to think about how we can start to work towards certification of QKD systems and the evaluation of products as they come through. So the ISG has been working on a protection profile. So we've selected the common criteria as the method for evaluation as a widely used international scheme. We published the first version of the protection profile in April this year. It was based on version 3.1 of common criteria. Over the course of the last year, we've been working with BSI Germany, so the protection profile has been going through an evaluation in order to certify the protection profile itself. And we've recently published a certified version of the protection profile, which has been updated to conform to the latest version of the common criteria. So the BP frames the work that we need to do in terms of developing background documents to support people in making certification applications of products. So things like protocol descriptions, attacks, evaluation methodology, and so on. So the target of evaluation in the protection profile is the two. So our protection profile at the minute is limited to prepare and measure QKD systems. So the target of evaluation is a QKD transmitter module and a QKD receiver module. Since QKD is aiming towards a fairly high level of security, the protection profile is targeted at evaluation assurance level 4, augmented with two components to ensure that we have advanced methodical and vulnerability analysis of the QKD protocol and the what's new here. Obviously, it's quite a different security primitive from ones that have been evaluated before, so we felt it appropriate to have a high level of vulnerability analysis. And also a matching level of developer environment security. So the protection profile has been set up as a fairly a nice standard PP that will cover all sort of prepare and measure systems, hopefully. And then we've added four component optional packages that can be pulled in to add trusted user interfaces, authentication, self-protection, provisioning after delivery, and local authentication of users. So people can optionally add those as needed. Another aspect that's critical to QKD is authentication. So we have a group report which we're developing at the minute to study the types of authentication in QKD systems. So in particular, QKD protocols assume an authenticated classical channel. And it's important to consider composable authentication schemes such as Beck and Carter. And currently it's an area where there's a lack of existing standards. In terms of characterization, the detailed measurement schemes are important for characterizing optical components in QKD systems. So we have a specification on some of the core components to the system, so photon sources and single photon detectors. So these set out very detailed schemes for measuring some of the most important parameters. So this is important as part of certification, but it also will hopefully help to build an ecosystem for supply chains for components. Then we have a document development to start to look at performing characterization measurements on complete modules, so initially transmitter modules, And there are some complicating factors when you start to try to measure some of these parameters in a complete system. So that's being addressed there. And let's turn to interoperability. So the sort of classical interfaces that are needed to put QKD systems together in a network. So we have some very well adopted specifications for retrieving keys from QKD systems. So a REST-based one for putting keys over HTTPS, and then a session-based interface as well. SDN is of growing importance to many telecom operators, and so we have developed a number of specifications for introducing QKD into an SDN sort of architecture. So first of all, this one that deals with the interface between a software-defined QKD node that has an agent within it and an SDN controller. Then secondly, looking at orchestration, so people might have a separate optical transport network, so we needed an interface to go between an SDN controller for a QKD network and a providing SDN orchestrator, and also talk to the OTN controller. So another aspect that's quite important is that you tend to find in real world you have a number of networks that need to talk to each other. So they may be under different control perhaps by different providers, and there becomes a need to pass keys horizontally between those networks. So we're developing a specification for interoperable key management system, for passing keys between networks. And a corresponding network to allow, corresponding specification to allow orchestration in that case as well. We're also looking at a QKD monitoring interface. So interface and data model to define the way telemetry can be done to enable operators to monitor what's going on in their network. So that's a new work item that we're just beginning. Then in terms of network architectures, we've been working on a group report to analyse aspects of various QKD network architectures that are seen around the world. Looking at the potential for interoperability, the architectural components and their interfaces, and really the commonalities between the architectures. And we're just about to start developing a group specification to find a modern architecture for networks. Okay, so an ISG is composed of ETSI members and ISG participants. ETSI is headquartered in France, but it's open to members from around the world, and it has so people are welcome to join an ETSI member, but ETSI membership is not a requirement to participate in work at the industry specification group, and participants can take part as well. We're pleased to have a very international profile in the ISG and QKD, with people from many of the countries that are working on QKD. And we're pleased to have a broad collection of experts with a broad range of experience that's necessary to consider the various aspects that are important in developing standards for QKD, from the quantum side, the security evaluation side, and also pulling in vendors of applications for systems, telecom operators, and so on. So that's really important. People are please very welcome to come and join us in work. So thank you for your attention. Thank you.
Thank you, Dr. Martin, for joining in for our session. Thank you so much. And ladies and gentlemen, finally we have Dr. Ajay Kumar Mittalji, who has a career of over 44 years in the field of telecommunications and is currently associated with TSDSI as advisor with special focus on standardization, related activities in 3GPP and ITUR. He's an ex-ITS officer and has worked in Department of Telecommunications in various capacities. So now we have Shri Ajay Kumar.
Thank you very much. Good afternoon, everyone. So the person is speaking just before the lunch has a pressure that I'm standing between lunch and the audience, and also another pressure if the session is running late, then maybe everybody expects that I should finish fast. But I assure you that whatever pressure you have on your mind going deep into technology, my presentation is not technical deep dive at all, it is informative. So be assured of a lighter presentation. Thank you. So with that word, so in this slide, if you see the word 10, maybe you are becoming inquisitive, what is this 10? So this TSDSI is actually 10-year-old this year. So we are celebrating 10th anniversary of TSDSI. So this 10 is, our Marcom team has created this image. So what I'm going to talk about is the TSDSI activities towards standardization in quantum communications. Next slide, please. Or I can run through this. Yeah. So about TSDSI, we are a standards organization in telecommunications and it's called SDO. And you heard from Mr. Vinod Kumar about the standard setting organization. So TEC is a standard setting organization for telecom in India, and TSDSI is a standard development organization. So there is a difference that so TEC actually is the final authority who decides what becomes a national standard. But we create standards and we hand over to TEC for consideration of making them national standards. We are a society, non-profit society, registered in 2014. And we are recognized by Department of Telecom as India's telecommunication SDO, and we work very closely with other organizations in the world. What happened? Yeah. So we are a membership-driven organization. It's not an office-like environment. We have a secretariat, but to support our members and technical activities. Maybe this may not be so much readable, but I can explain this in brief that we have members from all the organizations who have to do anything in telecommunications and applications and verticals. So anybody and everybody from those fields like manufacturers, domestic or international telecom service providers, R&Ds, academia, government departments, everybody is our member, and we have three categories of members: corporate, associate, and observers. So they have different privileges. I will not go into details of that. And if an organization becomes a corporate member, they have the maximum privileges and rights, and associate and observer members have some limited privileges. 3GPP and 1M2M are our two main non-governmental bodies whose membership can be acquired by virtue of becoming a member of TSDSI. So very quickly going into why we need standards. And I will not explain each of these bullets, but pick up some important points are that there is a technological development happening, and we want to actually make it a standard for everybody to use. So standards are needed there. Then some market requirements are coming. For example, everybody is now fearing that quantum computers will actually hack our protocols, security protocols very fast. So we are getting ready. So there is a requirement. So there is a need of standards. And interoperability, that there are two systems made by two persons, but they don't work together. So if you are sitting at two different ends, or you are two different entities but want to communicate, but they don't the systems you have are from different parties and they don't intercommunicate. So the interoperability is a major concern which standards actually address. And we have seen all over the world, different countries and different organizations are making standards. There are different entities who are creating different products, and nobody currently knows which standard they comply to. So interoperability is the major thing which is resolved by standards. Then reliability, of course, is an inbuilt thing when you create a standard. Reliability of the equipment and the technology is important. Regulatory compliance. You had heard about this in the previous sessions, and this session also about that we need to comply to the national regulations or international regulations. So the standards must address this, and by virtue of standards, economies of scale arrive, because every manufacturer actually makes equipment to a particular standard, so volumes become larger. So if you are in silos and if there are 10 different standards, so people will be making smaller quantities in their own domains, and the economies of scale will not be achievable, and fair competition. And by virtue of economies of scale and common standard, economies of scale are achieved, and the standards whole ecosystem then mobilizes the market, the deployments, the ecosystem, and further innovations and development of technologies. Now this is a standardization life cycle. This may also not be so much readable, but I can explain quickly that there are three basic building blocks of a standardization life cycle. That's in pre-standards work, standardization work, and a post-standardization work. Pre-standards is normally what we are doing today. Sitting here, we are talking of the requirements, what somebody is doing, what somebody else should do, what are the gaps in standards or the technology which is available. So there will be papers published, there will be some work being done in different R&D organizations, there will be market requirements coming from the different corporate bodies or companies, or some companies working on some product, but they don't know how to market it, how to bring it to the standards. So all that work happens outside a standards body as a pre-standards work, and there the requirement emerges that, okay, some idea has emerged, now we should make a standard on this. So after pre-standard activity ends, the standards body come into picture, and a proponent who is a member of the standards body then brings a proposal into the standards body, which is, in the case of TSDSI, it is called new item proposal, which goes into a study group. So the idea which is being brought for standardization may not be mature enough to do a normative work straight away, so it goes into a technical study cycle, which recognizes what are the requirements for making standards, and whether a standard should be made or not, or we keep it at study level, or go into the standard cycle, or maybe idea is mature enough, and then it goes into a normative work straight away. So at that stage, when this study group is debating on these ideas, the IPRs, the IPs which the companies or the members hold, they have to declare there. So this also, brings to the notice, I want to bring to the notice of everybody, that the standards are an opportunity for embedding the intellectual property of the companies or the owners into the standards. And that is the opportunity for creating a monetization chance or monetization trail in future when the products are manufactured as per that standard. So that I didn't cover in the first slide, because it is important to see where actually the intellectual property, IPs or the patents held by companies, they are inserted into the standards. And some of them may become standard essential patents, without which the standard cannot be implemented. And that is where the patent commercialization becomes really important. So by this process, and these patents are to be declared at an appropriate time to the standards body. They are put on the website of the standards body, and the patent declaration also says that, okay, we are ready to license it to any person who asks, the implementer, and then the implementer and the patent holder, they go into negotiation, which happens outside the standards body. And so it becomes a standard, and then within TSDSI, the process is that after the study group approves it, the general body of the TSDSI approves it, and then the last stage is we send it to TEC for approval as a national standard. So TEC have a process, and the difference between TSDSI and TEC process is that TSDSI is member driven, so only members are debating and contributing to the standards, but in TEC, when they go for national adoption, they take public consultation process, invite comments from general public, and there is an internal process that how they deal with the comments and how the standard is finally adopted as a national standard. And TSDSI also has membership with 3GPP, 1M, 2M, ITU, ITU-R and ITU-T. So there is a process I will explain in the future slides. And post standards is again outside TSDSI. Here the proponents who have actually created the standard, they evangelize the standard with the common market to make known to the people who are the users that this is what is available and how it can be implemented. And this post-standard activity also creates feedback about the shortcomings on the standard or the errors which are encountered while implementing the standard, and that feedback again comes back to the study groups for modification and creation of the next version. So in TSDSI, we have two study groups today. One is the study group networks. There is a list of items, focus areas. Quantum is one of the focus areas of study group networks. Study group services and solutions, which actually deals with the security and services and solutions part in telecommunications. So they are also having post-quantum cryptography as one of the focus areas, and it will go up now in near future. Additional items will come. So we have a standardization roadmap. Currently we have roadmap 2.0, which was to be implemented over a 3-period horizon. So they are the vertical. If you see the colored ribbons, those are different domains in which the items are listed, and quantum security, if you see, was the item against which the PQC was done. PQC study was done in TSDSI, and this is a regular exercise we are doing. Currently, we are working on roadmap version 3.0, which will be on the horizon of 24 to 26, that means covering the current year. And we had a workshop recently where we received 4 specific proposals on quantum communications from the industry stakeholders. And the roadmap is an exercise where we invite external stakeholders also who are not members of TSDSI, because we want market feedback that what should we do in standards arena. So here, if you see next generation secure, adaptable and cost-effective solution for quantum security, underwater QKD, quantum communication security and modeling, and PQC in embedded systems and all that. And we have a TRIP forum which we'll introduce in the next slide, where different standardization gaps are being studied, and more items will come into our domain very soon. So this actually summarizes the TSDSI's ecosystem and its activities. If you see TSDSI, below that arc, you will see the basic activities which we do, and we have connections with the global SDOs. If you can see here, TSDSI work when it happens. So we have a membership of ITU. We can contribute to ITU directly. For example, we did an amended version of 5G, which is called 5GI, which we submitted to ITU-R, and it is there as a separate 5G standard in the ITU recommendations on 5G. And we have a very close working relationship with TEC, as I explained in the previous slides also, that we can take our contributions even via TEC to the ITU. That possibility exists because that close coordination has been done in the past and can still be done whenever it is required. And 3GPP and 1M2M are two forums. 3GPP is for global mobile communication standards, and 1M2M is for the service layer standards for IoT. So these two bodies, we are our members, and TSDSI members can take individual membership of these companies by paying some extra fee. Otherwise, they cannot become member of 3GPP or 1M2M. And we do have adoption agreements. For example, ATSC is the broadcast standard, IP-based broadcast standard. We have adopted their standard, and currently they are with TEC for adoption as a national standard. ETSI, we have adoption. We have transposed some IoT and NFP standards of ETSI. IEEE, we have adoption agreement, and some adoption process is in pipeline. Now, what we have been doing in quantum domain, because this is a very new area, so right from 2021, some initial discussions started. So we have a annual flagship event which is called TTDD, or TSDSI Technical Deep Dive. It's an annual conference which we have, international conference. And in 2021, there was one session devoted to impact of quantum technologies on telecom networks. And in 2022, there was another session devoted to security of IoT and 5G in the context of quantum communications. So there were some learnings from there, and they are in our records, and probably when we start doing real normative work in TSDSI very soon, all these learnings will be very useful for us. And like the conclave we are having today, since yesterday, the last year conclave also, TSDSI partnered with TEC and CDOT for in the workshop, in the conclave. And the first formal work which happened in TSDSI on quantum was on a study of post-quantum cryptography for future 5G networks. So a report was published. The link is given here. And if you can go to the website, it is publicly available. So it gives different aspects of post-quantum cryptography. Initial study on that how this will impact and how what should be our approach for protection of 5G networks and applications by using post-quantum cryptography. And when this report was done, a liaison statement was sent to TEC, informing them that this is the work we have done. And currently there is another item of study in our study groups, which is called Location Privacy Preserving Scheme to mitigate the authentication relay attack under false base station 5G, a quantum approach. So this item has just begun. We will know its more details when more contributions start coming from our members. Now, this is a information to all that how we have prepared ourselves in TSDSI for taking up work on quantum communications in a bigger way, is that we created a TRIP forum. TRIP forum is actually a discussion forum, and its full form is may not be directly relatable, but because it works under the roadmap committee of TSDSI, so this is called Technology Roadmap Item Proposal. That means an item which is not mature enough to take initial study work, or we don't have enough information. So we have a discussion forum which is called TRIP forum, and here membership can be from TSDSI members and non-members. So that TRIP forum has been working for last more than 1.5 years, and in this audience we have members. On this dais we have members from TEC and CDAC. Dr. Anindita is also a member of this TRIP forum. So we have very good ideas, excellent ideas, which is now leading to a white paper which is expected to be released next month. Idea was to study what are the different silos. The work is happening in different silos, bring them together, identify the gaps which are in the current standards or current studies which are happening, where are the gaps, what should be done. And all those are being compiled into one report, and recommendations are being framed that how do we proceed further in this area. So opportunities for standardization, and what we have seen in the last 1 day and 1.5 days of discussion is that there are lots of areas where still understanding is to be developed, standards are to be created, or products are to be created. So it's more or less it's a green field area, and there is an opportunity for us. And the TRIP forum report is discussing on various items, and some of the items which are up for doing standards work or doing for further technical studies, they are listed here. They're just one example. There are many more which are based on the new technology requirements or emerging use case requirements, or where there are gaps in the existing standards. There are so many standards which Mr. Vinod Kumar explained, study group 11, 13 and 17, what they are doing in ITU. But apart from that, there are lots of work to be done in different areas, and these are all open for doing studies and by pooling in knowledge from all the participants or the people who are experts in this area. Now suddenly why I have brought this is that when we want to say that we want to do work on standardization, how do we go to gather together, where, what we do? So this engine what we shown here, if you see, there is one government cycle, one is industry, then academia, then R&D organizations, innovation hubs. There are so many contributors to the same idea or the same ecosystem, but where do they meet? So TSDSI in between is a platform. If they is joined by all the people who want to actually share their knowledge and see where to go and get a direction and collaborate. So TSDSI is a platform where everybody can come, share the ideas, see what is to be done, and then create standards and studies. And of course, STO, this is, again I will say that TSDSI is actually supplementary and complementary to TEC work. It will be an SDO, and standard setting will be done by TEC. So the discussions in TEC in the NWG is one place. Here in TSDSI, what is expected is a research-based inputs to create specifications for a technology. And TEC will be the standard setting organization, that what comes out as a standard or a specification from TSDSI goes into TEC's consideration. And they have a process, it may be NWG, it may be another process which they have put in place. I will not go into detail of that. So this engine of standards, how it works, is basically it shows that it requires collaboration. If there is no platform for bringing people together, then people will work in silos. So this TSDSI removes the silos, everybody can come together, we can do even pre-standards activity. TRIP forum is a pre-standards activity actually. So what is the way forward? That as we already discussed, that is quite a greenfield area, quantum communications, and India can still take lead, because we are talking of a time frame of 2030s for quantum, something to happen in quantum really, realistically. So we can still have chance to take lead. Lots of countries will be trying, but we may have some of our niche areas or some important areas where we can create our own standards. They may take time to go to the international standards. Path is available, but then if we take lead, we can keep on modifying based on the feedbacks received from the market and keep our standards updated. But it gives a guide to the market that, okay, this is how things will require to be done. So, and for doing this, we require pooling of knowledge and efforts by collaboration of various stakeholders. TSDSI provides a platform, as we discussed. So now it is also important that while we aim at the leadership in the quantum standards, we should also influence the global standards. And global standards is the way we can harmonize the global standards, because the communications will happen across the national boundaries. So interoperability is very important. And interoperability is provided by standards. And it has to be globally harmonized. That is the best part. Only certain components which need not be essentially part of a standard, there may be implementation methodology difference, or options are available in different standards, but they ensure interoperability. They can still remain as national standards, but then global harmonization is very important. ITU has already taken up jobs, so we have to see where to contribute there. 3GPP is doing the mobile standards. They have not yet taken up anything on the telecommunication, on the quantum, but we hope that by the time they take up 6G work 3 years later, probably the quantum technology inputs will be available to 3GPP to provide a layer of security over the mobile communication. And harmonization, I talked about it. And I must emphasize that this is the right time for coming together of stakeholders to join TSDSI and to drive telecom standards. Because unless you have a telecom, you have a cooperation and collaboration, put together our minds in creating specifications, we will not be able to actually come out with something which is acceptable across the country and across the globe. So these are some links to our reports and standards and other aspects of TSDSI, people who want to go into detail. And this is our general email ID, secretary@tsdi.in. And for anybody who wants to become a member, of course we have lots of entities in the TRIP forum, even otherwise who are not there. They can join TSDSI by writing to this mail ID or to me. Thank you very much.
Thank you, Dr. Ajay Kumar Mittalji, Advisor TSDSI. Any questions? Yeah, please.
Yeah, this Venkati again from IIT Madras, Protect Technology Foundation. Sir, we're just talking about standards. Are we also looking at standard essential patents? That's more important to us as a nation than getting into standardization activities. One. Second aspect is standardization activity mostly, when it comes to the Western nations, about solving optimization problems, right? So what we call as Jugaad is state of art. So how are we going to accommodate Jugaad technologies in case? State of art technologies in case. So shouldn't we also be looking at standardization as democratizing the technologies rather than optimization of technology solutions? Do you understand this thing, sir? Two aspects, why standards, why also not standard essential patents?
Can I take this? Yeah, so it's a good question, but let us see what is standard essential patent. The first word there is standard. So they become standard essential. Any patent becomes a standard essential patent. The first requirement is it should become part of the standard. And the meaning of standard essential patent is it has the best chance to get monetized, because if somebody goes to implement that standard, it needs to use that patent to implement that whatever product they are making. So that is where the patent holder and the user, they get into a dialogue for enter into a contract for payment, how much royalty or whatever name you call it, you get it. So SEP, any patent does not have cannot get a designation of SEP unless it becomes a part of the standard. So that is why standardization is very important. Number two is what you say is the jugaad technology or jugaad solution. Yes, you have to bring it to the standards body and see that how you can get it into the standards, because when it's a collaborative effort, there will be alternative solutions available from multiple parties. And what standards body do is that it is debated and the best solution which is voted inside the study group goes into the standard. I hope I have been able to somewhat satisfy you.
It's not about my satisfaction, sir, but we can take this discussion later. Thank you.
Sir, this is Arun Agrawal from Department of Telecom. I have a comment because right now in the quantum communication, we are in the standardization phase, the technology is taking shape. So now we have seen that in the 6G, there was an element of sustainability that has been now embedded in the 6G vision document IoT 2030. Now, because now the standards are being set, so this is my view that the element of sustainability or the sustainable development should also be embedded in the standards as IQ has already adopted. And now the government of India has got very strong emphasis on this view on circular economy in telecom also. Our Department of Telecom through TEC is working on it. So this element of sustainability should be introduced because 80% of such sustainability is at the design stage itself. So I think now it is the right stage, right step to see that the standard should contain the element of sustainability and circular economy embedded in them. Thank you.
Sir, I second that, sir. Whatever you just said, this is when we talk about this, there are specific sustainable development goals that we need to address to. So when you're talking about standardization, any of these quantum approaches that we are talking, we need to see how much of them are really energy efficient per se, and what is their energy footprint per se. Okay, so that's very important. I don't know how many of us are actually, any groups are they're actually looking into it. Energy is not a free thing that is given to us, sir. Let's be very this thing about it. If anyone is interested, I could just come and talk to them about this specific aspect.
Sir, I'm P.K. Panda, Director from TEC. My question is to Madam Dr. Anindita ma'am. She was being just given a lecture on this National Testing and Standardization Organization. TEC being the standard setting body in the communication area. So where you are going to place TEC in your this organization?
I think it's a collaborative work, sir, and a test center of what we just together envisaged in the presentation I had given, definitely TEC will be a part of it. And there has to be a proper brainstorming done on how the activities, the roles and responsibilities of different stakeholders, whether it be an SDOs, some other test labs, some R&D labs, they have to be discussed and mutually agreed with. So, yes, sir.
Just one. Regarding the observations on the circular economy and the sustainable development goal compliance, we know that study group 5 in IQT already deals with the circular economy. So while the quantum protocols and specifications are under finalization, I am sure within the IQT it will be taken care by study group 5. And if we have any doubt that it may not be, we can give a contribution to that effect so that it will be then taken.
Okay, thank you so much, ladies and gentlemen. And now we wrap up this session on standardization efforts towards quantum technologies. May I request Shri Ashok Kumar Jha, DDG RC2, TEC, to kindly felicitate our speakers. So, Shri Ashok Jha will first present a memento to Shri R.R. Mitterji. Mr. Jha will now present a memento to Shri Vinod Kumarji. May I request Shri Jha to kindly felicitate Dr. Anandita Banerjee by presenting a memento to her. And now Mr. Jha will felicitate Shri A.K. Mittalji by presenting a memento to him. Thank you, Shri Ashok Kumar Jha ji, and we thank all our speakers. Thank you so much for joining in. Thank you. And now, ladies and gentlemen, yes, of course, it's a lunch break, and we'll catch up around 2:30. Sorry, ma'am. Okay, yeah, 2:30. Yeah, 2:30 is fine because we have one more session to go, and after that we have a panel discussion also. So thank you for now. Thank you so much. Quantum Communication Conclave. So this conclave is basically, as you know, our two-day event. Yesterday, on 15th of February 2024, we started with this conclave, and today is our second and last day of this conclave. Before lunch, we had 2 sessions, and now we are going to have our 6th and last session of this conclave, Emerging Trends in Quantum Technologies. This session will basically focus on discussions we'll have on the roadmap for development of quantum computers, quantum chips, and the quantum random number generators. May I invite the speakers of this session? Dr. Venkat Subramaniam. I request you to please come onto the dais. Quantum Lead India, IBM. Ms. Megha Srivastava, Senior Scientist, Takwid Labs. Shri Manan Narang, CEO, Silico Fellow Quantum. And Dr. Gautam Paul, Head Cryptology and Security Research Unit, Indian Statistical Institute, Kolkata. We will be joined by online speakers also, but for now, let's begin with Dr. Venkat Subramaniam ji. Dr. Venkata Subramaniam, the IBM Quantum India lead, is a distinguished figure in the realms of artificial intelligence and quantum computing. His work includes leading contributions to 6 products and 34 patents, alongside authoring 150 papers that have amassed over 3,000 citations. Currently, he is dedicated to establishing quantum computing as a premier research area in India, aiming to drive the nation's prowess in cutting-edge technology. So we now request Dr. Venkat Subramaniam ji.
Hi, good afternoon. Thank you for having me here. So this is a quantum communications conference, but I'm here to talk about computing. So in the next 15 minutes, I'm going to give you an overview of where computing is today and where it's headed, what are the things that are happening. So we have entered what we are calling now the era of quantum utility. Okay, so at the end of this 15 minutes, you'll understand what is quantum utility, what are the applications that are being tackled, and what is the roadmap. Okay, so that's where we are, and so here we go. So what are quantum computers? Okay, most of you, I guess everybody here knows, but the very important thing to know is that today computing has branched. There are 2 types of computers available today. One is our classical computers, your mobile, your laptop, your supercomputers, and the second, an entirely new kind of computer is the quantum computer. Okay, so 2 different types of computers, and the premise is that quantum computing, which follows the laws of nature to represent data, can solve some of the tough problems of society, of science and technology. Okay, and that's what we are going to discuss today. What are those problems? Where are we with quantum computing? And where are we headed? So why quantum? So as we know, our classical computers are built using the basic information processing unit, which is a bit, zeros and ones. Okay, that's what our bits are on our computers, on our laptops, on our phones. The quantum computer is built using qubits, okay, zeros and ones, but where you can take multiple states until you observe it, right? So your quantum computer can be in all these multiple states, and this, you're using the paradigm of quantum mechanics to solve some of the problems, whether it is in simulation, search, optimization, machine learning, all of these, right? So you're trying to solve some of these problems by utilizing these facts about quantum mechanics in your quantum computer. So where are we today, right? What is the quantum state of play? So that graph that you see there is the qubits we talked about, right? So in 2016 we started with 5 qubits, and till 2022 or so we were still under 100 qubits. Okay, so that's where we were. And that is something which you can actually just simulate even using the 1981 IBM system. So that's where we were until 2021, 2022. Our systems, quantum systems, were so primitive that anything you could do with them, you could do much better with the 1981 IBM computer, classical computer. Okay. But what has changed now? Something has changed this year, well, end of last year, or middle of last year, something changed, and that's when we entered the era of utility. Okay, so that's what I'm going to talk about, where we took this leap, where otherwise we were going to follow this curve, and as you can see, for you to get to applications which solve real problems, you had to wait until 2038. Now there was a leap, and that's what I'm going to talk about, that disruptive change that happened last year. So now I'm going to define what is quantum utility. So quantum utility is a point where you're able to do high fidelity quantum computations which you can not do using classical simulators. Okay, so you've reached a point in your quantum computer where you cannot use classical simulation to replicate that. Okay, so that's what we achieved in 2023. In June there was a paper published, but before we go there, what is this? This is what this is, this graph that you see on the right hand side. It is showing what is the circuit width, basically how many qubits do you have. So we were able to use 127 qubits, 100 plus qubits, and a large circuit depth. Okay, a circuit depth which again crossed 100, and that enabled us to get into this point which we call utility, quantum utility, where you are able to use quantum computers to do things which classical simulators cannot do, right? And that's the point we reached, and that the purple box that you see on top is the region where you get quantum advantage. Okay, so we have reached very close to that point where we are now saying that using a quantum computer you can solve a problem, a real business problem, in a way that's much, much better, much faster than what you can solve using a classical computer. Okay. So have we reached that point? Till today we have not, but we have reached a point where we are able to show quantum utility. So the evidence of utility before fault tolerance. So as we all know, today we haven't reached fault tolerance with quantum computers, but even before we reach fault tolerance, what we are saying is we have reached a point where we can show utility. We can use these computers to now show things on actual problems which you could not show using quantum computers before. So I'll not go here, but what it is basically showing is that in that research paper which I showed you in the previous one, the Nature one, we are able to show that quantum circuits are able to simulate things, are able to demonstrate results which go beyond exact classical simulatability. Okay, and since that paper, multiple universities have used these 100 plus qubit machines to actually demonstrate utility scale experiments in the past 6 months, And these are in multiple areas like materials, physics. In these areas, people have now shown that using these utility scale 100 plus qubit systems, you're able to now show these experiments in these multiple areas which go beyond what you can do with classical computers. Now, so a lot of advancement has happened in the past 4 years. In the past 4 years, there has been 1,000 times improvement in terms of the number of qubits and the number of gates you can use to build a circuit. Okay, so what you see on the top left is something you could have done in 4 years back, and today what you do is 1,000 times more. So you can build much more powerful circuits, which means that you can solve much more complex problems, right? So we have now entered the era of quantum utility. So what is it? What is next? Okay, what is next? Where are we headed with all of this? So first of all, we want to, the goal here is now using these quantum circuits, we want to be able to run them faster on our quantum systems, and that's something, the systems today we'll just briefly talk about. So what we say is that, you will be able to run noise-free estimators on these quantum circuits much faster than you can do using classical hardware alone. And the second thing is, once you are able to run these large circuits, you are also now able to map these to real problems, okay? And so in terms of the system reliability, today quantum systems are available 24/7. They are reliable with 95+% uptime, and they are stable. The 2Q gate errors have gone so low now that you are able to use them on realistic applications. In addition to that, you have software development on top of that using Qiskit, which provides you several tools. In fact, the new Qiskit which got released just yesterday or something also enables you to build circuits. You can actually write what you want to build and it will generate code for you, right? So a lot of the advances, both in terms of hardware and software, have been happening. And what this has now enabled us to do is, we are now aiming for quantum advantage, by next year. Okay, so what that means is, you'll be able to solve real business problems in areas like optimization, materials and high performance computing, high energy physics, healthcare, life sciences, in multiple areas. We expect that very soon we will be able to solve real problems using quantum computers. Something which we could not do until recently is now possible. Okay, so what quantum computers have reached that level where they have now begun to breach what can be done with the best supercomputers which are available to us today. And these are being used in multiple applications, whether it is healthcare. So these are some examples, and a very interesting example with Boeing. If you know, rust or corrosion is one of the biggest problems when it comes to airlines, ships, oil rigs, all of these. And in this, how do you reduce corrosion? What kind of new materials can you come up with? A lot of this work is now happening. People are trying to use quantum computers to come up with new ways to solve some of these very compelling problems of both technology and science. These are other examples from finance. CERN is an example we all know about. For example, the Higgs boson. Finding that is one of, it's a big search problem that you have to solve. So there are now 37 quantum centers, and what I wanted to show you here is that there is one in India, which is IIT Madras, from the 37, where a lot of research and development and skilling work is going on in India. And that's one of the 37 quantum innovation and computation centers across the world. And already several research papers, several industry collaborations have happened out of this center in India. So I want to end here by saying that, you know, this map you see is of people using the quantum systems of IBM, okay. And what you will be seeing there is India, you know, is one of the power users. There is a huge talent pool available in India. You know, about 20 to 25% of the IBM systems get used from India. A lot of the students here are very good at programming and running these circuits. So there is a large talent pool available for us to solve some of these tough problems. And as I said, we've entered that utility scale and we are just about to touch quantum advantage. So this is the right time for this talent pool to actually begin solving some of the tough problems of science and technology. So thank you very much.
Thank you, Dr. Venkata Subramaniam. And now, ladies and gentlemen, we have Ms. Megha Srivastava. Dr. Megha Srivastava, working as a senior scientist, give me a minute, ma'am. Working as a senior scientist at TechBit Labs, Dr. Megha Srivastava holds a PhD in physics with specialization in ultra-fast and non-linear optics. She is working as a senior scientist in an Indian startup, TechBit Labs. Her works include development of giga-fast quantum random number generators for industrial applications. Yeah, ma'am, over to you, please.
Good afternoon to all the esteemed delegates. I am Dr. Megha Srivastava, working as a senior scientist at TechBit Labs. First and foremost, I would like to express my gratitude to TEC for providing me an opportunity to present here today. It's a pleasure to be back at this incredible conference once again. Last year, during the first IQCC, I was one among the attendees, soaking in all the knowledge and inspiration shared by experts across the world. But today, I stand before you for an entirely different role. But before delving into the details, I would like to give a brief introduction of what TechBit Labs is involved in different verticals. So, in this era of quantum transition, it is needless to say that safeguarding your data today is imperative to secure its integrity tomorrow. And this is what we do. We provide solutions that safeguard your data in the post-quantum era. Our solutions are secured by laws of physics, and they offer quantum resilience, cost effectiveness, and also the seamless integration with the existing technologies. So the field of quantum technologies, it spans a wide array of verticals ranging from quantum computing to materials to communication network, simulators, and post-quantum cryptography. Now, despite their diversity, they share a common requirement: the need of the random number generators. Now, the concept of the random number generators is quite straightforward. It is a device that generates a sequence of numbers or symbols that cannot be predicted with certainty. And it is well known that random number generators have a wide range of applications, scaling from cryptography to IoT devices, to simulations, numerical analysis, games, and lottery predictions. Traditionally, pseudo-random number generators have been the go-to choice for most of these applications because they offer advantages such as low cost, high generation rate, portability, and ease of implementation. However, they have a severe disadvantage of being deterministic, and therefore, they are not a reliable option for having robust security, especially for having key generation for encryption protocols and also for the authentication among different nodes or users in a network. We need random number generators that are high performing and reliable. One way to achieve genuine randomness is to use truly random number generator, a device that harnesses the physical process or a phenomena that is inherently unpredictable. And this is used for generating the random data. Now, one way to ensure the true randomness is to use the quantum system as a source of randomness. And this has sparked a great interest in the quantum community to explore different ways to realize the quantum random number generators. Although these methods come with its own advantages, but they also have their own set of limitations, such as they involve integration complexity or the high rate, the limited generation rate, the high cost, or the challenging practical adoption. On the other hand, the quantum random number generator based on the vacuum noise offer clear advantages of high generation rate and being simple and low cost implementation. However, the quantum random number generator based on the vacuum fluctuation that is available in the market to the best of our knowledge is SAS based, and therefore clearly the indigenously developed product in this space is completely missing, and this has been the driving force for us to explore, to develop a product that will actually fill this crucial gap in the market. So today, here at the second IQCC, I am thrilled to announce that we'll be launching our latest product, GigaFast Quantum Random Number Generator, in June 2024. Let me now take you through the journey of the progress, innovation, and dedication. So it's just the last year when we planted a seed of idea of implementing an indigenously developed QRNG, which is cost-effective, compact, and provides high generation rate. And today we are here presenting a product that is not only reflecting our progress, but is also ready to set new standards in the industry. Our product is based on the vacuum fluctuations. Now, vacuum fluctuations in the quantum physics are vastly different from what it is described in the classical. In the classical physics, the vacuum is nothing but an empty space devoid of photons or matters. But in quantum mechanics, the vacuum fluctuations, the vacuum resembles a space that is a sea of virtual particles appearing and disappearing continuously. And consequently, the electromagnetic field of the vacuum exhibit random fluctuations in phase and amplitude at all the frequencies. We have utilized these vacuum fluctuations to realize the QRNG. Now let me take you through how it works. So this is the functional block diagram for the vacuum fluctuation based QRNG. It mainly comprises of three modules: optics, electronics, and post-processing. The optics module consists of the laser and the beam splitter. Beam splitter combines the coherent laser with the vacuum fluctuations and produces the two equal balanced output beams. Now these optical beams impinges on the photodetector and they generate the corresponding current. Now that we are saying that it is the balanced output beam, so we will be expecting the currents to be equal. These equal currents are fed to the subtractor, and we will be expecting that this resulting photocurrent difference will be 0. However, it is not 0. The photocurrent difference is proportional to the vacuum fluctuations. And by utilizing these, we have realized this quantum random number generator. Following this, we have carried out the simulations in ANSYS interconnect numerical to quantify the quantum noise, the amount of the quantum noise and the classical noise by measuring the power spectral density in presence and absence of the laser. And we observe that in the absence of the laser, the dominant signal is just the electronic noise. On the other hand, when we have a laser signal in place, then there is a clear signature that the total noise is 15 dB above the measured electronic noise. And this confirms the domination of the vacuum fluctuations in the total noise spectra. Following the simulation, we have validated the concept of VFQRNG in the lab by implementing it practically. And following this, we have made multiple lab trials and optimization. And ultimately, we are here with a product that is commercially viable, having gigafast speed, is compact, and is easily integrable into the existing technologies. One other key feature of our product is the software suite that it offers for the diverse applications. The software suite offers the features such as different data formats and then user-defined block length and array size, the random number acquisition up to 1 Gbps, and also there is an option to carry out the NIST test suite on the data acquired or the user input file, and it also provides the compatibility with the external applications. With these features, we believe that our product will bring in significant strides in different sectors such as defense, government, finance and banking, cybersecurity, IoT, data center, telecom, industries, and healthcare. So this is all from my side today. Thank you so much for your listening.
Thank you, ma'am, Dr. Megha Srivastava for speaking on emerging trends in quantum technologies. I was told to request my speakers to please adhere to the time limit given. But fortunately, this time I'm not even saying, and thankfully you all are going by that. Thank you for that. Next, we have Sri Manan Naranji. He is an electronics engineer from the Vellore Institute of Technology and also an IBM certified Qiskit developer. He is the CEO of Silico Feller Quantum, working on the quantum processing unit or quantum chip. Sri Manan Naranji.
Hello. Yeah. So hi everyone. Thank you so much first of all to TEC for giving me this opportunity. Pawan sir, thanks so much, and all the panelists that are present here today. So it's with great honor that I would like to present to you about our developments and most importantly the quantum chips. So before going ahead, I just want to give you a brief background about why we started developing quantum chips. So a few years back, I envisioned that very soon, since there's a chip shortage that was happening at that time, so I thought that maybe sometime soon there's going to be a quantum boom, and in that quantum boom there'll be thousands and thousands of quantum computers, right? And so there'll be a shortage of quantum chips maybe. So with that in mind, I thought that okay, let's just start working on developing quantum chips and how we can make them in India or make them anywhere, but just develop quantum chips. So that's why we started Silico Feller. So Silico stands for silicon, and Feller stands for John D. Rockefeller, who was a pioneer in the oil industry. So similarly, we wanted to become the pioneers of quantum chip industry, but when we say pioneers, it means that somebody who's already doing it, and there are companies that are already doing it. So we just wanted to do something new and something innovative in India. So that's how we actually started out. So I'll start by telling you more about the first quantum revolution, right? So when we say that quantum is something new, it's not new. It's already been there, and in fact, we are living in a quantum world. It's not a classical world. We all are living in a quantum world, and I just want you to think of, we've been seeing the world in a classical sense, so we're all accustomed to it. But let me give you an honest example. If we are seeing the world with a blue color lens, we're going to see the world blue. But if we see the world from a red color lens, we're going to see the world red. So it's all about the perception, right? So I just want you all to think that it's a quantum world that we're living in, and even the phones that we are using, right, they have the transistors. They are also part of the first quantum revolution. And in fact, MRIs, lasers, GPS, they are all quantum, right? They all have some quantum nature in it, and that is how the first quantum revolution actually began. So the second quantum revolution is being led by quantum computers, right? And quantum computers is it's like the most powerful technology in the history of mankind. If you look at any single industry, the fastest growing industry has always been technology, right? And in that we have a computer that can calculate something that would take normal computers 10,000 years to do. So you can imagine how every single industry is going to get revolutionized, be it healthcare, be it automotive, be it finance. There's a revolution that is about to come that we haven't even thought of yet, and the world is about to change in unimaginable ways. So how does the stack of a quantum computer actually looks like? So these are some of the areas that that if you look at the stack, how the stack looks like, and we have tried to come in at the bottom and the top. So where we have started developing applications in quantum computing, and then at the bottom of the stack we are working on hardware design, as I told you about the quantum chips. So in between there are tests and measurements, then we have system integration, how do we build a quantum computer, then apart from that there's error correction and a whole lot of stuff that actually goes on when we are building quantum computers. So what actually can we solve with quantum computers? What are the problems that we can solve? So if you look at the three circles over there, so we need to hit at in the middle of that, where we need to find a useful problem, and we need to have no fast classical algorithm for it, and we know that there's a fast quantum algorithm. So right in the center we'll be finding the useful quantum applications, and so we can improve the polynomial improvement if we so these are some numbers. I'm not going to get deeper into the numbers over here, but I just want to give you a sense of how actually we can solve quantum problems and what kind of problems, as Venkat sir also discussed regarding the NP-hard problems and other kind of problems. So this is where we are looking to solve some of the problems. And the solution for solving these problems, as I said, has been quantum computers. So that is why we are here today. And I'll come about our product now, about Kohinoor. So we have made India's first 4-qubit commercially available quantum chip, which is actually here displayed at our booth. So if anybody is interested to learn more about it, they can come at our booth and I can show you all about the quantum chip. So it was launched by the Ministry of Electronics. Secretary had launched it at the National Quantum Symposium along with Dr. V.K. Saraswat. So it's just a small step towards going to thousands of qubits. So I'll tell you more about our roadmap and what exactly are we trying to do over here. But before that, let me take you into the components of a quantum chip, what actually makes a quantum chip, right? So there are a whole bunch of different parameters that are there that we need to, while we are designing quantum chips. So fabrication is different, designing is different. So there are, you can see it as an LC oscillator, and every single qubit is an artificial atom that we are creating. So we've reached a point where we can now create artificial atoms, and every single qubit is like an LC oscillator, I said. So we're just restraining it to zeros and ones. That is all that we're doing, and that is done in the block sphere. Yeah, so you can see that we send signals from the classical computer to the quantum computer. Then we have this cryogenic environment, which is called the dilution refrigerator, which is operating at ultra low millikelvin, highly cooled temperatures. So it is colder than outer space. Then we have the quantum processing unit, which is housed inside the cryogenic environment, which is called the QPU. And then we have the design of the chip, which is the physical layout. And while designing the chip, we have to do electromagnetic analysis, HFS, using HFSS, all those APR analysis, everything happens. And then quantum Hamiltonian analysis happens. And then we come to the qubit Hilbert space. So that is the final thing that in the whole picture. So this is the process flow, how we go from an actual chip design to the delivery. So first step is designing the chip, then next step is simulating the chip on actual normal computers, classical computers, then fabrication and then testing, and after that we deliver it. So what actually makes a chip better, right? There are multiple chips out there. So how do we figure out that, okay, this chip is better than the other chip? So there are three things that we need to consider. So the first one is scale, which is the number of qubits that are there inside the chip. Then comes the quality of the chip, like how good is the chip and how many circuits can it run, what is the size of the circuit that it can run. And then the speed, like how fast am I able to calculate on that chip. So with these three parameters, we benchmark the chips and figure out, okay, this chip is better than this chip. So first I'm going to talk about quantum volume, right? So I spoke about quality over here. So the scale is just a number. We can say, okay, we have X number of qubits. Then how do we determine the quality? So the quality is determined by quantum volume. And quantum volume is the largest square circuit of a random 2-qubit gate that a processor can successfully run. So what do I mean with that is, let's say we have 8 qubits, right? And the circuit depth is also 8. So it's a square. We can consider it like a square. So how many times can can we actually increase the number of qubits? Let's say we go to 9 qubit and then we increase the depth to 9 before the circuit starts to give us errors, right? So let's say if we start from 1, we go to 2, so circuit with 2 depth and the number of qubits 2, then we go all the way up till 8, let's say, and we reach that, okay, we see that now we are getting the error, so we have a quantum volume of 2 raised to the power 8, which is 256. So these are some of the parameters that are there when we are considering the quality of the chip. Then next step is the CLOPS, right? Now what is CLOPS? CLOPS is circuit layer operations per second, and that is how many times can we run this quantum volume circuit and in X amount of time, let's say 100 seconds or 10 seconds. So that is how fast we've determined that. This is the parameter that helps us determine that how fast is our chip. So this is when it comes to the CLOPS, right? Now when we are designing the chips and building the chips, what are the key challenges that we face, right? So the first challenge is extending the coherence time of the chip. Then the error correction is there. Then how can we achieve high fidelity, faster gate speeds, and how can we increase the number of qubits? Can we put some qubits on one layer? Can we put the readout on the other layer? So all these things we need to consider while developing the chip, and as also the materials, like which material are we using. So this is the deployment strategy, okay? So right now we have made 4 qubits, the world is at 1000 qubits, but the goal is ultimately 10 lakh qubits, right? So if you think that the race is still not open, if we got the winner, so it's not like that, right? Anybody can come in with a new approach and try to figure out how we can reach to 10 lakh qubits. Some people are doing it with superconducting, some are doing it with a different approach, let's say photonic qubits, ion trapped, right? So the ultimate goal is how can we get to 10 lakh qubits, right? So what we think is that if we can connect 1000 qubit processor with 1000 qubits, so that is how we can envision, like in the next 10-15 years, this is probably what's going to happen, that quantum computers will be connected with each other, right? And there's going to be a certain amount of number of qubits that we can accommodate on a chip, right? We cannot go farther than that. That is, then we'll have to connect those qubits together. So this is our roadmap. So right now we are looking to build a 27 qubit quantum chip. That is what we are doing currently. And then next year we plan on to scaling it to 127 qubits. So we don't want to build the hardware. We don't want to build quantum computers. We just want to build the chips. That is what our aim is, right? And then if somebody is building quantum computers, well and good, we can replace those quantum computers with our chips. So that is a cost-effective way of upgrading the existing quantum computers and making it cost-effective in the process. So that's all for the chip side, right? Now I would like to also tell you more about what else we are doing. I'll just take hardly a couple of minutes more and then I'll wind up. So, and if anybody over here wants to learn quantum computing, right, I know some of you might be just starting out or some of you might be experts, but still if anybody wants to learn quantum computing, we are also teaching quantum computing. We have our mobile application using which you can start learning quantum computing. So I would suggest you all to go ahead and download the mobile application if you guys are taking out your phone. So I'll just put out the scanner in just a minute, so you can scan and download the application. So these are some of our success stories. We've trained people at GIT University, then Sharda, and then we've also signed an MOU with VIT University where we are trying to co-develop a quantum computer. So that is one exciting achievement that I would like to share with you all. And then this is the link to the application, so if you can just sign up and show your interest, that would be great, and I would be happy to entertain you at our booth. So Silico Fellow, the booth, I think it's booth number 9 or 8, so you can come over there. So with that, I would like to thank DSCI and NCOE for giving us, for incubating us and supporting us, and also the Government of India for hosting this. Thank you so much, everyone.
Sir, I have one question. Can you elaborate on qubit Hilbert space and quantum Hamiltonian analysis?
I'm sorry, because we have our guest lined up from France, so let's finish with that. Yeah, definitely. I mean, in the end, we'll have this open forum. I mean, this question answer this thing. But for now, let me just connect with our next speaker, Dr. Olivier Nora, because he's joining from France. And to tell you about Dr. Olivier Nora, he's devoted his He has devoted his career to client focused innovation and new offer development. In his prior roles, he led several team mergers, restructurings, as well as large complex international deals. Oliver joined IDEMIA as Senior Vice President in charge of products and systems for the financial institutions business unit. In particular, all the payment cards business lines. Dr. Nora now leads open innovation activities in IDEMIA, driving emerging tech development collaboration with industry partners, in fact. So we welcome Dr. Olivia Nora. Welcome to the session, sir.
As the presentation I will do you is focusing, in fact, on something which is often overlooked in terms of quantum threat, which is the edge computing. You all know that the quantum computer is going to pose a serious problem to all cybersecurity solutions. And today, the industry worldwide is working on data center solutions, cloud-to-cloud communication, and things like that. However, there is one part which is currently yet a bit overlooked, which is the edge, and in particular, what will happen to all the critical devices on the field that are critical for national security. And this is what I'm going to present to you today. Let me first remind you something that you all know, so I will not explain too much. You all know that the quantum computer is able to break some cryptography with two types of cryptography. The symmetric one, which in fact is safe, it's just an acceleration. The main topic of my speech will be around asymmetric cryptography, so RSA, elliptic curve, or Diffie-Hofmann, which actually are solved by quantum computers, so there is no way but to change the cryptography behind it in order to find a new asymmetric cryptography which will be able to resist against quantum computer. We call that post-quantum cryptography. And the goal of this presentation is to understand what it means for critical devices such as smart meters, automotive or industrial control systems, and how can we prepare for the risk that the quantum computer will pose for these devices. But first, a little bit of timing, because it's important. A lot of people are asking when will quantum computer be ready in order to break that cryptography. You have here the presentation from the Global Risk Institute. They do it every year. And in a nutshell, what they say is nobody really knows when quantum computer will have enough qubit and stability to break current cryptography. However, 50% of the experts think that there is maybe one chance out of two that in 2030-2035, the quantum computer will be able to solve elliptic curve problems or RSA problems. Now, the real question is not when the quantum computer will come. The real question is, do we want to run the risk, even 10% chance, that with a single quantum computer, somebody can organize a complete blackout of a country? So the question is not really when will quantum computer be there, but how do we prepare to migrate before 2030-2035 critical devices that are all over the place on the field, like smart meters, like automotive. And so there is an urgency, which today is still a little bit understated on the market, to understand how to build quantum-ready devices that will be able to migrate in 2030-2035 on the field, when our experience today, we have tried with several devices, is that most currently deployed devices will not be able to migrate with software update for CPU, memory, or hardware reasons, but also because they were not designed to change the heart of their cryptography. What is the risk for critical connected devices? In fact, the main risk is to have a deployment of large-scale quantum attack possibilities. In particular, to use what the NIST call remote authentication vulnerabilities, which is, I'm getting a public certificate, with one single transaction on a quantum computer, I can retrieve a private key. And then with that private key, I can compromise the secure boot of the system, I can compromise the software update, I can compromise the access management. In fact, I can do pretty much what I want with this system. I can order an automotive to stop or to speed up. I can order a smart meter to shut off. There is another vulnerability, which is data copy, catch and exploit. Most focused on healthcare personal information and confidential process information. However, the most dangerous for national security is the remote authentication. And just for you to understand how easy it is, you don't need to own a quantum computer. You need to have one access to any SAS quantum computer to retrieve the right private key, and then with that private key, you use classic attack. You have the key to enter in any device on the field. There is a specificity for connected devices, which is that they have resource constraints, performance requirements. They are highly optimized. And most of the connected devices we are working don't have enough memory to handle new algorithms with much larger keys. They don't have the bandwidth, the communication bandwidth to do more exchanges, which is required for post-quantum cryptography. And most importantly, they rely on their own cryptography, which has been locked in order to make sure that nobody can change it, because at the heart of the security. And so you have to design something which is crypto-agile, so where you can remotely and securely change the cryptography at the heart of the connected device. How can we do that? There is one opportunity that I will present now, which is on all these devices, you have two solutions. Either you can redesign the device to implement the new post-quantum cryptography, but remember, we have to be ready for 2030, and in fact, we have to be ready as fast as possible. Otherwise, we will have to replace the equipment on the field. The other possibility is in most of these equipments, at least those connected to mobile network, you have a secure element, which is a SIM or an eSIM, which is largely unused. It's just used for connectivity. However, this secure element can be a crypto-agile, quantum-safe root of trust. So by upgrading just this single secure element, there is a possibility to rapidly achieve quantum protection on equipment on the field and leave in time for long-term exchanges. But let me first highlight one specificity of the post-quantum algorithm, which is that they are very safe. In fact, we are coming from a world of security where everybody knows implementation of RSA or encryptor, and it's been known for 20, 30 years. They are stable, there is no vulnerability yet known. We know all the attacks possible, all the countermeasures. The new algorithms have never been deployed on the field. They have been selected in the past 10 years, they are quite young. And when we look back at the first implementation of RSA in the 1970s, we see that there were patches approximately on a monthly basis, and 4 major redesigns in the first 10 years. So there will be vulnerabilities discovered for 10 to 15 years in these algorithms. There is also the risk that somebody solved an algorithm. Some of them, for example, Bach, has been solved by a mathematical PhD that has found a solution to solve it on a PC. And last, the standards which are currently being developed will be evolving. So not only we are going from a world where we know the algorithm to where they are very young, but it also means that open source algorithm, which everybody is using, might reveal 0 days in them. So there might be vulnerabilities that nobody knows and that could be exploited by the one who finds it. So crypto agility becomes critical for security in this quantum safe world, which means that you need to be able to update algorithms in a timely basis on the field. I will give just a single example of what it means. Corporate badges or government badges. It means you need to be able to update the algorithm in all corporate or government badges in a timely basis if there is a vulnerability found in the algorithm implemented in this badge. This is just brand new. Nobody has ever done it. And you need to be able to update that for physical credential, but you need also to change the credential reissue. And in the extreme event where somebody finds a mathematical solution, let's say for lattice, which is the algorithm that are currently standardized as a list, you need to be able to rapidly change the type of algorithm in all devices in order to avoid a malicious person to exploit it with a mass attack. What critical device are we working on? Electricity smart meters, with the risk of blackout, with the risk of load balancing at a nationwide level. Speaking about automotive, electric vehicle, automotive, connected automotive, autonomous vehicle. We're speaking about connected factory, entering into a refinery, entering into a chemical plant. These are use cases where people could easily do, which are at the heart of national security. For the sake of this presentation, I will just take one example, which is electricity smart meters. The other ones are very similar. If I look at an electricity smart meter, this is one of the two architecture possible. So here we're using smart meters that are connected through BPL, broadband power line connection, to a concentrator that is then connected to the network through mobile network. What we've seen on smart meters is that although the symmetric cryptography is secure, provided that we shift to AES-256, there is a very high risk on the secure boot, on the authentication, on the firmware software update, on the communication protection. All these are using asymmetric cryptography. All these can be easily compromised with a quantum computer, which means that an attacker with a single transaction on a quantum computer can take control of concentrator, can insert new authenticated devices on the BPL, can stop power in a house, can take over the identity of field technician and enter as a field technician on the equipment, can change the index, can modify the load balancing of the network, can neutralize any equipment remotely. How do we protect against that? In fact, we believe there are two steps. The first one, we believe the first attacks will come from remote. There will be unsophisticated attacks. They will use a quantum computer, but they will first attack directly remotely. And so the short-term issue is to design equipment that will be able to be protected from quantum computer from mass remote attack. Today, the standards are not yet set. So the question is, how can you design an equipment that is quantum safe when the protocols and the design are not set? That's where cryptoagility comes into play. We know that even when the standards will be set, they will change. So in fact, the key functionality to do is to implement a device which is able to migrate to post-quantum cryptography. So we do proof of concept to show that we can implement the current version and the standardization of post-quantum cryptography, and that is crypto-agile, so that when the standards are finally set, the equipment will be able to migrate to these standards. The goal is to have, as soon as possible, an equipment which will be able to migrate, which is not the case with current equipment. And then there is another activity, which is to set up the management tools in order to manage the crypto agility. These tools in the back office do not exist today. We actually use the GSMA, OTA, and management tools to do that, to make them evolve in order to be able to manage crypto agility. Because these were tools that are designed to handle root of trust, distant root of trust, billions of objects, and are extremely proven in terms of functionality. And third activity is to prepare the migration project, to understand how the system will migrate between the new quantum safe equipment and the old one on the field that will not be able to migrate to quantum safe. One of the topics we are investigating as academia is really to leverage the eSIM and the GSMA, OTA, and SMDP, so all the GSMA remote management tools, in order to rapidly deploy crypto-agile quantum safe root of trust, which equipment can easily use. On the longer term, we have to protect from local attacks. These local attacks are more sophisticated. It can come either from local contact, local technician entering through the local access, or it can go from a spare part, so in the supply chain, so you change one of the smart meter with a malicious one, and then you infect, or it can also come from insertion or extraction from the local architecture. We believe these attacks will take a little bit more time, and in any case, modifying the architecture of the edge solution, it takes much longer than protecting from remote scale attacks. However, we are already working on such architecture because if it takes longer, it needs to be started in parallel with the first one. So what I have presented to you is really the need to focus on edge devices, critical devices. The ones, automotive, smart meter, industrial control systems are the most exposed and the most vulnerable and incapable today to migrate to quantum safe cryptography. And one of the goals of my presentation today is to urge you to invite people to start working on that, do proof of concepts. We do them worldwide with other clients. We have the full sandbox environment in order to mock up and to try to understand this migration. We do believe this is as critical in terms of urgency as working on the data center. I thank you very much for your patience and your listening.
Thank you so much, Dr. Olivia Nora, for your participation and for speaking on this topic. And now we have Dr. Gautam Paul with us. Dr. Gautam Paul did his MS from sunny Albany, USA, and PhD in cryptology from Indian Statistical Institute. Currently, Dr. Paul is serving as an associate professor and head in cryptology.
So, can you see? Did you see my presentation?
Currently, Dr. Paul is serving as an associate professor and head in cryptology and security research unit of Indian Statistical Institute, Kolkata. Dr. Paul has published more than 100 research articles and has completed supervision of more than 10 PhD students. So we now welcome Dr. Gautam Paul.
Okay. Good afternoon, everyone. I thank the organizers for inviting me here and welcome all the dignitaries on stage and in the audience. So the title of the talk is Quantum Random Number Generators. Megha has already talked a lot about it, and particularly the physics part of it. So I will focus on the computational view on random numbers. Okay. Next. Okay, so this is a roadmap. So after a brief introduction, we'll talk about Indian and foreign manufacturers. Then I will compare existing QRNGs according to some criteria, and then I'll conclude with some comments. Fine. So random numbers, she has already explained. It's a process to generate sequence of random numbers. And the difference between classical and quantum random numbers are that classicals are mostly software-based, though there are some hardware-based designs in classical. And quantum, it's based on quantum physical phenomena. Then classical versus quantum is deterministic versus non-deterministic, predictable versus unpredictable. And then classical is either high entropy or high throughput. You cannot get both at the same time in the long run, of course. So there is a caveat here that in principle you can generate classical RNG which will give you high entropy and high throughput for quite some time and enough time for practical applications, but not forever. On the other hand, quantum RNG will give you, forever high throughput as well as high entropy. So from computational point of view, there are some issues here which I will highlight towards the end of my talk. Fine. So I don't know whether it's visible, but I will try to explain the main components here. So this is a classification of QRNG, and this is taken from this 2022 survey paper. So broadly, they are classified in three aspects: semi-self-testing, trusted, and self-testing. So the difference between trusted and the other two is that in the trusted paradigm, you have the trust on all the devices. So your source device, your transmission device, your measurement device, everything is fully trusted, right? So that's kind of idealistic model. Then on semi-self-testing and self-testing, in both the paradigm, you don't have trust on the device. Now, depending on the trust level and to what extent you are having your trust, the classification is there. So for example, in source independent, you are actually not trusting the source. So there may be some kind of characterization problem in the source. You are not able to fully characterize the source, but in this case, your detection device or measurement device are fully trusted. On the other hand, when you talk about measurement device independent, then your measurement devices are not trusted, but your source is fully characterized. In the bounded dimension scenario, neither the source nor the measurement devices are trusted, but you have some assumption on the dimensions. So you have some bound on the dimensions, and there is a concept of dimension witness, which is used to generate and certify the randomness. Okay. Then in the self-test, okay, and semi-self-testing and self-testing, the difference is that in semi-self-testing, there is no entanglement that is used, whereas in the self-testing paradigm, the random numbers are generated based on entanglements. So there are two concepts here, randomness expansion and amplification. I mean, though it looks the same, for expansion, basically you need some kind of a seed. For amplification, strict requirement of seed is not necessary. So, these things I will cover in the comparisons anyway. So, the red circled ones here are the ones that are available in the market currently, and which are not circled, it's kind of open research still going on. So, as you can see here, under the trusted paradigm, non-optical and optical both are there, and then in the optical, you have these qubit, spatial and temporal. So, the difference is that spatial is determined by the spatial location of photon. So, you have a kind of a series of detectors, and you generate your randomness based on the coordinate of the photon detection, spatial coordinates. Temporal is based on the arrival time of photon, that is kind of most common. And when you talk about qubit generated randomness, that means the qubit is created with superposed state, superposed of the the basis states, and then you do measurement on different bases and generate several states. Okay. So let's see that. So Indian manufacturers currently two devices are available, which is one is from QNew Lab. Their device name is Tropos, and this is available in cloud mode also in the name Cosmos. So that's a TRL level 9, and they have 3 randomness test suite they have passed. Speed is claimed to be 100 Mbps based on photon arrival time. Security is trusted, and the cost is given. This is approximate cost definitely, which may be updated from time to time. Then there is another one from DRDO Young Scientist Laboratory. So they also have passed all the tests, as well as there is a DRDO's indigenous test suite, Mulyankan. It has passed that also. However, the speed is less. It is 1 Mbps. But recently I was talking to the director of this lab. So they are kind of working on a scheme. With the next release, they are targeting towards the GBPS generation. Okay, so there the technology is based on path splitter, and the cost is high. So they are working on reducing the cost as well. Then there are some works which are not yet fully commercialized, like proposals from academics, from Natarajan, then Pathak, Chandrasekhar, Urvashi ma'am, Dr. Pradeep Kumar, and Professor Samanta from PRL Ahmedabad. Okay, and these manufacturers are there because I have not listed them in the table: Skytel, TQBit, QTS Lab, and CDAC, because not enough information is available in public domain, but hopefully they will be updated in this one. And we have some update here also from Mega. So the next version that will be included. Fine. So foreign manufacturers, there are a lot in the market. Particularly the first two are important. I mean, they are more prominent. Quintessence Lab Australia and ID Quantic from Switzerland. So I got a chance to work on the analysis of their QRNG devices to some extent. And as you can see that according to the speed, the Australian design is the highest. This is 1024 Mbps. Their technology is based on quantum tunneling, and ID Quanting is actually based on short noise of the light source. Then we have some companies in Spain, in US, and Canada, Germany, China as well. Okay. So some comparison based on used technology. So basically, all the designs that you have seen in the previous two slides, they are now classified according to technology. So photon arrival time, phase fluctuation, so you can go through the table. I'm sure the slide will be available. So I'm not reading it out. I will highlight some of the issues as and when it comes. So So comparison based on statistical tests and security. So basically you see that there are some designs which have actually passed all the tests, but that is not a guarantee that you can classify them as quantum, which I will come to the end of my talk. And security wise also, so this TSF is kind of a paradigm generated by the Quintessence Lab, Australia. This is called Trusted Security Foundation. So under that paradigm, the security is evaluated. So it is not absolute, obviously. Next, comparison based on applications. So here different applications are written. So applications in secret key, in authentication, signature, as a seed of some other generator, IoT, VPN, simulations, noise, sampling, scheduling, financial transaction, POS, OTP, blockchain, risk, market, lottery, satellite, vehicle, AI, ML, etc. So you see that the green bars actually indicate which random number device on the left cover which applications, right? So you see that some of the devices have a wide, wide area, so not too much applications are covered over there. Okay, fine. So in summary, most of the available devices are optical in the market. High speed 2 Gbps is achieved by Australian design, Quintessence Lab, and that's based on vacuum fluctuation, and they also have a cloud-based service. Then among physical device, there is another, okay, so the Quintessence Lab also has the high speed in physical device as well, like the cloud one. Several Indian companies and government bodies are also working, and devices are available in USB, PCI, chip, appliance, etc. Fine. So now there are some interesting issues that I would like to cover. So in QRNG, normally we say that no initial randomness is required, but as far as the randomness theory goes, you cannot generate randomness out of nothing. So you need randomness to generate randomness. Okay. Without randomness, you cannot create randomness. So classically, that initial randomness is provided by the seed of the random number generator. Now, in the quantum domain, that initial randomness is provided by nature. So either you are banking on some kind of a noise in the circuit, in the vacuum, wherever, in the device, right? Thermal noise, any kind of noise. So initial randomness is there, it is implicit. Okay. Second point is that we often take it for granted that just because a random number generator is quantum, it is more secure. It is not that. The reason being, most of the applications that require random numbers, they require uniformly distributed random numbers. Okay. Now, whenever you are generating random numbers from quantum device, the output, the raw data may not be uniform. In fact, in most of the cases it is not, because even if your scheme theoretically guarantees uniform random numbers, it will be associated with some sort of noise, classical noise, quantum noise, measurement noise, and lots of things. So you have to do some post-processing. Now, suppose you have a pseudo-random number generator classically, right, which has good output in terms of randomness evaluation, and you have QRNG. After post-processing, the QRNG may pass all the statistical test suite, but it may be slightly more biased than a good PRNG. So in that case, it is not at all secure. Okay? So again, security is an assumption over there. Now, regarding distinguishability from classical, there is an issue here. So first of all, if you assume a black box model, that means you are given only the output sequences and you are not told about the schematic or the design or how the random numbers are generated, then just from the output, there is no way you can tell the difference between a classical random numbers and quantum random numbers. There are no statistical tests or mathematical tests possible. On the other hand, if you have access to the device, then possibly you can tell by kind of evaluating the design, how it generates, and tapping the intermediate output points. Okay? So that's one important point that we should remember. Okay. Then with respect to the stream encryption, QRNG is an essential component, so not QRNG, any random number generator, whether classical or quantum, is an essential component of stream cipher or stream encryption. And you know, the stream encryption goes back I think more than 100 years during the time of Varnum, which was the idea of one-time pad. So you have the message bits, key bits, then you XOR them, you get the cipher text. It's because of, you know, Shannon's celebrated theorem that independent of the distribution of the message, your message may be fully non-uniform. Your message bits can be all 1, all 0, doesn't matter. But if your key bits are uniformly distributed, then your cipher text is also uniformly distributed. So all that is fine. Now, traditionally, what you do that you cannot generate the key stream as long as the message. The requirement is that this key stream ki should be as long as the message, because for every message bit you need a key bit, right? And if you do that, either using a classical random number generator or a quantum random number generator, it doesn't matter. In either way, if you try to generate you know, your key bit as long as the message bit, then it actually defies the purpose of communication. Because you know, if you could actually transmit that key, right, which is as long as the message, then by the same technology you could transmit the message as well. Why you transmit the key as long as the message, right? So that is the necessity of a random number generator with a seed, and the seed may be classical or quantum. So that's one point of view. Another point of view is that you know, stream ciphers, there are some stream ciphers designs which are actually secure against quantum attacks. I mean, the only quantum attack that is possible on them is the Grover search. So just by doubling the key size, you can get all the security that a post-quantum design has. So you don't have to go for lattice-based or hash-based design or elliptic, you know, hyperelliptic curve-based design. You can get the same level of security without depending on any hardness assumption that is susceptible to quantum attacks, okay, either period finding or factoring algorithms. So stream ciphers are not listed as you know, post-quantum crypto system, but they are secure provided you maintain the key length, right? So we may need to think about this in the post-quantum scenario, how to intelligently use stream ciphers, because one advantage of stream cipher over the PQC designs are that stream ciphers are extremely fast. So they are very natural choice for real-time designs, okay, when the response is immediately needed. When you have to encrypt on the fly, you have a streaming data and you can't store them. You have to encrypt on the fly and pass on to the you know, next device in the communication. So that's one aspect I wanted to highlight. Okay, so this is our research related to QRNG and related fields, so which ranges from QKD-based quantum cryptography as well as non-QKD-based quantum cryptography, because you know, the moment we say quantum cryptography, everybody assumes it's QKD, but you know, there are other paradigms. So for example, quantum private query is an interesting applications of, you know, randomness, where there is a you know, server, database server, and there is a client. So the requirement is that the client will have some query, but the server will not know what is the query of the client. Okay, so the server will not know which data the client is accessing. It will serve the data to the client, but without knowing which data it is serving to the client. And also client, the requirement is that client will not get any additional information than the specified query. So it's kind of both-sided, there is a privacy preserving thing, and it turns out that all the classical designs are susceptible to some form of weaknesses, but using quantum, we can actually get rid of that by, you know, some sort of randomization of the, you know, client query indices and randomization of the server's output, okay. So that's quantum private query, that's just for an example. Then quantum secure direct communication is another example where actually you can securely transmit your message by encoding it as a quantum state from the source to the receiver without requiring any key or any key distribution. So just like in QKD, you transmit a classical bit string from the sender to the receiver, or you establish a common bit string. Here also you can do that along with the message. Now the only difference is that in QKD, you don't have any control of what the final key bits are going to be. The final key bits are random. That cannot be pre-decided by the sender, right? Whereas in quantum secure direct communication, you have to ensure that whatever message the sender has decided to transmit to the receiver, that has to go as it is, without any change. So that is the challenge with respect to the QKD. But it is possible in principle, both using entanglement as well as without entanglement. Okay, and there are some other works which I am not going over here in details. And that's the end of my talk. And thank you for attention.
Thank you, Dr. Gautam Paul. And now we have, ladies and gentlemen, our next speaker connecting from Switzerland, Dr. Bruno Huttner. Dr. Bruno Huttner is the Director of Strategic Quantum Initiatives and a quantum key distribution expert at IDE QuantiQ. He's also the co-chairman of the Quantum Safe Security Working Group organized by the Cloud Security Alliance. Dr. Bruno joined IDE QuantiQ in 2014, participating in business development and product management in the Quantum Security Division, which develops next-generation encryption and especially quantum key distribution systems. So, Dr. Bruno Huttner, we welcome you in this session.
Thank you. Let me share my screen. Window. I think. So if you see, can you see my screen, I think? Yes, okay, so that's good. Thank you very much for the invitation. I'm happy to be with you remotely this year. As some of you may remember, I was also happy to be with you physically last year. It was a great meeting. Unfortunately, I couldn't travel, so at least I'm with you remotely for a few minutes. And without further ado, I will start my presentation about the quantum safe security solution, and I will focus on banking and financial. It will be a rather high-level presentation. I hope that this is suitable for you. In any case, feel free afterwards to reach out for me and ask questions if you have. You probably have my email. You will see it otherwise at the end. The agenda of my presentation is, first of all, I will discuss a little bit the quantum threat. Of course, you probably have seen that already, so I will try to focus on what is relevant for finance. Fortunately, we have solutions against the quantum threat, which are quantum safe solutions. I will discuss them and explain what kind of solution we have. Again, probably something you've seen in this meeting a lot, but just again to give some ideas, maybe a different view. And I will focus on two quantum technologies which are really relevant, I think, for finance and banks, especially. One for data in transit, which is, of course, QKD, but as we know it, very common. And the second one, a little bit different, which is really using quantum technology for data at rest. We call it the quantum vault. And just very briefly, what we see as the future. So let's start. What about the quantum threat? What we all know now is that a bank is not at all what it used to be 100 years or 50 years ago. At some stage, a bank was a place where you put your value of your assets. So you would put all your assets in a safe, and that's it. Now, today, a bank is simply a repository of digital assets, which means that all the bank has is bits, strings of bits which represent something, but really their core assets are represented by these bits, and these bits have to be able to move from one place to another. You have to be able to know where it's come from, you have to be able to authenticate somebody sending you bits, and you have to be able to do transactions. So a bank is really not anymore a safe or for physical stuff, but really a digital entity, and it's probably the most important thing for a bank is to have access to its digital asset to be able to share them and move them around. And that's why the quantum computer will be a threat to bank and all the financial entities. So the quantum computer, the main difference between classical and quantum is that you do computation with qubits, you probably heard that before, and you build coherent superposition of states. So instead of having an input state which is a single, well, you have a single state, but you can make a coherent superposition of many, many states, and therefore somehow the quantum computer behaves as a massively parallel computer. I'm not going to discuss the quantum computer with you here. It would take too much of my time. But the idea really is by using a quantum computer, some intractable computation suddenly becomes feasible. So you can solve problems which you couldn't solve classically. Of course, most of these problems may be useful. You're trying to use them for the good. But some of them, I call it the dark side, means that they will destroy our cybersecurity infrastructure. Again, I'm sure you heard that before. So the idea is that factoring, which is at the heart of all our public key cryptography, becomes an easy problem. And now you can easily destroy everything based on public key crypto system. And that's really the big worry for all applications, but of course, especially for banks and so on. For finance, there are two very important requirements, but with different ones. Probably the most important one is authentication and integrity. When you do an exchange with your bank or between banking authorities or between financial entities, the most important thing is that your message is authenticated and that the integrity is assured. Because if you send a message, please forward $10,000 to my account, you need to make sure that it's $10,000 and that it's your account, obviously, otherwise that's a problem. So the most important thing really is to assure integrity. But this integrity has to be done until the time of the transaction or at the time of the transaction. Once you do it, it's over and you don't care so much. So it's the most important thing to do. However, you only need to be sure that it's working until the time you do the transaction. Another thing which you need for banking application, for others as well, but especially for banking application, is confidentiality. You don't want people to know what you've been doing. You don't want another company to know. You don't want your colleagues to know. I mean, financial details are really something you'd rather keep confidential. And that actually might be a little bit less important than integrity, but the worry is that this has to be assured for the future. If I exchange a message with my bank today saying, send $10,000 to my account, I want this to be authenticated on integrity check, but I also want this to be confidential for some years, I mean, as long as possible. And that's a little bit harder because you need today to believe that your message will be confidential now and in the future. The same applies a little bit for signature, actually, because if you sign something, you need to be able to demonstrate later that you signed it. So the signature has to be unforgeable even in the future. And that's a little bit more difficult to ensure to know what will happen in the future. Why is it so important now? It's because of what is called harvest now and decrypt later. A full-scale quantum computer is probably not available today. We are not entirely sure about that, but we believe so. However, it's quite reasonable to expect that the quantum computer will be available by the end of the decade or a few years later. In this case, if you get data from your bank or from anywhere and you store it, and the data is encrypted with non-quantum safe systems, which is the case today, because every single encryption today is based on public key crypto, which is itself based on RSA, on this factorization. So we know that everything we exchange today over the internet, and it's true actually for any kind of exchange with banking and so on, will be discovered as soon as you have a quantum computer which is cryptographically relevant. That's called the harvest now, decrypt later. So even if you don't have a quantum computer now, which is what we expect, we still need to make sure that we will have security in the future. So we need to start addressing this problem of the quantum computer today for ensuring confidentiality of the future. As I described, for integrity, for example, the problem is slightly less acute because you only want the integrity to be until the time of the transaction. If today you have no quantum computer, there is no problem. However, it will also take time to move to quantum safe, so you need to prepare your infrastructure to the quantum computer in any case. Fortunately, we have some solutions. They are called quantum safe solutions. I will very briefly give you a hint of what they are. You probably have seen them as well, and then focus more on two banking applications. So we have a quantum safe cryptographic toolbox, I call it. And this toolbox contains different types of solutions. Some solutions, I call them the mathematics solutions, and some are physical based on quantum. Mathematics, you have symmetric crypto, which is quantum safe today. We also have hash-based functions for authentication and signature. So these functions, these are really believed to be completely secure today and quantum safe, these two, and they exist today. You also have so-called post-quantum algorithm or quantum-resistant algorithm, which are devised for key exchange mechanism and signature. So these can be used in very different applications. These ones are being now standardized by NIST and around the world, and we hope to have also some solid algorithm which will do the job. However, there are still some questions about the long term, and I will come back to that in a moment. In addition to this mathematical object, we also can use quantum in order to protect our cybersecurity. The first thing you need to do is to use key generation with quantum random number generators. If you do that, then you have better keys, and that will improve your encryption. And in fact, better key generation combined with post-quantum is very good, because post-quantum algorithms require a lot of randomness. So it's always better to use the best possible randomness. And as you all know, the other thing we can use for improving our cybersecurity is quantum key distribution. Quantum key distribution is only used for key exchange mechanism, so you need to add to it some other possibilities for authentication and integrity, but this is good for the future. And that's what I'm going to show right now. Any kind of computational security, security based on algorithm, comes with an expiry date. It means that because you have better algorithms, you improve also the computing power, the security of anything you exchange today will decay with time, whatever you use, which is computational security. And we see here, for example, if we have Diffie-Hellman, we believe it would decay slowly, but at some stage a quantum computer comes, and we believe now that in 10 years or more there will be no more security. When you use post-quantum, we hope that the slope will remain the same. The slope is probably higher today than with Diffie-Hellman because we are not sure about the classical properties of our new post-quantum algorithm, or not as sure as we are with more standard crypto we have been using for years and years. So we believe today that there will be a decay. This decay might not be so fast, but in fact we don't have any strong idea about what will happen in 10 to 15 years about also post-quantum. Maybe we have chosen the wrong parameters and somebody will come and say, no, in fact, the parameter you choose here was not safe enough and the decay will be faster. In contrast, QKD will remain safe forever. It means that if you do a key exchange today, the key exchange will remain safe whatever computational progress you have in the future. Sorry. So that's, I think, the big advantage of using QKD for some exchanges, because you know that in the future the key exchange will remain safe. Of course, at IBM Quantic, we offer QKD solution. I just give you one example here. If you're interested, of course, please contact me. The idea here is not to do a marketing pitch, so I will go fast on this one. Let me give you two examples for finance about using quantum safe QKD for this application. First one is data in transit. This is a very standard way of using QKD. You have a data center, which can be a headquarter of a bank, which is really a big data center. And you need to have a backup because you don't know what can happen. This can be damaged, destroyed. And so all the data of the bank has to go from your data center to your backup center in order to be secure. So every day you have so many exchanges here. All the life of your bank is going through this encrypted link. So you use today, most probably, if you're a bank, you use most probably link encryptors with AES encryption, and you exchange the keys for your AES encryption by post-quantum crypto. Our idea, our suggestion is you keep all that, you don't change anything, but you add to that a new key which will be given by QKD. So you add a QKD key to your encryption system, you keep the whole network, and you have now something which is already quantum safe. The good news is that many of the link encryptors you can buy now commercially have this possibility to add this extra key coming from quantum. There were even standard API to do that. It has been standardized by Lexi. So adding a QKD level to protect the biggest link you have with your bank is something you can do easily today, and it's something we truly recommend for banking applications. There is another application of QKD for data at rest, and we call it the quantum vault. The quantum vault is based on the following idea, that in many cases, your link to your asset is only through a private key. So you have a private key, which is basically a title to your assets. This private key has to be stored, and of course you would like a backup. But you don't want to duplicate this key because anybody with a duplicate of your key would be able to get to your assets. Okay? Nobody can know who you are except by having your private key. So anybody with your private key will be able to claim your assets if you want. So what we suggest is use the quantum vault where you take your keys and you split them. It's called Shamir secret sharing in such a way. Here I saw an example with three different, we call it a shard of the key. So you cut your key into three different shards, and you send the shards to different storage nodes. And the idea of Shamir key sharing is that if somebody is destroying, let's say, one of the storage nodes or got access to this storage node, he will not be able to recover the key. However, if the two storage nodes collaborate to go back to get the key back, they can do it. So you can actually lose one of the key storage nodes or have one storage node attacked, and it doesn't matter, you can recover. This is just an example. You can make it much bigger with, for example, 5 storage nodes, and decide that if any 2 out of 3 fail, it doesn't matter, and that 3 are the minimum that you need to recover your key, or you can even go further and further. And the idea of the quantum vault is that if you exchange these keys here protected with QKD, you got the best possible protection. In fact, when you use QKD with these keys, it's exactly equivalent logically as if all your key storage nodes were with you together. Logically, this is in the same place, but physically they can be aside, which is actually necessary in order to make sure that you can recover the key in case some of these storage nodes would fail. That's what I've been telling, basically. This slide is about what I've been telling right now. We got really conditional security thanks to Shamir secret sharing. You can have a backup of your key because even if something fails, you still have your keys, but you don't duplicate them. In order for somebody to have a copy of your key, you need most of your nodes to collaborate to take it back from you. The good thing also is you got a good separation between access and storage. You don't access your asset all the time, but you want to store them for a long time. When you need access, you bring them back, you do whatever you have to do, and you send them back to storage, and that's easy to do it. And you can choose your level of security by adding more and more nodes. So I think these two simple examples show you that QKD is useful for banking and all kinds of financial applications, both for data in transit and in some cases for data at rest. What about future development? Just one last slide about this. Today we do QKD between nodes, and if we want to go long distance, we need to build what are called as trusted nodes. We hope that soon in the future, maybe in the framework of 5 to 10 years maximum, we will build a quantum infrastructure where you can exchange qubits freely around the world, and then any point in the world can share qubits with another point in the world, and you can build a secret key from any point to any point without of the network knowing anything about the keys. The only technology challenge which remains are quantum memories and quantum repeaters, but if you follow, and I'm sure that there is a lot of work on these things even also in India and in the rest of the world. With that, I thank you for your attention. I wish you a great meeting. I think it's actually towards the end, so have a good end of your meeting. And again, I'm quite happy to answer questions if you have some. Maybe the best way would be to do that later remotely. Thank you very much.
We thank you, rather, Dr. Bruno Huttner, for joining in our session and conclave and for your presentation. Thank you so much. Any questions, ladies and gentlemen, if you have anything to ask?
Madam, I asked some questions. Can you please elaborate on this qubit Hilbert space and quantum Hamiltonian analysis?
Yeah, so qubit Hilbert space is basically the space where we do the computation. So you can see it as an infinite dimensional space where the inner product is usually happening. So it is represented by Dirac notation, and the symbol is there. So you can study more about the Dirac notations that are there in order to learn more about Hilbert space. I hope that
I'm sorry I didn't get the question. Can you, maybe somebody with better sound?
Mine is represented by 1, 0 invert. So it is mostly used to only 2 dimensions. How you extend it to infinite dimensions?
So we restrict it to 0 and 1, right? So you said what is Hilbert space. So Hilbert space is sometimes finite also, it can be infinite also. So you can check it out. I think that is in just a summary that this is what Hilbert space is. That is where the quantum computation takes place. So it's the inner product that does the mostly the Hilbert space.
Basically, the qubit is represented by the linear dependence of the 0 and 1.
Yeah.
So that qubit is, if it is between 0 and 1, it can be written by 2-dimensional representation of 0 and 1. Alpha 0 plus beta 1. So that is the representation, center representation of qubit. How do you extend it to the infinite dimension Hilbert space?
Sir, because you can consider it like a globe. Okay, on the globe there is north pole and south pole, right? So north pole you can consider 1, south pole you can consider 0, and on the
More technical.
so it can be like on the globe there are a lot of points are there, right? So you can say there are infinite points on that globe. So similarly, that is the Hilbert space where all the computation is happening, and that is what a qubit block sphere is how it looks like.
What about this quantum Hamiltonian analysis?
So Hamiltonian is a different methodology, like how when we have to, let's say we have to find out the Hamiltonian when we are doing the chip analysis, right? So what is the right Hamiltonian? So
Hamiltonian is basically energy, that sum of the potential and kinetic energy as far as classical mechanics is concerned. How do you generalize to quantum mechanics and quantum computation, quantum chip design?
So when we are designing the chip, right, these Hamiltonian analysis and all those EPR analysis, all
technology you are using accordingly will model the channel noise and do appropriate error correction, right? So in any communication scenarios, it's coming from classical communication as well and applies to quantum communication as well, that any channel noise or error correction will be done after encryption and before decryption, right? So that's kind of an additional layer.
Like sir, in classical encryption, classical communications, encryption is nothing but a permutation and combination of ones and zeros, right? And in your quantum encryption, it is a permutation and combination of different qubits.
No, I didn't talk about quantum encryption. Even when we do QKT, after QKT we do classical encryption only. So the goal of QKT is to generate a classical key.
No, then what is the vehicle which transmits the QKT bits from the transmitter to the receiver?
The QKT
Yeah.
bits. Yeah, so you can, okay.
It has to travel on some way.
Yeah, so that is either free space or these fiber optics, right? There are many technologies, but that schematic is a replacement of PQC. Okay, so that has nothing to do with quantum channels per se.
Okay, thank you for now, ladies and gentlemen. And if you have any query, any doubt, any question, you can ask directly later on. For now, thanks to. I'm really sorry, sir. I'm afraid we are getting already really sorry for that. But then, first, I would like to thank Dr. Bruno Hartner, and then we were joined by Dr. Olivier Nora from France. So we thank our speakers, and especially speakers sitting on the dais. Now I request Sri N. Murli Krishna ji, DDG Southern Region, to kindly felicitate. Sri N. Murli Krishna, DDG Southern Region, TEC, will now felicitate our speakers. First, Dr. Venkata Subramaniam will present a memento. May I request Sri N. Murli Krishna ji to present a memento to Ms. Megha Srivastava. Sri N. Murli Krishna will now present a memento to Sri Manan Narangji. And now, Sri N. Murli Krishna ji will present a memento to Dr. Gautam Paul. Thank you, Sri N. Murli Krishna ji, and we thank all our speakers. Thank you so very much. With this, ladies and gentlemen, we wrap up this session, and now we have a tea break. But on the other side, after the high tea, we have a panel. So, ladies and gentlemen, in our second International Quantum Communication Conclave, now we'll have panel discussion on applications of quantum technologies, deployment, perspective, and use cases. Dr. Rajkumar Upadhyay, CEO of C-DOT, will chair the session, this panel discussion. And our panelists are Shri G. Narendranathji, Joint Secretary, National Security Council Secretariat; Shri Amit Srivastav, Scientist F, Research Center, Imarat DRDO; Shri Manoj Gurnani, Chief Technology Officer and Head Strategy, Nokia India; Shri Saurabh Tiwari, Chief Technology Officer, Dell Technologies; Shri Sridhar CV, Head Alliances Corporate Incubation, Tata Consultancy Services; and Ms. Tavleen Oberoi, Senior Solution Architect, Thales Cloud Protection and Licensing. So these are the panelists who will be joining in this discussion. And as I already shared, Dr. Rajkumar Upadhyay, CEO of C-DOT, will chair the session. So, ladies and gentlemen, we'll now have our panel discussion on applications of quantum technologies, deployment, perspective, and use cases. May I invite on stage Dr. Rajkumar Upadhyay, CEO of C-DOT. I now invite our panelist, Shri G. Narendranathji, Joint Secretary, National Security Council Secretariat. May I request Shri Amit Srivastav, Scientist F, Research Center, Imarat DRDO, to kindly join us on stage. We have with us Shri Manoj Gurnani ji, Chief Technology Officer and Head Strategy, Nokia India. I'm requesting him to kindly join us onto this. Shri Saurabh Tiwari ji, Chief Technology Officer, Dell Technologies. I'm requesting you, sir, to kindly join us. We have Shri Sridhar CV, Head Alliances Corporate Incubation, Tata Consultancy Services. I'm requesting you, sir, to kindly join us onto the dais. And now we have Ms. Tavleen Obroy, Senior Solution Architect, Hales Cloud Protection and Licensing. Thank you, ma'am, for joining in. And now I'll request Dr. Rajkumar Upadhyay, CEO of CDOT, because sir will chair this session. Thank you.
Good afternoon, everyone. I think we have really thin attendance today in the afternoon session. Maybe still people are in the T area, or we have this much of attendance. I think somebody from the organizer side can put a thing towards the T area. So good afternoon, everyone. First of all, let me thank all the esteemed panelists for joining this panel. I think they are all experts in their respective fields. We have been listening to various talks, technical talks, deployment talks, challenges, opportunities in quantum. I think both the days had been very, very enriching in terms of knowledge dissemination, in terms of what is happening in some countries, because we saw some of the speakers from other countries. I think it is an excellent platform to know what is happening and how we steer forward for our country. We all know that first the biggest challenge is awareness, that the awareness of quantum is very limited, and these kind of events actually bring this important topic in the fore, because we all know the security is going to be very, very important once quantum computers come, and there are other applications also. And there is a lack of priority also, but if you see in last 2-3 years, many countries have launched quantum programs. China, for example, is $15 billion program, US, Chile, Australia. I mean, most of the countries have put program, and we have also recently announced a national quantum mission. There are other challenges, deployment challenges in terms of lack of dark fiber, lossy fiber, terrestrial solar noise, pest infestation, ambient temperature control, like for superconducting material with the cryogenic kind of environment. I was just reading the net and saw that what are the key, because this panel is about the use cases, what are the key areas where the quantum can do. One is primarily what this conference was about, quantum communication. But in terms of quantum applications, I was reading that there are the use cases for quantum is in financial modeling, weather forecasting, traffic management, studying the traffic patterns, use of AI, ML in a big way, cryptography, cyber security, simulations. Simulations will become very, very easy. Drug discovery, because it becomes very easy to make these changes. Solving complex problems which are not possible to solve with classical computers. One application is when you given the MRI scans or this thing, it can predict what is happening without even going to the doctor. Image and speech recognition, which is available today, but it will be much accurate, much faster. So there are lot many applications there, and we have a very esteemed panel representing different. We have people from Thales, TCS, we have from Dell, Nokia, we have from DRDO, we have from the government, NSCS. I think how I propose that we will give each participant 5 minutes initially to talk about what is happening in their organization about quantum, what are the opportunities, what are the challenges, what are the priorities, and what the government should do, what the as ecosystem we should do to take it forward, so that as a country we advance ahead. We have 2 presentations. I think 2 of them have come with PPTs, so we will allow them to have PPTs, but we should restrict it to 5 to 6 minutes so that others also give time. So I think we'll start with TCS. I invite Mr. Sridhar to make presentation, and then followed by Nokia, and then we'll have a free flow discussion in terms of first each participant will talk about what is happening in their area in the quantum, and then we'll, if time permits, questions from the audience. Over to you, Dr. Sridhar.
Thank you, sir. And
5 to 7 minutes.
Thank you. Yeah.
Thank you for giving us the opportunity to be at this panel and a part of this initiative. So I'll briefly cover what TCS is doing in quantum. So it will be very comforting to hear for many of you that an Indian organization is investing into quantum technologies for some time, and we are also part of the larger ecosystem. So I'm part of a group called Incubation, so which works mainly on technologies that are close to commercialization. So we have taken this quantum bet as an incubation program in 2021 when we saw that the technology trends are shaping up very well. So earlier this was a research program at TCS, started way back in 2017, but 2021 onwards the trends started shaping up very well. So I have a lot of information on this slide, but some points that I would like to cover. We've been talking to all major players that are working in this technology area. So talking to OEMs, one interesting data point, which is maybe at an inflection point, is most of them in their roadmaps for 2024, 2025, they've announced that these things will come into data centers. And there is also a possibility of networking and stacking. So these are the two data points. That is a inflection theme. Given while we are battling with other challenges like 1000 qubit quantum computers that are available today, whereas we can do very little amount of things on those machines. I'll come to those use cases as well. But these are two interesting trends which will shape up and also align to the theme of this conference. We do have a lot of challenges working on this technology. We'll not go into that one, but some of the things, there are few implications for all of us. So how will our data center will look in, say, 2030? So when we have quantum computers available. So do we need to buy more infrastructure for running our AI applications, or we need to reduce because we have quantum computers and also give position for quantum machines in that one? So on the customer side, there's a lot of dilemma. So whether to wait, because a lot of information that is coming in all directions. So again, there is a hype around this one, and customers are little confused also whether it is a fear of missing out or they have to wait for making decisions. But having said that, so we being an incubation team, so we try to unravel all these mysteries and try to work around these things. So what we have structured is we've created 4 different teams that attack all these areas. So we've divided our teams that are working into the areas like optimization, AI and optimization is one theme, which is more of mathematics, and simulations, which is mostly working on chemistry applications. And then there's a cybersecurity team, and there's a new sensing team. We've been working with Dr. Vijay Raghavan's team for TIFR for building the software stack for the quantum machine that he's working on. We're also part of the Quad Forum, where we are representing India on the quantum computing task force headed by Japan. Myself and Vijay Raghavan are one of the members of India Quad task force for quantum computing track. And again, we're contributing to standard bodies. But more importantly, it's also important that we take these initial themes to customers and see how they are adopting these things. So to start with, at TCS, we started with a quantum virtual lab. So we created a virtual lab in partnership with AWS, and then try to get access to all our associates who can try out experiments in this one, because it's a new technology area and requires a different set of skill sets compared to the traditional classical skills. So initially we did not find even interest also from members, but eventually, again, after some time, so we could identify a good set of people. And then we also had a lot of external experts who come as who are postdocs abroad. So we got them into the team and then started working on different set of use cases and built a critical mass. And that is when we started going to customers and then presented what are the possibilities in this case. Okay, so I'm just going to cover, because the theme of the presentation is anyway use cases. So just to give an idea of what kind of things that customers are exploring or trying today. None of them will generate any ROI today. If you ask me whether is a visibility for what is a visibility, so maybe 26, 27 or beyond that. That's also a 50% probability. It all depends upon how the hardware evolves. So these are 4 different set of use cases. Just take the theme. So sir already mentioned some of the possible applications. So the first one, we are working with Asia's largest construction company. So they've done this use case with classical AI, which is like image processing to detect rust or anomalies in the building. Right? So they said, okay, why don't we take this problem as an experiment and then do it on quantum. So we took the very popular model, so which is UNet, and modified that with quantum, and then try to rerun the experiments. Right, so yeah, we achieved some success, but it is a mixed set of results. We cannot say that our results are good or great, but the objective of the experiment is achieved. The second use case is working with a postal company, services company, leading postal service company based out of Europe. Here it is a forecasting use case. It's a time series forecasting use case. They were using the most popular model created by Facebook. And now again, they also wanted to experiment, okay, can we try quantum way of doing these things? Again, so we are able to match whatever classical is getting, but we never be able to beat the benchmarks, right? And the results are also not consistent. So can't say that every time you run this, it is probabilistic and you will not get the same results again. We have some good success with pharma customers, so we built some platforms and we have a lot of IPs and patents in this area. So this is the area where we are seeing a lot of traction. All the customers are excited, all the leading pharma companies, anyway they are part of the QPharm forum, which is a consortium of 17 pharma companies. So they are working on this, a lot of interesting activities going on, and this is area where we are seeing initial traction. So if somebody wants to invest into technology areas in quantum, so this is one area. So the last one, very relevant for this forum, is working for a leading bank, and this is the case of a post-quantum crypto migration, right? So here is the first bank that has told. We've been talking to multiple banks, so because half of TCS revenue comes from banking customers, but there's one bank which said, okay, let's give a try. So we started a post-quantum crypto migration project pilot with them. Said, okay, let's take a series of applications and then apply a framework and then get the migration into PQC. So this is what actively working on. So I think the 1, 2 are complete. The phase 1 is complete. 3 is an ongoing activity, and 4 is an ongoing activity. On the post-quantum cryptography side, just take 2 minutes, sir. Yeah. On the post-quantum cryptography side, so we are working with a partner based out of UK, and also we have our own products which we are using in this area. So it requires a risk assessment framework, so you need to understand your applications and then put a strategy for migrating those applications. So following a framework for this one. Other areas also we are working on sensing. So just to give some input, so we've partnered with multiple players, and then most importantly, we again partnered with a few customers and floated this challenge. So with that, I'll conclude this. So what we generally go to customers is with one idea, saying that because this is a story that is coming in 2030, so no customer will be interested to invest into this technology. So we say, okay, please join us and go with this quantum value discovery approach, and then experiment within a 16-week cycle, and so that your team can also learn and do pilots in this scale. So the hardware is continuously evolving, requires a different set of skills, and it is very exciting. So with that, I'll conclude this and hand it over back to sir.
Thank you, Mr. Sridhar. Madam, we have time up to what is our time limit? So we started at 4:50? Yeah, so 5:50 we have time, right, thank you. So now I invite Mr. Manoj Gurnani from Nokia.
Okay. Good evening, everyone. I represent Nokia and Nokia Bell Labs. I'm sure most of you would have heard Bell Labs name. Bell Labs is the name which is known for innovation. And as you would expect, we actually invest heavily in this new area of quantum. What I'm going to, so may I have the slides? So till the time slides come up, I can start to do a little bit of a self-promotion. So, yeah. So you would have heard that the discovery of transistor, the very basis of the digital world, was made in Bell Labs, 1947, William Shockley, right? Bell Labs has 10 Nobel Prizes and several other awards for innovation. So at Nokia and at Bell Labs, I think we are very, very committed in terms of investments towards innovation and how the societal use cases can be developed. So, okay, so I covered the self-promotion part. I'll get to the presentation now. Can we go to the next slide, please? Okay, yeah. I think we are all in the middle of Quantum 2.0, right? Heavily invested area, especially the quantum computing. And the very basis of the current Q 2.0, as we call it, is basically the two great properties which we all know, entanglement and superposition. And these two properties, which used to be just like the sci-fi kind of things, have become the very basis of the future and the capabilities it will bring in front of us. Next slide, please. So, yeah, I think this is covered. Maybe we go to the next slide. Let's look at some of the numbers. I think it's very important. Sometimes we fall in love with technology so much that we forget about that, what are the use cases, what is the business it is going to generate. So I have pulled in some numbers in terms of how much effort is going in terms of the research, how much business potential this new thing called Quantum 2.0 promises to bring. And these are all McKinsey numbers. So if you have a look, almost in 2022, there were investments of a whopping $35 billion made, right? So kind of underlines the fact that this technology has huge future. If you talk about the value add which this technology will be bringing, we are talking about trillion of dollars. So $1.3 billion by 2040 will be the value which this technology alone can bring to the world. In terms of the business revenue, 106 billion by 2040. So another 15 years, I think this is going to be an industry in itself. So that's Quantum 2.0 in terms of the potential. If you see the patents, 1,600 patents, and it's normally led, you would expect that by US, UK, Canada, and Europe. I think these are the large four nations who have been investing heavily, and I think they are the ones who have been able to generate quite a bit of patents in Q 2.0. Next slide. So if you talk about quantum, I think roughly we have three buckets which we talk about. First is the quantum computing, and we all know about the processing capabilities of quantum computing. At Nokia, we are not into computing that much. What we do is we focus on the use case which is coming out of quantum computing. So it could be cryptography, it could be AI/ML kind of cases which eventually lead to the communication infrastructure. And we all know communication is critical infrastructure. The second stream is really the quantum communication, which is where we focus. So most of our research is on quantum communication. So we talk about quantum internet, we talk about cryptographies, the quantum safe distribution, keys, etc. Sensing is the most under-researched area today, but I think very, very exciting. And I say this because when you talk about 6G, I think RF sensing is another potential use case which you talk of. So we are talking about RF sensing, and now we are talking about quantum sensing. And this quantum sensing is going to be another beautiful area for the simple fact that the sensors will be so sensitive that all the parameters, be it your acceleration, velocity, and other things, you are able to measure it. So, more precision. I think that's what will lead to. So as Nokia, our focus is on quantum communication, little bit on sensing, but right now more on quantum communication. And we are trying to figure out that will we actually have what we call it as quantum internet. Next slide, please. Yeah. So I think, these are the myriad of technologies. I'm not going to run through all these, but like I said, I think for us, the exciting areas continue to be in terms of the sensing and in terms of the communication. I'm going to spend maybe just 2 minutes on the use case because I think that's what the theme of this discussion is. And maybe next slide. Yeah, molecular modeling. And I think this is one thing which really amazes me. Just imagine, thanks to the power of quantum computing, you're able to do the molecule modeling. And what it basically means is that the process of drug discovery, and we saw how much time normally a vaccination, for example, formulation takes place in the COVID times. We all saw that. With this kind of capability, all the research and all the precious dollars can be wiped out, and you can do precision-based modeling, in a matter of days and months, actually. So I think that's the power of quantum for you. So, huge impact in terms of molecular modeling. Drug discovery, for example, I think that's another use case which this technology can bring in. So completely out of communication, but I think this is another potential area. You know, for example, we talk about the cancer treatment. I think that's what this technology is going to bring on table. Next slide. Cybersecurity. I think most of us are going to talk about cybersecurity in detail, but just to give you the idea about how crucial this is, the amount of digitization which we have done today, right? The quantum computing, even with the classical cryptographies, etc., with the advent of quantum computing, all this can be broken very easily. You know, we talk about so many algorithms, Shor's algorithm and other things. The classic computers, RSA algorithms can be broken very easily. What does it mean? All the critical infrastructure and all the digitization systems which we have built, they are under huge threat. And therefore, what do we do? The first thing which comes to human mind is that we should back up these systems, right? One estimate says that the amount of digitization which we have done, if you have to do all these backups, it's going to take you 20 years. And by this time, quantum computing will become very big. And therefore, I just want to realize to the whole audience that this threat is real. And therefore, it should be taken very, very seriously. So that's cybersecurity. And again, I think this is a huge area of research for Bell Labs and Nokia. And I think we are investing very heavily, right? So how to make the next generation telecom systems very quantum safe? How do we do it?
Udani ji, we have to summarize.
Yeah. And I'll just quickly, artificial neural networks, again, I think we talk about deep TX, deep RX kind of technologies. Thanks to the computing capability, artificial neural networks will become very, very quick. And then we talk about logistics, financial modeling, and there are so many other areas, you know, which we can talk of. So with that, I end my introduction. Thank you everyone.
Thank you, Udani ji. Thank you. I think both the presentations were exciting in terms of the real application of quantum. It's not theoretical. It's practically how Nokia is using, how TCS is using. So I'll now start with Madam Yu. You can talk about the context I set in the beginning. What is being done? What are the opportunities, challenges? What is the roadmap and how we should progress?
Okay, so thank you very much for inviting Thales on this platform. So a little bit background about Thales is, so as it's mentioned from the Nokia team that we are heavily invested in the cyber security, and where this is the area where Thales begins its journey. We are a decade-old company, and we are in the process of making those hardware, those software that can help the digitization process, the overall process, a secure process, even it's the on-premise or cloud migration or fast scalability, your data is expanding. So you need to have those solutions that can actually protect your data. So we being Thales are market leaders in developing solutions like HSM, which is hardware security module. If you can recall, there was a slide which was presented by the gentleman Bruno Huttner on from the IDQ, and he mentioned that you are using QRL and feeding it to the HSM-based solution. So the reason why you are putting any QRL into the HSM-based solution is because they are known for their security of keeping the secret as a trade secret, and no one in the world can export it out. So this is where Thales' journey begins, and with the quantum era, we are also investigating and we are also making our product quantum ready or quantum resistant kind of approaches. So in a nutshell, there are various ways of dealing with, just associating why we are here. In today's era, there is various attacks which we are seeing in terms of quantum computing, as gentleman completely mentioned that with the cyber security and the way you are expanding the digitization, the basic form of this digitization is PKI based, wherein you are using the asymmetric key pair and public private key pair for exchanging of your communication and having a secure tunnel between two entities. Now, if there is a quantum era which is coming into picture, you are under the attack of breaking that RSA key pairs. How to make sure that these foundation can be secure in the quantum era by using quantum resistant approaches, which could be using PQC, which is post-quantum cryptography technologies, and it could be even having your appliances generating the key, which is robust in the quantum area, like quantum random number generator, or you can have other ways of distributing the keys, which is quantum key distribution mechanism. So coming back to the topic, so Thales is basically investing and making the products approach of securing your data with quantum safe approaches. And with that, I think I have set some context of what we are doing in Thales.
No, you can explain that you talked about HSM.
Yeah.
So how was it in classical era and what is the change?
Okay. So
Because so that audience understand that what
so
is the
in
change.
classical era, we have two definitions, like we are protecting data at rest and we are protecting data in motion. So for data at rest, you need some encryption keys. And if you have the key, you can basically unlock all your protection layers. So how well you secure your encryption keys is the bottom line for you. So HSM is one hardware which is NIST approved FIPS level 3 hardware appliances that can give the assurance that you would have the best in class security for your encryption keys and hence you are able to secure your data. So this is the traditional way of dealing with encryption and its security. Now with quantum era, when you are securing your keys, you are typically relying on the RSC cryptographic key pair kind of technology, wherein you are using some public key and some private keys, and you are storing that private key into the HSM box. Now, with the quantum evaluation, as mentioned by the gentleman, with Shaw's algorithm, it has been predicted that if there is a quantum computer, you would be able to break the RSA key pair very easily. So, in order to make sure that you are not relying with the security just with the typical traditional asymmetric key of RSA, you are using and opting for various NIST finalist algorithms like Falcon, Kyber, Deletium, and so on and so forth. So this way you are basically ensuring that whatever encryption keys you are using, they are NIST finalist. Of course, the standardization has to come yet from the NIST, and not relying on the traditional asymmetric algorithm of AES or RSA and ECC, just using these keys like key encapsulation right from Kyber and handshaking mechanism from Spinch and Falcon for the asymmetric algorithm. So the hardware security module has those post-quantum cryptographing embedded in the HSM module itself. So this is how we are, gearing up from traditional to the quantum era.
So it is already operational, what you are saying?
Yes. So our HSMs now, starting from version 7 onwards, they do have the capability to load the PQC firmware within the within the HSM appliances, and they are ready.
Thank you so much. So I now move on to Mr. Saurabh Tiwari, who comes from Dell, and you all know Dell is a leader in terms of compute and storage. So given that context, you would like to open up what exactly Dell is doing and what do you think, where we are going, where we should go?
Thank you, sir, and thank you so much all for taking time out for this quick session. Honestly, so we're a leader and we collaborate with industry leaders to realize use cases in classical computing. Now, obviously, quantum is a completely different ballgame, and there we collaborate with a rather large and very innovative player, which is IonQ. Okay, they are into trapped ion ytterbium-based quantum computers. So we collaborate with them. We build the infrastructure around it to make sure that we guarantee committed fidelity. Okay. From a solution point of view, I think since NN sir is also here with us, I thought it is only worthwhile to mention that while we work to build competence in the field of quantum computing, it is very important to also look at the current geopolitical scenario, which is perhaps not in the most optimum situation at this point in time. And we need to look at quantum-proof encryption algorithms, which we can incorporate into our sensitive infrastructure, particularly defense, particularly finance, immediately, to ensure that as and when, while we do not have leadership in quantum computing at this point in time, but our geopolitical competitors may soon achieve something which is called quantum supremacy. And that is something that worries me because while a lot of the data that we transmit is inherently encrypted, like information from banks and so on and so forth, there's a lot of information that is being transmitted governments, and all of that, while it is encrypted, it is being, it could be stored. And later on, let's say 5 years down the line, 10 years down the line, when quantum computing actually does become a realizable and a practical solution, our enemies or malicious actors could go ahead and decrypt that information using quantum computing. So the question one would generally ask is, let's say they do it in 10 years, would that information still be relevant? Well, the location of our missile silos would not change. The location of our army bases would not change. Air Force bases would not change. Information about where or who or what secret sources we're using to build our next generation defense equipment, the defense aircraft, the missiles, that would not change. And those are going to be needing a lot of protection. So if someone were to, let's say, store that data which is being transmitted on the wire, that is going to be a challenge. In addition to that, historically, we've lacked fiberization. So only 30% of our base stations, 32% of our base stations are fiberized. So if in case we want to build end-to-end quantum encrypted networks, the lack of fiberization will prevent us from doing so, because obviously microwave transmission, you're not transmitting photons, you're doing a lot of protocol conversion, you're doing a lot of conversion across domains from electrical to RF and so on and so forth. So again, that is going to become an increasingly difficult challenge to overcome. So we've got a lot of progress that we need to make, and I'm hoping that through such fantastic endeavors, we will be able to achieve the best interests of the country.
So what you're saying is Dell is working primarily quantum computing, or means you are developing quantum computers, or you're working into other areas of quantum also?
So we are a very innovative organization. Like our founder said, that we are a very large startup. So to use that to segue from what he says, we work on whatever our customers ask us to work on.
So what are they asking you in terms of quantum today?
Absolutely. So pretty much everything that Gurnani Saab just showed, everything that I'm sure Anand Saab is working on, everything I'm sure that you are working on, all of that is an all-encompassing series of verticals that we work on. Okay, it would not be fair for me to just take one of them out and leave the rest. I'm sure we don't have time for me to do that. But we work predominantly on the compute infrastructure part, if I were to put it so bluntly. But that infrastructure can be used for pretty much anything.
You also mentioned geopolitical scenario, and you said that store now and decrypt later, harvest later.
That's right,
you using. So since you are in the storage also, are you telling the governments to store the data of the adversaries, and this is how you store and decrypt it later?
I'm sure people are doing that, and we should be doing that, and we do make appliances which make storing petabytes and petabytes of information and referencing it in a split-second a reality. But I'm no advocate on defense, sir. I'm not mature enough to comment on that, sir.
Yeah, thank you. I think that was of the cup. So we move on to Amit Srivastavji. He's from DRDO. You know, the DRDO takes care of the defense requirements. I think you could put the perspective that what is happening in defense area and how these technologies are posing challenge to defense sector, and how the challenges need to be addressed in our country.
Yeah, good evening everyone. So as I think mentioned in the opening remark, that the quantum technology has got a dual uses. So it is like applicable in the defense as well as other sectors like health sectors, power grid and all. So what is specific to defense, I would just like to bring this point. So as we know that in the defense primarily we have to secure our assets and try to get more information about the adversaries or enemies. Okay, so the quantum technologies helps in effectively or getting this information about the adversary, also protecting your own assets. So that is why I think if you see the there's a quantum roadmap by most of the countries, and in making all these roadmaps, the defense is involved. Okay, so there's a race. I think among all the countries, whoever reaches first, they will have the competitive advantage. And I think, as history tells, that as the Enigma system was broken, and that has resulted in in the World War II ended 2 months before. Okay, so I think that is why it shows how serious it is to protect our assets and try to get the at the same time the information about the enemies. Okay, so it's this realizing this potential of the quantum. Around 6 years back, there was a committee set up by DRDO chairman, and we were tasked to define the roadmap. So as out of this work, that roadmap was defined, and then we have found out all the 3 or 4 verticals. So primarily, the first was the quantum communication and computing, and the sensing, ancillary, and the post-quantum cryptography. So we were asked to initiate the work in each verticals. So initially, the first was the quantum communication, and as I think others have done, so we started with implementing the simpler protocols. So some of the protocols were implemented like COW and DPS, and there were 2 demonstration field testing was done up to 100 kilometers, and after that we had a lot of brainstorming what next. So then we realized that the actual potential of quantum technology would be to use the superposition as well as the entanglement. So I think most of you will agree, suppose if you give some n number of qubits only with Hadamard gate and there is no C not gate. So if you cannot create entanglement, then I think it is of no use. So the same is applicable in the case of computing as well as sensing. So the real advantage will come if you can use both entanglement and the superposition. So I think the task may be you can say take a country-wide location, and then you select 2 locations, and can we create a efficient fidelity entangled pair at the 2 locations. So if this task is solved, I think most of the things would be done, because this would help us in doing the distributed computing. This will help also in doing the distributed sensing. So like you can have 2 telescopes recording the data, and then you can teleport the information and can achieve, you can do the super resolution kind of thing. Okay, and also you can decimate the accurate clock. Okay, the timing information, that is very much crucial to synchronize the all device across pan-India network. Okay, so this task, I think, as we know that the resources and even the manpower is limited, so why not target to end goal? Okay, so we have started working on this, and at our place also we have on tabletop we have created entangled pair, and we have given some projects to IIT Delhi and other academic institute, okay, to create an efficient entangled pair. And then the next we would be doing create 2 entangled at the distant place. Okay, so we need to use either, there are 2 approaches, either do entanglement swapping. So there are 2 places, 2 entangled generation, and then they do this Bellstead measurement at the center, and then communicate, and then these 2 points get entangled, and then we have to repeat this process, and then we can get any 2 points entangled. Okay, once we have entangled, then we can do teleport, or we can communicate, or anything can be done. Okay, and coming to the computing vertical, so there is we have set up DRDO set up a DYSL QT Young Scientist Lab, and who is working on along with the TIFR to have on superconducting qubit to realize these 5 or 7 qubits. And other than that, they are also developed the QRMC. I think that that was presented here, and also they are doing some work in the sensing. So I think sensing is also had a lot of use case in the defense. So which will help, we can do the sensing of many parameters, like you can sense magnetic field, you can sense oscillations. Once you do acceleration, you can, if you do on the 3 axis, you will have a gyro, and then you can do a gravity if you do the vertical acceleration sensing. Okay, so once if you can map the gravity map of entire Earth, so like you can find out the assets underneath, or even yeah, you will get a lot of information. Okay, so even there is another approach like in doing the quantum imaging. Okay, so that is also part of the sensing. So there is one concept called ghost imaging. So whatever object you are imaging, you are not touching that, but still you can image. So if you create an entangled pair, you send one pair to the object which has to be imaged, and then there is a correlation between these two pairs, and you use this to get the image. Okay, so this is called new concept, but IIT lab at Dehradun, they are starting doing work in the ghost imaging, and there is a concept of quantum radar and quantum seekers and other. So in which, as we know that, see in the quantum, like we are all second revolution, so we need to have the full control of creating quantum state and send it and manipulate it, or like measure it. So like the measurements, there are n number of possibilities. There are different type of state, like there is a single photon state, there is a Bell state, there is CHZ state, there are cluster state. So there are n possibility. There are skewed state which can do CVQKD. You can also have an entanglement in skewed state. Okay, so there are n unimaginable possibilities are there, and I think we have to try. And so yeah, so far we have been creating in the photonic in the visible or NIR range, the same entanglement we can generate in even RF. Okay, so once if we can generate in RF, and then we can send it to the target, and either it can be only just send and receive, or it can be entanglement based also. So if we have entanglement, then we can have very low SNR based quantum radars. Okay, and so because the advantage quantum provides that we can correlate these two, whatever entangled photon we are sending, and it is believed that that no stealth technology can escape with this. Okay, so we are also trying to initiate some work in quantum radar, and then other than the sensing, we have also working on the PQC and all. So the KL lab at Bangalore is working on post-quantum cryptography. So yeah, I think this is all.
Thank you, Mr. Srivastava. I think you touched upon quantum computing, quantum communication, and quantum sensing. Quantum material, I don't know whether you're working or not, but at least 3 sectors you covered very, very well. Thank you so much. Now I move on to Narendra sir. He's from NSCS, so we know that one of the responsibilities of NSCS is cyber security, and NSCS is taking all the responsibility, coming up with the policy measures, how to ensure security of a country. I think, sir, from your side, that what is that we are looking at quantum as a country?
So one of the things is that any new technology that comes up, there are, as you said, dual uses. It could be used for security, to ensure security, and the other is there are security implications of the technology itself. How do you address the security implications of that? So that is something that we keep looking at in the organization that I work in. So I'll say around 3 years back, we wanted to run through a project proposal for the telecom networks which are there, to how to make them secure, quantum secure, and how to put the encryption systems also, make them post-quantum secure. So we had got a project proposal prepared, but then I'll tell you, it was a challenge getting it through, and we failed. It didn't get approved. Of course, one of the reasons it didn't get approved is because people told that the national quantum mission is going to come, and so when that does come, then we can take it up with that. So let's keep it for the present. But from our side, the thing is that it would be coming, but we could parallelly start this work, because it will take time for the country to build up the technological capability, and there's a learning curve that's involved, and then you'll be able to build a team in the country that would actually learn this technology. So when the national quantum mission does come, we'll be in a position to have a quick ramp up of the activities in the country. But still still that didn't carry much weight, and that didn't get through. Good, now that we have a national quantum mission that's come about, hopefully we'll be doing much better now. So, however, subsequently a year later, we did come up with smaller proposals. That was a big proposal actually. We were actually wanting to have a proof of concept and then trying to roll out across all the networks in the country. That was a big proposal. So we did scale down that proposal, and then we started having multiple proposals on quantum technology, and engaged with organizations like CROT and IISc Bangalore and Puno Labs in the private sector also, and another organization is there. So we actually engaged with these organizations, and multiple R&D projects on different aspects of quantum technology we did. Of course, we didn't work in the areas of computing or in sensing area. Most of that was pertaining to quantum communication only. So, like some of the output of those initiatives, you would see in the demonstrations that we had. One is the hub and spoke model for QKD, which Unilabs has done, is a project that we had funded, and that has actually been completed. The norm within our organization is that whenever we fund an R&D project, we have, in the scope of the project, we have a PRMC which actually reviews that project and gives guidance for that. But at the end of the project, we also have a validation team that's created and a validation document also that's created to verify the claim. And that exercise of validation of that particular project has already been completed with it, and the product is also being deployed in certain installations. Another product, of course, is that video IP phone that CROT has developed, which is there, using post-quantum cryptography in that. That is now ready for transfer of technology. So we are trying to approve the transfer of technology so that CROT could actually transfer the technology, and there are multiple agencies involved in it, interested in taking it forward. So that is one that's been done. The other is the inline encryptor, post-quantum inline encryptor. That is also an advanced stage. I've done a lab demonstration of that, but of course they had some challenge with getting the cards manufactured in the country, Make in India part. The Indian vendor could not do it, and I think now they're going for a global tender. I think that should be another product that should be coming about. And of course there's some work that with IISc Bangalore also we have done for the pure energy part. And another one is that device independent PQC, QKD, device independent QKD work that's happening. So there is traction within NSC to see that we build up the capability in the country and also have products. The focus in our organization is not to do basic research, but to have some translational research so that we have products that can be deployed in the field. There's a challenge here. When we start off, we haven't really thought through how would we actually productionize. So because we are basically looking at the research problem and then do it, but then subsequently we have realized in many of the products that we have come to a stage when the product is mature, how do you take it to the market? And that's been a challenge for us. And with the national quantum mission that is there, I think that is something that we should now at this stage think through the whole process, how to put in place the process so that as we go along and do the basic research and then the fundamental research and then the translational research, and how do we actually productionize is something that has to be done. So the radar part is another one that we talked about. That is another area that we have been looking at, and we're working with certain organizations in the country for a quantum-based radar. That's another project that's been funded from our organization. So this is some activity that we're doing, and hopefully as we learn, and that's all the learning curve. I mean, I'm not an expert on quantum, but we know that there's a requirement. That's one thing. We understand there's a requirement and then try to work with the subject matter experts and institutional experts which are there to see that those works are done. So if you have any problem statement that you understand that's required to be solved, please do come and approach us, and then we'll work with you. Thank you.
Thank you, sir. Thank you on that. I think we have now 14 minutes left. So I can put one more question maybe. So one is that most of the security agencies around the world, like CISA, NISA, ANSSI, NCSC, BSI often have told that they recommend that business and government should move to quantum safe, and there is lack of awareness still there. What do you think? How do you create awareness that at least the critical sectors should move into quantum era? So, I think Nokia, Dell, anybody can take it.
I think it's the quantum resiliency threat is real. I mean, it's in front of us. I think we have to take a very simple logical approach, which is to prioritize and which is to ensure that smart grid, financial institution, defense.
But how do you tell them? I mean, that awareness, how does it come?
I think awareness will come by telling them the impact, and we all know the dire impact, especially in the current geopolitical situation. It cannot be more real. We have seen there. I mean, I was reading a report which said that last year, and these are official numbers, there were around 350 government sites which actually suffered the cybersecurity attacks. So the threat is real, and it's in front of us. So we have to acknowledge that, and now we have to take a very, very pragmatic approach and see that these are the priority systems. You talk about telecom, telecom is actually a critical infrastructure. You talk about defense, you have to start building the plan for making them quantum safe. I don't think we have a choice here. I mean, that's my honest opinion.
You would like to present?
Absolutely. So I agree with Manojji. Okay, see, the fact remains is that currently, so we've been very late to adopt encryption. And to be honest, if Google Chrome, Microsoft Edge, and all these other browsers had not stopped web pages from loading completely, okay, if they were not encrypted, if the connection was not encrypted, most of the government websites would still be, not using HTTPS. They would still not be doing it. And we actually see that as a fact. We see that some websites are still using it while they're using HTTPS. The certificate has expired because it needs to be renewed. The fact is that everything that we do, store, and whatever is encrypted, is just a few years away. It's a ticking time bomb. It's just a few years away from being decrypted completely. So the sooner we move to stuff that is, like for example, vector-based algorithms, encryption algorithms, the sooner we move to those, quantum-proof algorithms, the lesser we are becoming, the lesser exposure we have. We already have a huge exposure, don't get me wrong. I mean, we are completely exposed. Everybody is completely exposed, not just us. But we will be limiting our exposure for future, challenges.
Yeah, thank you. I think the another thing is, how do you encourage critical sectors to conduct trials so that if the trials are done based on the feedback, the equipment can be developed, indigenous equipment can come in, and that we can pitch in.
Yes, so see, the fundamental thing is that quantum computers are yet to be designed. So if something is yet to be designed, the thing is how to basically do a field testing of it. So technically, the one measure that, or a proactive measure that you can take to ensure that you are in the right direction or you are in the direction of adopting the quantum safe approaches is to basically have that environment or infrastructure that is quantum ready and follow these algorithms, or maybe first of all do the assessment of all the risks that are present or all the assets that you have, and what are the assets which are being highly relying on the cryptographic technology. For example, you mentioned that we have certain data centers and which are being encrypted using certain keys and so forth, and you have some backup of data to be kept because there are certain regulations which ask you to keep the backup of 5 years and 6 years down the lane for any reasons, for any audit purpose also. So the idea is to ensure that if you do a right set of analysis of what sort of cryptography that you are using, what sort of asset that you have, and then to be prepared to remove that cryptography in phase or plan out fashion. I mean, not everything can be executed in one go. It has to be a phase out manner. So you do the risk analysis and then change the cryptographic approach to the one which is, let's say, in the verge of finalization or standardization. So you would have the real essence of when you change this approach impact of you or your application working in that scenario? What is the performance impact around it? And if there is a need to change the algorithm, or if there is a need to change or improvise the techniques that are being used for, using or being in the verge of replacing the classic algorithm versus the quantum algorithm, you would have a fair idea. Like your application might have stopped working, it is not that performant efficient, or your entire ecosystem is not that well tuned. So the idea is to start it in a phase out manner, do some sort of a testing of the assets which are very critical, rely on the concept of flipped analysis, NIST standardization, mathematic analysis to do some sort of a field testing around it.
Yeah, thank you. I think now we move to DRDO. See,
इसमें कुछ बोलूँ ना?
हाँ बोलिए सर, हाँ बताएं सर.
Okay, I think the point here is, I think from the ideas that have been presented, one thing that comes out is that there's a sensitization that's required. Normally, I take this example in many places. Highway में जब जाते हैं ना, you have a speed breaker that comes around, and you go to the history of that speed breaker, you find that there was an accident and so 4 or 5 people have died there, and they put the speed breaker there. That's normally what happens. Now we come to the critical infrastructure. How to make those people that put these all these safety measures in place? Do we wait for that accident to happen and then they realize and then they wake up and they said that these are certain measures are taken? That's not something you can enforce. That means that there's a lot of sensitization activity that has to happen, and for that I think this is an interesting research problem that we should have to create, like what should the roadmap or a migration path for a traditional database which is using traditional classical encryption methodologies. How would you migrate that to a post-quantum cryptography? Now that is something that we are not in a position currently to present to somebody and say this is how we would do it. I think this is one research problem that I think we should take up as typical enterprise database, and then work on it, that what should be the migration path.
Or what should be
then what should be the migration path? And then come and present it to organizations, say this is how it is, these are the financial implications, this is how much time it will take, and this is the pain points that you would have when you're going to migrate. When you could do that, I think that is something as a country we should start.
So do you think National Quantum Mission
should address
encourage trials and deployments and solve some of these problems?
See, one is you encourage people to give their problem statements, you evaluate based on their own capabilities the community has. They give you problem statements. They give problem statements and the solutions that they were working on. That is one way of going it. But then you have your own priorities as a country. Then you say this is a problem statement. Now I'm asking for partners who will come and then work on this problem. I think this is one problem statement we should invite proposals for people to work on. And then out of the submissions that come, select 1 or 2 entities who would actually work, not one, multiple entities who would work on this and then come up with solutions. So this is an important point.
I'll ask you one more question.
Yeah.
There's a debate between QKD and PQC. The US, the DRDO was reading out the statement of NSA saying that don't move to QKD, come to PQC. What is your opinion about it? Don't be diplomatic.
No, I'm not. Can I answer that? Yeah.
No, we'll first take him.
Frankly, I'm not a guy who has insights or in-depth knowledge of quantum. I started off from that premise, okay? And to say that one is better than the other is something I'm not in a position to answer. I'll be very frank on that. I'm really, and I think he's the right person.
Very sure, sir.
Yeah. So I think first, So I think I'd just like to mention, see the attackers now what they attack. So I think there is also one equation that the gain they are getting, if the cost is more than the cost spent in attacking, that only they will attack. Okay, so we need to classify the things. It's not that everything you put everywhere secure. Okay, so I think we have been debating this point, QKD versus PQC. And in fact, I was doing QKD and one of my colleagues was doing PQC. So always we used to work together and we used to fight. So then we have come up with, we have a classification of information. So there's a top secret, secret, and then confidential and restricted. Okay. So up to restricted you can use PQC only, and then confidential and secret you will have to use, if you want theoretical secure, you suggested to use QKD, and for top secret you have both and do XOR. Okay, so I think that may be
hybrid is the solution.
Yeah, hybrid at the top, and then it depends like what type of assets you want to secure. So even at present in defense, we even don't rely, though we don't have powerful computers, still we don't rely this classical asymmetric systems, because whatever we know, it is available in public domain. Who knows that there might be efficient algorithms, classical algorithms, okay, which can factorize large number. How can, there's no proof that. Okay, that is why we have some setup of trusted courier sending manually the things. But I think if the QPD comes, and then we can get the confidence that all this is mathematically proven and all, that can be replaced by the QPD, but not by the PQC. Only either you go hybrid or use QPD plus QPD.
One question on
I think in the interest of time, I think I have left Sridharji. I think critical sectors we all talked about is a necessity, but finally quantum has to go to masses, right? So what is that, what is your advice to an enterprise, what practices they need to follow in terms of, these practices get adopted to enterprise and then come to the masses?
So the enterprise adoption in India is not much, whereas if you take countries like US or Europe, there is an executive order that mandates them to look at PQC and QKD infrastructure, especially PQC in the US. And so all these private sector enterprises started looking into these algorithms now. So we have a lot of public information where many enterprises started working on PQC. Most of the telecom players have got some solutions or offerings around PQC or QKD now, or they have at least done trades. But that has not happened in India yet. Probably we would require a regulatory push and followed by a policy push for support. So both will help for people to try out, and events like this should have CISOs from all the Indian enterprises. So that is missing in this.
So I think it was a wonderful view from the experts. Now I open the floor to the audience for your questions, please.
Just one question I have. There is nobody from CERT over here, but we know that around 350 sites have been hacked last year. My question is, if anybody is aware, how many were hacked using Short's algorithm? We have been talking about Short's algorithm.
No, the websites can be hacked even in classical way. You don't need quantum computers to hack the website. What you need is the quantum hygiene in your website. If you don't use, like he said, HTTPS, you don't use the proper certificate, you keep your without firewall. So these are the problems of the classical era itself.
I know that there may be many options, permutations, but the sheer number of it and the sheer sensitivity.
No, that is only reported one. The actual number will be much higher.
That will be much higher.
Yeah.
So I am sure, and we are all under Short's algorithm, so there must be some connection. And we have to decrypt that, and the way that you are telling that how the governments have to sensitize. This is the beginning. Like as you said, CISOs should be there. Yes, they should be there. And then if you really know about it, then once we have to show the threat, then solutions will come. Just we try to propagate it more. So I think that needs to be seen. How many were done with Short's algorithm and how many done by what means, and that should be.
No, I don't think you need Short's algorithm to attack the website. This can be done with the cyber hygiene. Yeah, Mr. Rao.
My question is to Mr. Manoj Moldani.
How is your mic on करिए? क्वांटम कर लीजिए.
Just you have launched Joint Sensing and Communication Lab in Bangalore as part of that innovation. So what do you think the difference between the quantum sensing and your joint sensing and communication which we are starting for 6G? This is the first question. And can we add something from quantum sensing to joint sensing and communication in the 6G for with RF? So what is your opinion?
I think it's a great question. So joint sensing is again a research. I think it's not working, but I hope you can.
It is entanglement.
Entanglement. Yeah. Still some connection is there.
No. I think most of them are off. You just switch them off. Others just switch them off. Yeah.
Oh, okay. Now you can. So joint sensing is again a research topic, and we are working very, very closely. I think for a country like India, it's got a great use case because you don't need physical sensors, right? The network itself acts like a sensor. So that's the beauty of the joint sensing. There are great use cases. We are talking about health, and so let me give you an example. A senior citizen, for example, who's not carrying any phone, he's not wearing any wearable. Joint sensing can, with the aid of AI ML, can kind of predict the falls. You know, I can predict your heartbeat, right? And all that can happen. So, you know, you can see for a country like India, it brings huge societal use cases. Now, the thing is, it is RF based because, you know, it's basically what we're trying to do is we are using network itself act like a sensor. Quantum sensing is completely a new topic. It requires a lot of cryogenic kind of environment, right? So I think this is still a research topic, and that is what we are trying to come to. I mean, can we kind of have a convergence in these two topics? If you are able to, then it will be great, because what quantum does is it brings great amount of accuracy. So,
anyone else?
What about low SNR radar? One question from Mr.
Yeah. Yeah, so if we see the quantum sensing, basically there are three approach. Okay, so the first one is, as we know that we are creating qubits, they are very fragile. Okay, so if we do just measurement, any environment perturbation will change their state and you do just measurement. Okay, so that is the first approach. The second one is you create an interference between two and then try to read the phase. Okay, and the third is getting entangled. You create entangled and then correlate the information and get the. So I think the third gives the highest, and you can reach up to the Heisenberg uncertainty. Otherwise, we are all limited by the short noise. Yeah. So I think that would most accurate sensor would be using the entanglement and then these qubits.
Yes, sir.
My question is to Mr. Sridhar. You talked about use cases, quantum use cases. So, what is the state of these use cases? Whether it is matured and it can be put to the standardization world for making it a standard?
No, as I mentioned, so none of these use cases generate ROI today. So these are at the state of experiment level. So it all depends upon how we get quantum hardware down the line. Right? So we are hoping, so if we get 1000 qubit hardware, so that is when we will be able to do a decent set of use cases. Right now we are hovering around, even though we claim so 1000 qubit quantum computer is available, the real quantum logical qubits that are available are under 20. So with that we will not be able to do much. And we have simulators which are actually powerful than the real quantum computers today. So with that all the experimentation is going on today, which sets the roadmap for future. But again, so once so these are initial evidences, so theoretically you will get advantage. So now we are proving in small experiments that there is advantage, trying it even on smaller quantum computers and building the algorithms. But it is not, maybe it is too early for standardization with respect to the quantum computing algorithms.
Then the next question, timeline you expect that it should be ready for standardization?
So the roadmaps given by companies like IBM, etc., are Google, so million qubits roadmap by 2029. So that is the roadmap that they had given. Again, we have seen 2-3 new players who are giving 1000 qubit quantum machines this year. So they're surprisingly they were not even there a year back, but suddenly they came and claimed 1000 qubits. Let's assume with 50% probability we will see some commercialization around say 2026 or 2027. That's what IBM CEO says at World Economic Forum. So we'll take his word. So yeah, we can look at these algorithms now, and the standardization of algorithms are mostly people are trying to put patents around the methods as of now for these algorithms. The abstraction is happening in some way. There are some niche players who are also working on the abstraction of these algorithms, and these algorithms, the abstracted algorithms, are good for standardization. So that can happen sometime soon, maybe 2 years down the line.
Last two questions, because madam is already started looking at me. So we'll, memento and all, everything we have to finish by 6. So, 2 last questions.
Yeah.
Murli.
I know that last 2 days we are dealing with quantum communications, security and all those products. But I have a little curiosity to know, is it the only solution or we have to think ahead over a couple of decades at least, or anything beyond or equal to quantum security, anything that is also visible or within vicinity?
See, everythy works with the business. As in fact, Mr. Sridhar said, there is no visibility on ROI, but still every organization is spending money. Nokia said there is a market of $106 billion by 2040 and $1,300 billion in the downstream market. So you have to look there and invest, and therefore, you know, whether.
Not asking in terms of ROI and all, but I'm just asking, is it equal or parallel to quantum, anything else also? Because it's in developing stage, evolving stage, and just taking a shape. Is it only quantum or anything beyond that?
No, it's real. I mean, whatever is being talked about is real. The only thing is I can say the way we had semiconductor industry in 1950, we are at that stage today. The semiconductor from 1950 to 2023, where they have evolved. Nobody would have thought in 1950. So we are at that stage, and it is real. Means the whatever is happening is real. The ROI, even if it's not there, companies are investing, governments are investing, because you know, there are possible winners. You look at the possible winners today in semiconductor industry. Those who invested in the beginning got the leaders today. So as India, as a country, we need to invest irrespective of whether it makes sense today or not. And it is a near reality, as he was referring to, that you store the data later and harvest, and you still get the missile information, nuclear information. You want to pitch in something?
Yes. I think the question. So I think just to answer your question, you mentioned whether there's something better down the corner, right? I think that is what you were trying to get at. Honestly, quantum mechanics is how nature works, right? So if you see how we smell, how birds navigate, right? How how creatures evolve. Let's say a caterpillar to a butterfly, or a tadpole to a frog. All of that is quantum mechanics. So if you ask me, is there something which is better down the corner? The answer is not really, not in our civilization, because this is how the universe works, right? Does that answer your question, sir?
And nobody can predict. Actually, today it is quantum. Tomorrow it could be super quantum. We don't know. As of now, it is today quantum.
2 decades down the line, you might.
We don't know. We really don't know.
Sir, I may add one topic on the emerging technologies. Right? It may not be super quantum or pure quantum. We don't know what it is, but there is also another team at TCS that is working on neuromorphic computing. So which is more of putting the algorithms on neuron type kind of cells in a microprocessor. So that's another exciting area.
So we take the last question of the day. Ehtisam, yeah.
Thanks for.
तुम बहुत क्वेश्चन पूछ रहे हो हाँ नहीं बाकी सेशन में बहुत पूछ रहे थे अच्छी बात है
Sort of an academic question only, sir. Now with the help of this legacy computing power, we are able to make such smart AI engines. So if can the quantum computers be used to make super smart computing AIs which can successfully break the quantum keys?
No, as he said, the quantum computing computational power will help in doing good in terms of molecular discovery, forecasting, and as of now, the algorithms, the QKD as well as PQC are supposed to be safe. What happens tomorrow is matter of debate. So thank you so much, my esteemed panel. I think you did a wonderful job touching various things and bringing different perspectives from the government, from the defense, from an operator to Thales enterprise. I think it was a wonderful thing and wonderful audience. You asked wonderful questions, and definitely next year, I think next year again we'll meet. We'll have more questions, and so from our side, the panel is closed. Thank you.
Thank you, sir, Dr. Rajkumar Upadhyay ji. So, ladies and gentlemen, that was a panel discussion on applications of quantum technologies, deployment perspective and use cases. So now I think we should felicitate our panelists. I would request Dr. Rajkumar Upadhyay ji to kindly felicitate us, all the panelists, sir, starting with Shri G. Narendranath ji, Joint Secretary. Sir, as you feel comfortable. For photo op, I think it's better if you can just come forward. Yeah, please, sir. So now Dr. Rajkumar Upadhyay ji, CEO of C. will felicitate and thank all our panelists. Certainly, sir. Shri, I already announced the name of Shri G. Narendranath ji, Joint Secretary, National Security Council Secretariat. Our next panelist, Shri Amit Srivastav ji, Scientist F Research Center, MRR DRDO. Shri Manoj Gurnani, Chief Technology Officer and Head Strategy, Nokia India. Shri Saurabh Tiwari, Chief Technology Officer, Dell Technologies. Shri Sridhar CV, Head Alliances Corporate Incubation Tata Consultancy Services. Although it's been said ladies first, but now we have Ms. Tableen Obroy, Senior Solution Architect, Thales Cloud Protection and Licensing. And we also thank Dr. Rajkumar Upadhyay ji, CEO of C. Thank you, sir. Thank you so much. And we thank all our panelists. Thank you. And now for word of thanks, may I invite Shri Vinod Kumar ji, DDG Quantum Technology, Telecommunication Engineering Center. Sir, please. Yeah, sure, sir, please. Even you can join in, sir.
Good afternoon. On behalf of TEC, I would like to thank Dr. Rajkumar Upadhyay, CEO C. For chairing the panel and very nicely moderating this panel discussion. The panel has very nicely brought out the use cases and applications of the quantum technology and the challenges in implementing the quantum technology in the networks. I would like to thank all the panelists, Mr. Sridhar CV from TCS, Mr. Manoj Gurnani from Nokia, Sri Narendranath ji from SCS, Sri Amit Srivastav from DRDO, Sri Saurabh Tiwari from Dell Technologies, Ms. Tableen Obroy from Thales. I would also like to thank we had our exhibition hall, 7 exhibitors from exhibitors from CDOT, QNU Labs, Keysight, Silicofeller, Thales, SkyTel and QPI. I would also like to thank all the speakers, participants and media for gracing this event. I would like to thank the organizing committee from TEC, CDOT and TSDSI. From my team, Rakesh Goyal and Ram Raju Chillehi, they have done very tireless job and they have put all the efforts to making this event successful. Sir, your team was also very helpful into this. And Madam for guiding us and supporting us to hold this event. And thank you everybody. And all those sitting here, are special thanks to you to staying till last discussion. Thank you very much.
Thank you, Shri Vinod Kumarji. And with this, ladies and gentlemen, we conclude our two-day event, that is Second International Quantum Communication Conclave. We thank you all for joining in for today's. Thank you so very much. Namaskar, Jai Hind, Jai Bharat.